¿no? Hola.
Good morning, everybody. Welcome to the third day of our workshop, Mexican workshop of the Mexican Division of Particles and Fields. And today morning we have a very special session because due to the lockdown that we suffered the last almost 3 years, it has not been possible for us to give the award of the medal of the division. So today morning we are giving 3 of these awards. One it was already given last summer. Sorry, I was running. Well, our first speaker is Dr. Alejandro Ayala from UNAM, Institute of Nuclear Science, and I will give him the medal, 2019 medal of the Mexican Division of Particles and Fields, and it's very, very well deserved, and with a big recognition of the community. Congratulations. And your diploma. Yes. So for the photo? Yes. So at that time, the president was Eduardo de la Cruz, and the vice president was Salvador. So that it was, it's very strange this for me to give you, but it's okay. So enjoy. A big applause, please. So let's start with your talk. You are going to move the slides from the computer, and I will let you know when it's. Thank you.
Karen, and of course to the Division of Particles and Fields. It's a great honor to be awarded this medal. I've been part of this community for a long time already, as you can tell from my gray hair. And it's been a pleasure to see how it has developed over the years, how many good students, high quality research has been developed in the time that I've been part of this community. So it is a great honor, and I really appreciate it. And I hope that we can continue having these fruitful interactions for many years to come. So thank you again. And with this said, let me start with the formal part of my presentation. What I want to tell you a little bit about today is on some recent research that I've been conducting with a group of colleagues in the general aspects of the phase transitions that strongly interacting matter can undergo when subject to extreme conditions. So this is the title of the talk, and this has been this is paper that has been conducted over many years with many colleagues from even present. So before I go into the details of the specific research, let me just put it into context. What we are interested in general is to study the phase transitions of strongly interacting matter. So let me start by discussing a little bit about what is or how we envision to study this phase transition. A little just recall that phase transition is a transformation of a substance, any substance, and strongly interacting matter is a substance in that sense, from one state to another. And during the phase transition, some quantities change, and often in a discontinuous manner. So changes result in variations of external conditions. For instance, in the case of our well-known system of water, when we vary, say, pressure and temperature. So when does a phase transition happen? Well, you see, this is a matter of a technical definition. The way we identify a phase transition is by looking at the free energy of the system, the energy which is available to do work. And so if one of the derivatives of that thermodynamical quantity diverge, then we uh, give names to the phase transition. So, for instance, if the first derivative diverges, it will be a first order phase transition, and so on. So, in general, it is true that we often call this the thermodynamical limit, in the sense that the phase transitions happen when we have a system with a large number of particles. I will come back to this point in the case of strong interacting matter, because when we are talking about a large number of particles, we usually have in mind vacuum instead of real particles. You can imagine this may not be the case, for instance, in an experimental setup such a relativity theory. So, in general, phase transitions don't happen when the system is very small, so volume approximation may be very important. So we say that a phase transition happens when the free energies in both phases, more than one than two phases coincide. And sometimes it is possible to change the state of substance without crossing a phase boundary. And in that case, we call this as a crossover phases. So with these generalities having been said, let us just touch base in for the case of the theory that describes strong interacting matter. And this, as we know, is QCD. So what is QCD? QCD is a gauge theory with a local symmetry based on the SU NC, where NC is the number of colors. We know that this up to the energy we've been able to study, NC is equal to 3. And the fundamental fields are quarks, gluons, of course, anti-quarks, anti-particles. And we have a number of flavors, quark fields, NF flavors. We know again that up to what we know, we have 6 flavors. And the idea is to build a theory which has these properties, this gauge invariance, for these many colors and flavors. And this is QCD, and here it is in all of its glory. Well, not all of its glory, but you know that this is a complicated piece. It's a non-abelian theory, and it has many symmetries, and in particular, one of the important ones, which I will pay attention here, is in the limit when the masses of the quarks, the fundamental fields, go to 0. In that case, we have a global symmetry, which is called the flavor symmetry. As you know, this can be converted into what we call the chiral symmetry. So, in fact, it's chiral symmetry what is responsible for the observed atomic spectrum of low energy. So, this is the fundamental object that I'll be looking at, this Lagrangian, and in particular, I will be concentrating on the chiral aspects of it. So, with that said, then let's put both things together. And the way we can study these kind of systems, in other words, strong interacting systems, in a comprehensive manner is to construct a representation of the different phases that this strong interacting matter can take. And in this case, let me just draw this cartoon, which consists of a two-dimensional diagram, in which in the vertical axis we have the temperature, and in the horizontal axis we have the baryon chemical. And as you see, we have lines here which try to represent the phase transition lines. So in particular, if we go to the situation in which at, say, usual densities and temperatures, that we experience them here on Earth, we have nuclear matter at low temperatures, basically, and at a given baryon density, which is different from 0, in the sense that we have more quarks than anti-quarks, so we have more baryon density. If baryon number was 0, then the chemical potential would be 0. But that's not the case in our world of usual circumstances. And so the idea is to try to explore all of these diagrams here, and in particular, these have been done successfully with experiments, which have explored some region of this diagram, in particular, going through some phase boundaries, and this line here, which is this dotted line, tries to represent a crossover transition, which we know is the case for low baryon chemical potential value. But you see, the conjecture, and this is why this is a cartoon, the conjecture phase diagram seems to have a very rich structure. In particular, it has been speculated that at large baryon density, large baryon chemical potential, and low temperatures, the phase transitions are of first order. And if that is the case, if we continue this line here, we should convert this first order line of transitions into a crossover, and therefore there should be something that we call a critical point. So let me emphasize that the kind of transitions that I'm looking at right here in this line correspond to the chiral symmetry restoration density. So what if we go from low temperatures and low baryon chemical potentials up to the situation when temperatures and baryon chemical potentials are higher, then we make such a transition in this line in particular. From here, it will be the chiral restoration. But there may be some other. And in particular, one we could ask ourselves, well, is chiral symmetry one kind you can find it. And this, of course, happens at very large values of chemical potential, and it may be studied in other contexts. For instance, when you look at the properties of dense compact physical art. So again, just to summarize, it seems that there is a large, a rich content of thermodynamic properties of this matter when we study it in terms of this thermodynamic ability. And this is illustrated even better here in this more colorful cartoon. It's the same kind of diagram that I just showed. We know or speculate that these transitions may happen if it exclusively as an implicit state, which is for lambda. And this lambda class is of the fundamental state that will not be persistent in the case of this value class. What I'm saying is you make a simulation of the population of the QCD phase diagram by a merger of two neutron stars with certain parameters, of course, after certain time. So this is a short time after the merger, this is a larger time. But then you see that these lines here, in the temperature versus density, given in terms of the saturation density, you see that the phase diagram also goes certain population. Okay, sorry. I hope I don't have to repeat everything I said. Please tell me if I do. So you see, there are more systems that can be also studied and that can provide complementary information. But that's not the whole story, of course, because see, what I've been telling you about has to do with this axis, temperature and baryon chemical potential. But there are other control parameters, and those other control parameters, of course, may be also present in systems that nature provides with. And one of those control parameters may be the imbalance between the number of quarks and antiquarks in a given physical system. This is quantified in terms of the so-called isospin chemical potential. So we could put that extra axis here and study what is the way this strongly interacting matter behaves under the circumstances when we vary the imbalance between quarks of one species, one flavor, say U, and another flavor, say D. So if we do that, we can also find a rich structure of the phase diagram. So overall, we have a multi-dimensional phase diagram, which is very rich to study. How do we study it? Well, there are two ways. One of them is looking at the skies, and with these gravitational waves messengers, try to also infer this kind of properties. But there is another way in which we can do it more in earthly terms, and this is studying relativistic heavy ion collisions. So let me again go back to the two-dimensional phase diagram and just show you that in terms of temperature and density, this has been already the program to explore the properties of strongly interacting matter is a rich program and has been conducted over the last at least 30, 40 years. And when RIC came into operation at the beginning of the century, the program got a boost. Of course, it also had a boost with the starting of operations of the LHC. And the way we have been exploring this phase diagram with these experiments has been a very successful and rich program full of results. And one of the things that we've learned is that at least close to the temperature axis for low densities, which we achieve when the energy in the collision is large, because of this property of nuclear, which is called transparency. Nuclei just pass through each other and leave behind a region of excited matter, which is mainly composed of almost the same number of quarks and antiquarks, and therefore low baryon density. So this region has been explored, and it has many results, which I will come to mention in a few slides. But you see, overall, even though this program is very rich and very successful, one of the things that still remains to be explored is whether or not this critical point that I talked about exists. And for that, some experiments, current experiments, and future experiments will be exploring deeper into the phase diagram, in particular in the density region. How? Well, what we want to do is to lower the energy in the collision and therefore increase the density to see whether or not we can explore such a situation. But to be honest, this is terra incognita. Nobody knows. There are many efforts, both from the experimental and theoretical points of view, but there are no definite conclusions here in this region, and therefore it is very exciting. And the next years will also provide clues and a deeper understanding of these kind of systems. So again, what I've been talking about has to do with the properties of QCD vacuum, and in particular, what is the kind of transitions, phase transitions, when we go from the situation which is closer to nature, as we know, in under ordinary circumstances, to the situation in which we have extreme conditions. So, as I mentioned, one of the key questions in this business is whether or not this critical endpoint exists, and what it is. Is it here, close to the temperature axis? Is it here where we say or we think that the two transitions, the confinement and final restoration phase transition, split? What is it? And of course, there have been many efforts over the years, and some of them are provided by lattice QCD, which is the handle, the theoretical handle, which is better understood. And using that technique, what we know is that the phase transition close to the temperature axis is a crossover. It happens for zero baryon chemical potential at temperature of order of 150 MeV. And if we try to explore deeper into the phase diagram, what we find with those techniques is that up to the region of validity where these techniques are appropriate, we haven't found the critical endpoint. I'll come back to that, perhaps just touch upon that, but lattice QCD cannot be employed for large baryon chemical potentials due to what we call the sign problem. The measure for the Monte Carlo configurations needed to sample these systems in using lattice techniques becomes imaginary, so it cannot be useful to to provide results, not even reliably, even if we try to go around this sign problem. The noise is very large, so it's not possible to get the results. So overall, it seems that lattice QCD has provided some boundary, so it depends, depending on what is the temperature of the phase transition, the estimate for the biochemical potential divided, critical biochemical potential divided by temperature is such that it seems that we haven't yet found that critical point. So it is one of the driving forces. The finding of this critical endpoint is one of the driving forces in the field. And now let me switch gears to try to describe what is the kind of techniques that one uses to try to localize this critical endpoint. You see, when we call or when we talk about critical or criticality, what we have in mind is fluctuations. And in fact, near the critical region, we should expect large fluctuations on something. This is no exception. What we want to do in this business is also to focus on fluctuations and to see how we can extract information. In particular, near criticality, the properties of the created medium should show fluctuations which deviate from the Gaussian fluctuation. You see, when we have a statistical system in the large number of particles, say, we all love to describe the statistical properties in terms of a Gaussian distribution. But it so happens that near criticality, this picture is not correct. And the physics behind it is that the correlation length increases a lot. So we need to look for something which is a signal of deviation from Gaussian behavior. And there is, of course, a connection with the thermodynamics, because the property that we want to, the function that we want to look at is, of course, the partition function, or more precisely, the logarithm of the partition function. And this is also related to what we call the cumulant generating function. And so what we want to do is to do statistics, thermodynamics, statistical dynamics, and look for the cumulants in a certain conserved quantity. This is the average using the statistical distribution that can describe the system. One of the important properties of these cumulants is that they depend, of course, on the volume in this fashion. So they are extensive quantities, and the coefficient of proportionality is called the susceptibility. It's a generalized susceptibility. So the strategy is to look for these susceptibilities, for these cumulant generating function, or the cumulants themselves, and to have proxies, experimental proxies, to measure them and therefore extract information about the system. Two important higher, and you see, if we want to look for fluctuations which are not Gaussian, we should look at cumulants of high order. So this N here should be of high order. Two important cumulants are the skewness and the kurtosis, and in order to have a better idea of what these are, well, basically, although it's not really precise, but basically, the skewness characterizes the way a distribution is skewed. And the kurtosis basically tells you how wide and how thin the distribution is with respect to a Gaussian distribution. So when a stochastic variable is normalized to the square root of the variance, then the skewness and the kurtosis, which are these important quantities, are given by the third and fourth order cumulants of the distribution. So the kurtosis is, the cumulant, the skewness is the expectation value, the kurtosis expectation value of the third power of the average, and also with this quantity, and the kurtosis is the fourth order P. All right, so with all this said, of course, I know that I went fast in this last part of the talk, but nevertheless, this is just to set up the stage. What we want to do is to look for these high order cumulants, and if we take the ratio of these fourth order to the second order, which coincides with the variance. Then the ratio is given by the product of the kurtosis times the square of the variance. And when we are in the critical region, what happens is that this product deviates from the one. So what we want to do is to look at how the given observable, some conserved number in a heavy ion collision, behaves as a function of the energy in the collision. Because you see, for large energies, what we should be expecting is to have something which is closer to a Gaussian kind of statistics. Whereas if we lower the density, the energy, and therefore increase the density in the collision, then we will perhaps reach the region in which we have criticality, and therefore these fluctuations should start showing up. This is the strategy. And let me just try to see if I can understand this from a simple point of view, because see, it's such a complicated system that there are some theoretical guidelines in simple terms, maybe very relevant. And as you probably know, you see in the low level as at least it's easy in the sense that the appropriate use of freedom describes the basic property of low energies, which is this kind of symmetry. So this Lagrangian, although I'm not showing it here, but please believe me, has this chiral symmetry, and if I implement the spontaneous breaking of the symmetry, which means that the vacuum state does not share the same symmetries as the Lagrangian, then with this breaking of chiral symmetry, I can write down the Lagrangian, and it is of course a little bit more complicated, but what I want to emphasize that is that the degrees of freedom mesons, sigma and pi's, and quarks, this size here, acquire masses, which are given by these terms in red here. And of course, they interact, and there is a Lagrangian of interaction. And so we can implement chiral symmetry in a simpler manner. And that simple matter is to compute in this theory the partition function, and that requires the computation of effective potential at final temperature and data density. And if we do that, then we see that with the Lagrangian I just showed you, we have the contribution from the tree part, that is the classical part. Then we do loops, and we can do boson loops and fermion loops, but that's not enough, because see, what we want to describe are these fluctuations which near criticality diverge like crazy. And these can be implemented if we recall that in a plasma, what produces these fluctuations are in general the infrared properties of the plasma, and these are captured by this extra contribution, which is not analytical in the expansion of the coupling constants. It's called the ring diagram contribution, and these are the expressions for these objects. Notice that for the ring diagram contribution, we require to compute what we call the self-energy for the bosons, and this is the large temperature approximation. This is the cartoon of the ring diagrams. It looks like a Mickey Mouse here, which is again turned back and then added more and more years here. And so if we resum this series, we can get the previous expression, and the result of doing it is to correct terms which are offensive. You see, if we just look at this simple Lagrangian here, we can imagine that there are contributions of this order parameter, this vacuum expectation value, the variance with temperature and density, that make this combination to become zero, which is chiral symmetry, or even negative. So the square mass of the pi can become negative. That is not acceptable. We will have vacuums in the system. So the way we cure that is by adding this ring diagram contribution, and therefore there's a window in which this squared mass of the bosons cannot become negative. And because of that, this square root to the third power does not become imaginary. So the effective potential is stable, and therefore we can use it in order to see or to explore how the phase transitions look like in the phase diagram temperature and density. And this is an example. So if I draw with this theory the difference between the effective potential as a function of the order parameter here, you see that when varying the conditions, the chemical potential and the temperature, we get a first order phase transition for large values of the chemical potential and low values of the temperature, identified by this here, this hump here, between two minima, which is the signal of a first order phase transition. Before we reach this point, and when we lower the temperature, we always get cross order transitions. Here, the proxy is second order phase transition. And so if we do, for instance, if we compute the probability distribution associated with these statistics that we just found, we compute the partition function. Here it is a partition function with that effective potential. This is a volume. And so we plot the probability distribution as a function of the order parameter. And we see what we were expecting, that when we approach criticality, this red dotted line, the system starts changing in such a way that you see we got two maxima here, whereas from second order phase transitions or cross order phase transitions, we only get a maximum center at vehicle zero. And this is the study of the fluctuations, in particular the kurtosis, and we see large fluctuations when we approach the critical value of the density. And if you put everything together, then you can study the phase diagram, temperature versus chemical potential. And indeed, what we find is that when we lower the temperature and increase the variant chemical potential, you get a first order phase transition for large values of the variant chemical potential. Notice it's really large, and the temperature is about 1/3 of the original temperature for zero variant density. And then we want to convert this to the way this can be studied experimentally in terms of the energy putting into the collision. And for that, we resort to some old calculations. The references up here cannot be seen here, but it's a reference from 2006, in which the relation between the temperature and the net variant density is for a couple of different conditions mapped in these kind of lines, where the numbers here tell you what is the energy in the collision, measured in the center of mass and in GeVs per nucleon. So this square root of S and N. The parameterization of that curve is given in these terms. And so the idea is to convert chemical potential to energy in the collision, and therefore have a handle in which we can follow this study of fluctuations in terms of the energy in the collision. And we did, and so you see that for large energies, we should be getting, in other words, there is no deviation from the Gaussian statistics. There is no deviation from 1, as you can see here. But when you lower the energy, something interesting is happening. So this product of kurtosis times standard deviation starts behaving in such a way that it's not monotonic anymore. So it comes down and then eventually shoots up. And if you do a close-up here, what you get is that this shoot up and then lower down happens when, for these values of the, for instance, the volume, shows the critical point that we found from this other analysis, that is, in other words, this point. So you see that with this fluctuations analysis, in this case for baryon number, we are getting what one should be expecting for the behavior of fluctuations near criticality. And in fact, this is very interesting because some recent results on that same number, baryon number, which is in this case proton number, a very good proxy for baryon number consideration. You see recent results from STAR and with the hardest point added here show a very similar result. In other words, we have Gaussian-like behavior at large collision energies. And then at some point, for central collisions, 75%, we get an increase. The STAR program has not yet reached this region here. The lowest energy point is about 7 point something. And then the hardest point here is near 2 degrees. So something similar is happening here experimentally. So shooting up and then it's, which is similar to what we're finding here. Now, let me just recall or remember that our calculation is made in the strict chiral limit. Pions are massless. So we need to improve this calculation and an explicit symmetry breaking term. So the results are encouraging, especially if we compare them to this experimental results. So how do we go about? Well, of course, STAR has a very rich beam energy scan program, beam energy scan program 2. And so the analysis is underway. It's going to be very exciting when these error bars increase and everything seems to be working fine. But there is still a region here which needs to be explored right here. And this is, of course, task for the future. And there are many dedicated experiments that will be looking at that region. I already mentioned ADES and the STAR, the beam energy scan program here. And what I'm showing here is a plot in which in the vertical axis I have the interaction rate in this collider mode or even fixed target experiments. And in the horizontal axis, I have the collision energy. So you see that with collider mode, STAR, of course, they also have a fixed target experiment, which is very interesting. I'm not going to speak about that, but in collider mode, the interaction rate, so for luminosity, is low. Fixed target experiments, for instance, BMON, baryonic matter at the nucleotron, has a better interaction rate, and we can explore at lower energies here. Hades is also doing a very interesting result, but what I want to mention here is that there is this new experiment, the multi-purpose detector, which is supposed to start in about 2 years' time in the NICA complex, the nucleotron ion collider facility in Genoa, in the city of Dubna, which also will be very competitive for this energy range in terms of the interaction rate. And therefore, a group of colleagues from Mexico have looked into taking part of this experiment, and these are listed here. And see, the idea is to build a collider, which, a collider and an experiment which measures in the interaction point the products of collisions of heavy systems. And if everything goes fine, this and things are in schedule, these are the approximate dates when we expect that the complex enters into operation. So this is the collider, and this is the experiment, MPD. For the future, there is a plan to also build another one, which is called SPD, dedicated to spin physics. And this is the schedule. Of course, I'm not going to stop very much here in the schedule, because this will be the subject, or it will be mentioned in greater detail by Victor Yabov, which is a spokesperson in about, I think it's scheduled for 4 months. And this is the collaboration as of 2 weeks ago. We got together in Dubna, and we continued planning on the operation of this experiment. So let me just come to the conclusion. What I tried to show you is that the study of the QCD phase diagram contains very rich and interesting physics. Much of it is related to the situation in which matter is subject to extreme conditions. So we need to understand what is the nature of the phase transitions when we go from low values of these extreme conditions to high values, and try to understand what is the kind of many phases of strongly interacting matter. There is, of course, a large international interest in the field, which is shown up by the building of several facilities and also by the operation of current facilities, which are exploring this kind of systems in terms of area innovation. So deviations from the gas, which is kind of boring, that can be obtained in theoretically simple model which you implement. Let's see how the development of the is showing you the element this case of the nine diamonds, which I purely using the experiment effects of final temperature in the university. And the reference point is signaled by the divergence of this product, the process times standard deviation. And we find that, and I think this is a trend which is being generalizing the finding of the critical endpoint for large values of the varying chemical potential. This is important to stress. Maybe experimentally it may be a little bit out of reach, so we should keep this in mind. But the question I want to leave it as a positive question is whether or not this critical endpoint can be found at NICA or perhaps Hades. So with this, I thank you again. I thank again the Division of Particles and Fields for this great honor, and I hope that we can have a very large and rich interaction, strong interaction for a new future. Thank you very much.
Thank you. So thank you very much, Alejandro, for this talk. So are there questions? We have time. Pablo, please go ahead.
So thank you very much. It was extremely interesting for an outsider like me. So I would like to ask you about your plot on slide 32. So yeah, you mentioned that given the values of the temperature as this critical endpoint, it will be very important to include this chiral symmetry breaking effect. So it will be even more interesting when you get to this point. But I'm curious in slide 32, about the behavior where you expect this divergence, because all points you show were increasing, so signaling what you explained for a critical endpoint. But do you really see the divergence or just this deviation from one? It's just curiosity about that. Thank you.
Could you please use your mic, please? I am listening,
Again,
but
yes,
I don't know.
Sorry. I want you to focus on these results for the collisions of the heavy systems. These are gold on gold collisions, which are selected for the low impact parameter cases, which are not very abundant, of course, but they can be selected. There are some criteria to select it. So these are called 0 to 5%. These are the most central collisions. So these are the red points here. And as opposed to the most peripheral collisions, 70 to 80% of the total cross section, you see that these are flat. So you see that for large systems and at central collisions, you get some non-monotonic behavior. And there's a lack of data in this region. And these are also finite volume systems. So perhaps, as it happens, very often happens with these kind of results, you won't find an infinity here. There's no way that experimentally you can find it. In the thermodynamical limit, perhaps you could have a shot. But in this case, it's not going to be like that. But what we expect is a strong peak. And in fact, what I mentioned about our result, our theoretical result to compare to this data, can also mimic that situation, because if you go away from the chiral limit, in which of course you have this infinite jump, away from the chiral limit with the finite biomass, you also expect some smoothening of that behavior. And therefore, what I would expect, although there are no data here, is that you have a smooth behavior, a peak at some point, and then a decrease. That will be my expectation.
Thank you, Alejandro. Are there more questions? I just want to call especially the young students and the young people who are here. I noticed that with this talk, there is a lot of very basic knowledge that we learn at the faculty. especially of thermodynamics, no, the chemical potential and statistical physics and so on. And it was very clear how to use it for performing a very high quality, very high level research, and that it is possible to join all efforts, the theoretical point of view, the astronomical point of view as well, and also the high energy physics, together with the big experiments. So it is a very, very, very interesting to see how to perform this kind of research. And I am curious as well from the practical point of view, how much high performance computing do you use, and how easy is to get all the data from those experiments?
Very nice comment. Indeed, when I prepared the talk, I had students in mind. I know that I went fast, but it's impossible to convey, I'm sorry, to give you many details in a 1 hour talk. Nevertheless, I encourage you, if you want to approach me, and maybe we can have a discussion. Those who know me, and as I said, I'm old enough to have been around for a long time, know that I like simple things. So I like to understand physical systems in simple terms. And as such, of course, I also have questions myself. I have curiosity, and I'm always eager to exchange points of view and information. So coming back to, so in that sense, please approach me if you have any question. Coming back to Karen's question, it's true, these kind of experiments require lots of computing power. So there are dedicated facilities and also distributed computing resources. We at the Institute for Nuclear Sciences in Mexico City, in UNAM, we have one of those nodes. We are performing some of these Monte Carlo analysis. Actually, now we are in the process of doing Monte Carlo simulations. But for the future, of course, we will need also large storage, or just as in any other high energy physics experiment, or even, for instance, Alger, or all of these. Yes, there is the need of high computing power. There is the need of young and enthusiastic people that write the codes, that analyze the codes, that use the codes, etc. So everybody is welcome to try to see whether or not this is a path for your careers, for you youngsters. Thank you. I think there is a question there.
Yes, please wait a bit.
Yeah, regards to the last question the Professor Karen makes, I'm curious about this the distribution. For example, in the statistical mechanics, we assume that all of things satisfy the central limit theorem, no? But the real scenario, many of phenomena doesn't match with that. Suppose, for example, I can think about the lifetime on a particle, for example, that satisfies exponential distribution. My question is oriented to that phenomena that doesn't match with the central limit theorem.
Yeah, thank you for the question. I'll try to be brief. It's a very good point that you raised. Indeed, if you look only at the mean values and at the standard deviation, the central limit theorem will apply. But the question is, what happens near criticality? And near criticality, what we know drives the physics, is the fact that the correlation length increases. Let me just give you a quick example. Imagine you have some substance. The typical one is carbon dioxide. When you lower the temperature and increase the pressure at some point, at such a point in which, when you shine light on it, you see that this sort of, we call it iridescence. In other words, it shines light everywhere. What happens is that this is exactly the temperature and the pressure in which there are clusters of molecules of all of the possible sizes. So the correlation length is increasing. There is not a single value of a correlation length. It's not a molecule. It's not a single cluster of a given length. You have every sort of size in the clusters. And that's why when you shine light with white light, with all of the wavelengths possible, this shines everywhere. The light scattered everywhere because it scatters in all of the possible wavelengths. So this is what we're looking at. Near criticality, locations are like crazy. They diverge as maniac. There are all sorts of correlations. And that's why you need to capture that physics. And this is the physics that is captured by the infrared properties of any plasma. Long wavelengths modes are there present and in all of the possible long wavelength modes. And this is why I think this has future. So just to come back to your question, true what you're saying, but near criticality, this situation breaks out.
Thank you very much. And let's thanks again,
Thank you.
Alejandro. Yes, it was on time. Our next talk is by Miriam Mondragon. We are going to make a small change in the program because we are giving the medal at the end of your talk. Because some students are on their way up to here and they want to be present when you receive the award. So,
Okay. Well, when my talk appears, let me thank Karen for the invitation. I will give the thanks after you give me the medal properly. And I'm really happy to see you here in 3 dimensions, in person, alive and kicking, after so many years locked. So if I start moving the microphone away from my face, please, there in the back, wave at me or shout or do something so I come back to my senses, okay?
yes, thank you, Miriam. I will let you know when you have 5 minutes.
So there's something. I gave my USB to somebody, so we can project it directly from my USB.
Yes, is it possible to
There was no internet right now. So
project directly? Friends, yes, who are connected to open the talk directly from the Indico and to follow this. It's because we are going to project not using the screen sharing. Bueno, ya, hola. Sí, sí. Bueno, now that we have a little more people present, so we will give the medal to Miriam. She got the medal 2021. And congratulations. So,
Thank you very
I will-
much. Thank
Voy a tomar la medalla. Que se me acuerde. So please go ahead. I will let you know when there is 5 minutes.
Yeah, you tell me when. Yeah. Thank you very much. It is also a great honor for me to be awarded this recognition, this medal. Yeah, and I'm also very happy to see you all in person, as I was saying, to see so many young people, to see some young people that I knew from many years ago, yeah, and to have the opportunity to meet with all of you. I'm going to give an overview of work I've been working in recently in the last 20 so years, yeah. So it's going to be sketchy, but I want to give you the idea of how are we trying to look for physics beyond the standard model, what are our guides, and how do we try to find out a path to go beyond. So this is going to be mainly about symmetries and their massive consequences. Okay. So modern physics is built on the observation that there are symmetries in nature, and these symmetries can be exact or broken. Yeah. Symmetry for us physicists is a transformation that leaves the Lagrangian invariant. So that symmetries are present everywhere in nature, not only in physics. So quantum field theory, I better look at from here, combines, as we know, special relativity, quantum mechanics, is based on space-time symmetry like rotations, translations, Lorentz and Poincaré transformations, internal symmetries that describe the internal properties of each particle, which are related to gauge symmetries. Our symmetries can be global, like space-time momentum, angular momentum, local, like gauge symmetries. Then we have continuous, and continuous symmetries always imply, thanks to the Noether theorem, one of the most beautiful theorems in mathematical physics, conserve quantities. Yeah, we can also have discrete symmetries like charge and parity, which can be exact or broken. In the standard model, they're broken, and they label and classify particles. So we have an assortment, an array of symmetries, and we're used to work with them. When we write the standard model Lagrangian, everything is included there, including the broken symmetries, even if we don't fully realize it. So what part of the standard model we don't understand? Remember, the upper part of the t-shirt is the front part, you know, in a very condensed notation. The back part of the t-shirt, it must be XXX, extra large. It's all with all the labels and, you know, no contractions. There's a lot of things there that are condensed in this front part of our t-shirt. And there are a lot of things that we know that work, that we don't understand fully why from first principles, but they work, and they work very, very well. So why go beyond the standard model? You are here, so you probably know, and you've heard it many times. So we have the hierarchy problem, the stabilization of the Higgs mass, the neutrino masses, not only the neutrino masses, all masses. Yes, they're all very different. The origin of gauging interactions. Now, with the new observations, dark matter, we are going to assume that it's a particle. Yes, it cannot be one of the ones of the standard model. Matter over antimatter abundance. Why is there so much more matter? The cosmological constant, we're going to move backwards in time, inflation, and so on. So in the square square, on the pink square, not rounded. We have all the part that is related directly to particle physics, like Higgs sector non-natural, fermion masses, origin of electroweak symmetry breaking, that's getting back to cosmology, Dirac-Majorana neutrinos, strong CP problem, etc. And then backwards in time to the origin of the universe, not enough CP for baryogenesis, the cosmological constant, as I say, what particle is dark matter, and so on. So there are many reasons to go beyond the standard model, but there's no simple way to do it. So there are many, many, many different ways, because there are many, many different things that we want to explain that we don't understand. So normally, traditionally, we add symmetries. And that has been proven very, very successful for the last 150 years, or perhaps even more. Yes, not more, actually. This can be complementary, or this can be done independently with addition of particles, of interactions, of space-time dimensions, and generally we do all of them. And they're all intertwined, and they all have consequences. So here I will concentrate on masses, on fermion masses and their mixings, and perhaps because also massive dark matter, and I'll just talk about leptogenesis and so on. So basically the message is that everything is mixed. We cannot start nowadays to talk about physics beyond the standard model, ignoring cosmology, which we used to do when I was a student. Yes, well, cosmology was, with huge error bars, it was more uncertain. It's not the case anymore. We have really nice experiments nowadays, which have reduced the astrophysical and the cosmological sensitivities or uncertainties, not to the level that we can do in an experiment here at Earth, but to the level that they can discuss theories, and that is really nice. Important. Okay, masses are very, very rich. And what I mean very, very independent, masses can be neutrinos, and there are 5 to 15 orders of magnitude of difference between the heaviest and the lightest. Yes, between the top and the up, 5 to 6 orders of magnitude. And then if you add neutrinos, then this gets even more problematic or less natural, whichever way you want to see it. Yeah. So neutrino masses enhance the problem because they're tiny, but they're really important. The fact that they do have a mass, it's a very important fact in theoretical physics. And the Higgs boson is there and found and crucial for the mass generation. So what we're trying to do is go, and this is a lot more messy in real life. Yes, this is just what I'm trying to do. It's already messy enough. So you have the standard model, okay, and you can go from a bottom-up approach, looking at the phenomenology, or you can go from a fundamental high energy approach and go down. Yeah, in the middle, they should be beyond the standard model theory somewhere there. They might not be mine yet, but or the ones I like, but there's one there. And in the middle, like like an onion, like the layers of an onion, there might be more. We don't know. That's what's been happening in physics, with atomic physics and nuclear physics, and then particle physics and QCD and so on. So it's not unlikely that we don't have a big desert, but we have lots of layers like a cake. Yeah. Anyway, so you can have more interactions, more symmetry, more space by dimensions, or you can go from a very, very fundamental theory here, string theories, M theory, or a slightly less granulified theory, and you can go all the way up or down. And here in the middle, you have to try to find answers, if not to all, because it's really too ambitious to find all. Eventually, somebody will find it, a group of people, probably lots of people, but at least to some of the new phenomena we are observing. So how do we move up or down in energy? Well, thanks to the renormalization group equations. This theory has the same structure at different energy scales. And that is really beautiful if you come to think about it. Yeah. And that is also a property of nature. Yeah. And this is related to scale invariance and conformal invariance. And in particle physics, I'm not going to give a class, so I'm just going to remind you, we use the beta functions to tell us how the masses and the couplings renormalize or change at different energy scales. And these are related directly to the renormalization of the fields through the anomalous dimensions. Okay, So scale invariance means that the things look the same at different scales, obviously, and conformal invariance is more fundamental, I would say, because also preserves the angles when you make a scale transformation. Yeah. Scale invariance and also conformal invariance, especially scale invariance, appears in many physical systems. That actually appears a lot in kind of systems that Alejandro was talking. It's related to phase transitions. The interesting physics is at the critical points of the phase transitions. Of those, we have a lot in physics, and we usually treat them a bit cavalierly, yes, but there they are, and that's where all the physically interesting phenomena appear. So one example of adding a lot of symmetry, and very fundamental one, is having a supersymmetric theory where you relate the interactions to matter, yeah, supersymmetry, and you also require that there's only one fundamental interaction or gauge constant. So this led to SUSY GOTS, which have been studied for many years, and they still be studied, yeah? So at high energies, you have only one fundamental interaction. It relates bosons interactions and fermions the matter, and now you have an extended sector. And at all low energy, the one more studied was the minimal supersymmetric standard model, which is the simplest version we have, which of the lowest or the simplest version of a very constrained model has been discarded in the LHC, but not supersymmetries as many people might infer. Supersymmetry is not discarded. What is discarded is some parameter space of a very constrained model. Yeah. What we can say is that its supersymmetry exists is not at the LHC levels that we're trying right now, unless we have a particular type of model that is in what they used to call the experimental is the horror scenario where you cannot actually detect it. So, but it's there. But the fact is that it's broken. Yeah, even if you have minimal or non-minimal models, it has to be broken. Otherwise, the supersymmetric particles would be at the same mass scales and the others. So you add symmetry, and you can keep on adding symmetry and interactions and particles, and you get to something very nice and interesting, which is like mole poblano, heavy, nice, full of ingredients. Yeah, but somehow, you cannot distinguish. You take a mouthful and you say, like, what does it have? Well, it has chile, one more chile, perhaps more chiles, and it has sesame seeds, and it has it's difficult. Yeah. Well, it's a bit like that. And here, more symmetry doesn't always help you to lead. I mean, it helps you to construct a nice theory and so on, but you cannot disentangle everything precisely because you have very large symmetry groups. It's difficult to have one path that leads you down to the standard model. There are many paths. In here, you have a very large symmetry group. You have to break it. There are many different ways to break it. You have a lot of different particles and interactions at high energies, like a supersymmetric, and then down at the unification scale. And then you have to compactify also the extra dimensions, 6 extra dimensions. There are 10 to 500 or something ways of doing it. So the problem starts getting very complicated, even if you started with a very geometrical, interesting theory. Yes, so it's super interesting, but needs extra guidance, for instance. Might be that it's not the ultimate theory, but something, I think, it will stay there. So what we've been doing, and I'm going to talk really fast about it to then talk about lower energy models, is, yes, take symmetry as guidance, but go on and take other principles, which are renormalization group invariance, which are related precisely with super surfaces where you have phase transitions here. And this has been proven many years ago by the group of Zimmermann at Munich, that is equivalent to solve a set of reduction equations. So you require that you are in a renormalization group invariant surface. The idea is very simple. You don't know what the symmetries are or the fundamental physics, but if two quantities are related in a renormalization group invariant surface, they have to be the same. So they have to be renormalization group invariant. If that's the case, the beta functions have to be related. Yes. So the idea is functionally very simple, and I think it's very deep. So you can then write reduction equations where these assumptions have been taken. There are quantities related to others. We don't know why, but they are. They have to be renormalization group invariants because it's not just a coincidence. It's a fundamental thing that they are related. So at some level, the new physics, these quantities are related. And then they lead to these reduction equations that relates the different beta functions of the, let's say, primary coupling, the ones that they are all dependent on. So this may indicate underlying symmetry, and there are solutions to these reduction equations without apparent symmetry, but probably it means that we don't have the full physics behind it. Supersymmetric solutions appear often as solutions to these renormalization equations, and this has been done many years ago in the standard model, and they could predict wrongly, but because they didn't know what the masses were then, it was still very impressive. So I'm making a small announcement for my student. He's going to do the same program of reduction equations without supersymmetry in the 2 Higgs doublet model. It has been done many years ago by Denner, but now he has found a systematic way of doing it. And because multi-Higgs models are very important nowadays, you should go to his talk. Okay, so that was the ad. And now, finiteness is related to scale invariance. Finiteness for us physicists in this lecture and for me means the beta functions are 0 to all orders in perturbation theory. So we get to a theory which is very fundamental, and it doesn't go on anymore if you want. There are no infinite renormalizations. It means that the theory is scale or conformal invariant. Yeah. So we have a very, very, very symmetric theory. The theory we live nowadays at these energies is not extremely symmetric. It's symmetric, but not that symmetric. We don't have neither scale, well, not conformal invariance. So couplings, we get to a theory, which is a basic theory, where the couplings do not depend to the scale, to the energy scale, and is based precisely on renormalization group invariance and these reduction equations. So this reduces greatly the number of free parameters and implies that there are new symmetries. So we've done this for many years with a partial reduction only on the third family, because it seems to be the natural one, since we didn't know them, but we know now that the Yukawa coupling of the top is of order 1 at low energies. So if you require this absence of infinite renormalizations, or you scale invariance, actually conformal invariance, you find that the beta functions and the normalized dimensions are 0. At one loop level, it relates the matter content to the irreducible representations, and the gauge and the Yukawa couplings, which we don't know where they were unrelated before. You can go and do it at all levels in perturbation theory, reparameterization invariant, gauge invariant, and it's super conformal invariant. You can only do it in supersymmetric theories. And it turns out that it's very, very predictive. So many years ago, they started to study SU5 models, then the connection with string theories, and these models with 3 generations. We only studied one with only the 3rd generation. The model had in principle 3 generations, but you only assumed that the 3rd generation was the one that was proportionally to the strong coupling constant. Then we found that there are more interesting models with SU3 to the cube, which is, SUN to the K, but the most interesting is SU3 to the cube. And these models imply that they're finite. So beta function is 0 to all levels in perturbation theory up to 1 on 2 levels. Then it implies that it has 3 generations. That is really nice, yes? And if it has 3 generations, this kind of models, then they're finite. Then there are more recent developments, relations with non-commutative theories and finiteness. The proof of conformal invariance is only in the adimensionless, this dimensionless, that's a missing there. In the dimensionless part, the super breaking terms, it's a scale invariance, but not conformal invariance. Relation between finiteness and quantum field theory in curved space that leads to inflation. That's really interesting. And there are some recent reviews. So basically what we do is we have a really reduced theory where we have all the couplings related to the alpha strong, because it's a unified theory, it's only one coupling, so alpha strong is all of them, yeah? And this is the model that survives. We have the gauge couplings related to the Yukawa couplings, so the Yukawa couplings related to the gauge couplings, and in the soft breaking terms, which in principle can have up to 120 free parameters, we have 2 free parameters. This is not the constrained MSSM. We force it to be the MSSM, but it has different boundary conditions than the constrained MSSM. And it turns out that even though it is, has only 2 free parameters, it is only the 3rd generation. It is very predictive in that 3rd generation. So now back to the front of our t-shirt. These are the Yukawa couplings, which in the standard model are free parameters. For us, there are not more free parameters. We determine the value of the Yukawa coupling and the unification scale. And with that, we can make a prediction because we know the value. So here it is. These is our thought. We call them finite unified theories instead of God's thoughts. So it's an SU5 thought. There are more thoughts. Yes. You have the boundary conditions, which are, well, here we have these things, but the Yukawa couplings related to the gauge couplings. You run down the realization group equations. You can do also a finiteness analysis for the soft breaking terms. That's what it reduces to only 2. They are not conformal invariants because you have a mass scale, but they are scale invariant, which is still pretty good. And then you run down mass of the plot. The mass of this plot is a very clean prediction. That's the mass of the plot is a concentratory voltage prediction that is related to the soft breaking terms and one of the free parameters, a large tangent beta, and to be compatible with all the experimental constraints, it implies a very, very heavy SUSY spectrum. So for us, since many years, not finding supersymmetry was, from our point of view of these finite theories, natural. The renormalization group flow doesn't take you to a low energy SUSY, takes you to a high energy SUSY. Why high? High is a TEPS, unreachable, as we did in our latest analysis, unreachable even to the FCC directly, but reachable perhaps by exotic decays of some of the supersymmetric patterns. So this is more or less how the program is now. So the bottom masses, we also could predict the the Higgs mass within our this depends on our 2 free parameters. So it's a less clean prediction, let's say, than the top, which really is like, you get the value and that's it, yeah, with a certain uncertainty for threshold corrections. And now, because they found them, we found them in a larger range than what the experimental value was. Now we restrict ourselves to only the experimental range, and that gives us some constraint on the 2 free parameters that we have. So 3 free parameters sounds like very few. There are very few, but remember, I can't remember which ones. Fermi or Wigner says that with 2 parameters, he can fit an LH1. Yes, it's still, when you do the analysis, it's still quite large, but okay, we have a blob in parameter space where our theories live, and it tells us that supersymmetry has to be high. Heavy SUSY spectrum in each of these models. We have analyzed the all loop SU5 put, so beta 0 to all orders, a reduced minimal SU5, this is discarded, a 2-loop SU3 pot, this is okay, this is still alive, a reduced minimal supersymmetric standard model, which would have been seen by now, so this is in the version we have, it's also discarded. And nowadays we're looking at dark matter candidates and 3 generations and neutrino masses. So we're going beyond the 3rd family. And the new analysis is being done with my young and not so younger colleagues, which I forgot to put there, and I'm sorry about that. This is work I've been doing with George Supanos and Sven Heinemeier for many years, and now is Kalinowski, Klotarski, which have joined our team, and Patelis. So we have made a full analysis with the LHC. So we have our God boundary conditions. We have the DR bar parameters at the SUSY scale. We go to fine Higgs, and then we have a precise prediction for the Higgs masses, all of them, and low energy observables. On the other hand, we have implemented in Sarah and Espino at the pole mass. We go back there and we improve the prediction. And from this, we have go to math graph, and then we go to the collider phenomenology. So we can really have some values for the next searches for supersymmetry in the high luminosity LHC and FSCC, and perhaps even ILC. So it's very challenging for most of it's a few TeV, but a few TeV for us physicists is the same order of magnitude. For experimentalists, a few TeV, maybe 30 years of developments, yes. But anyway, it's really interesting in the sense that, well, for us, it's not odd or strange that they don't find it. We don't expect it to be low energy. So these are the recent developments. I'm just going to say that, well, they're working, many of my students are working in this, you can read them. We are making fine finite SU3 to the cube. As I said, it has 3 generations because it's finite, or because it has 3 generations, it's finite, whichever way you want to see it. And we are doing it with all down like a more inclusive approach where we include all the 3 generations and the neutrino mass. It's interesting because lately it starts to be related to no-scale gravity theories. We don't know how, but many people have started studying these kind of models to see if they can make a bridge between a more fundamental theory, where it's our theories that, once you decouple them from gravity, you have a finite or a superconformal theory. And now, I hope I leave you like a bit picados, as we say in Spanish. Yeah, a bit curious about it. Now, what we do at lower energies? Yes, all of this, we start with a very, set of boundary conditions. We run down. Is it good? Yes. Is it not? Goes to the garbage. Yes. And in between, or really, a few of them have gone to the garbage. It's kind of sad because a lot of work, but okay, they go to the garbage. And at low energies, yeah, can we learn more when we are at low energies? Of course we can. The data is there. We have a lot of data, and perhaps it's already telling us something, but it's so entangled that we cannot see it. And I'm not saying that we're being silly or something. It is really difficult. Yeah. So that was the first part. Now the lower part is look at the data, and just going to be talking about masses and mixings, and see if already the data that you have tells you something. Yeah. So in here we are going to have we have a minimal approach with SU5 and with the minimal assumptions that would work with the reduction equations. Now we are going to follow the same idea, find the smallest symmetry suggested by data. The symmetry groups might be large, right? Might be like a superstring kind of thing, but we have to start from something and saying all these cannot be the end of a big group. Eventually this big group will break down to the standard model group, and in between we'll have something. So we want to discard all these somethings that are not good, yeah? And or find the guidance of which one is the good one. So we explore the smallest possible abelian symmetries, non-abelian symmetries, and how generally it can be applied. And we live with it. We follow to the end. Yeah, we try not to break it or break it minimally, and not to add too many things at low energies, because we don't want to add more things that we don't observe at low energies. At high energies, we always have the excuse that, oh, well, because they're high energies, we don't see it, they're decoupled and so on. Okay. So these are the quarks ratios and leptons, yes? So the top, second generation, third generation, that's what I was saying. The downs, the bottom, strange, down, and tau, mu, and electron, yes? So if we are normalizing with the heaviest mass. The neutrino masses are unknown. We only have the difference of the square of the masses. So we don't know it's an inverted or a normal hierarchy. So it adds more uncertainty to our study. The Higgs sector is under study. We are finding all the couplings and so on. And the quark mixing angles are, these are the other way around. I know they're okay. There's the quark mixing angles, yeah, which have a hierarchical CKM, or yeah, there's hierarchical basically diagonal. And then we have the neutrino mixing angles, which are all over the place. Yes. So small mixing in quarks. So the electroweak or the interaction states and the massive states are close, let's say, close together. But in the neutrinos, they're not at all like that. Yeah. So can we actually apply an underlying symmetry to both of them? That's what we're going to try. So this is the CKM, as I say, hierarchical. This is the PMMS, yes, non-hierarchical. People thought that this was 0 for a long time, but it's not 0. It's not even very small. It's 8. Well, small, but not terribly small. Yeah. So this is the logarithmic plot of the quark masses. So you're normalizing with the heaviest particle, say the top or the bottom in each section and the tau. And then you realize really that in a logarithmic plot, it's always useful to tell you about orders of magnitude, that the first 2 generations are close together and the third one is not. So this, from the point of view of the group theory, suggests a 2 + 1 structure. So for many years, people were trying to put it in triplets, but this doesn't suggest at low energies a triplet. It is suggestive if you have to work with something like SU5, you put them all in a triplet, but at low energies, it doesn't. So at low energies, 2 + 1 for the quarks works very well. For the neutrinos, you can do much more things because it depends how you generate the neutrino masses with a seesaw, with an inverted seesaw, radiatively, and so on. So we've been working for many years with S3. You know, these are the reducible representations, doublet, symmetric, and anti-symmetric singlet. And we apply it universally. So we say that this is for some reason unknown to us. The data suggests it, at least in the quark sector, and we're going to apply it universally to the quark, the leptons, and the Higgses. The Higgses, they didn't even know what the mass of the Higgs was when we started doing this. And we need to extend the Higgs sector. If we do it only with one Higgs, like in the standard model, then you have to break the symmetry. So if we don't want to break it, at least not terribly, we treat all of them simultaneously with 3 Higgs doublets, 1 doublet for each family. So we add flavor to the Higgses. So it turns out that with these assumptions, with these just very basic assumptions, the CKM matrix has the nearest neighbor interactions structure, which we know it's very good. So, you know, tick mark, yeah. The neutrinos, we also apply it. We have to make more assumptions. We make a type 1 seesaw. We make an extra symmetry to get rid of, because we have a lot more free parameters. And we find, before the diabase and the previous experiments measured it, that theta 1,3 is always different from 0. There's no way we can get theta 1,3 equal to 0 with this kind of symmetry. So that's now also a tick mark. It depends on the details of the model and what assumptions you make on the extra right-handed neutrinos, which we also have there. What is the value? But it turns out that we can always have it in the range, an experimental range. Some favor changing nuclear currents, which are, you know, the main problem of multi-Higgs doublet models, are suppressed by the symmetry. They keep on being suppressed by the symmetry in the latest analysis, so that's nice. We have lots of Higgses, and there's where the predictions are going to come. The other things are going to be the CKM, the PMNS. Well, theta 1,3 and one of the mixing angles were predicted nicely with assumptions. The CKM fits really nicely, giving us a delta CP, a prediction for the CP phase, which is depends how do you do analysis, very well or so, but close to the experimental value. And these are the nearest neighbor interactions I was talking about. And Adriana's talk yesterday concentrated on the Higgs sector, which is exactly where all the predictions are going to come. So we have, I'm just going to recall very briefly what she said. We have 2 scenarios. We have 3 neutral scalars. One, which is decoupled completely from the gauge boson, so that cannot be the standard model Higgs one. One, when the neutral is the lightest one, so we identified with the standard model, okay? And one, when there is a lighter neutral scalar than the Higgs one. That is very interesting because it means that you could actually explain this new signal that keeps on popping here and there about a 96 or 100 GeV scalar. It might disappear, but it could be a possibility. So, and we can parameterize it in a phenomenological way in the decoupling limit, when one of them, or alignment limit with one of them is the standard model Higgs, it reduces exactly to the standard model trilinear coupling. And we can parameterize small deviations with this kappa parameter or the kappa framework, which has been already studied, you know, extensively in the literature, and it's constrained. So in the literature, it appears like kappa can be a number, yeah? This number is related for us to an expression of our parameters in the model. So we can say within these bounds from kappa, our parameters can be this big. These are all intertwined. These are all related. So if we fix one of these masses, or we fix one of the mixing angle between the doublet and the triplet, then we can estimate kappa, yeah? Which means that we can really, once we have better analysis in this kappa framework, we can discard or include parts of our parameter space. So the future analysis is a mass spectrum. We have to add to that. This is all one loop corrections. We have them very clearly just to show there because for the sake of the correction way out. So, that we have big parameters in in a region with their flat. That means that all the masses are more or less the same order of magnitude. There is no problem with the oblique parameters, so it's viable. The Higgs masses, all of them, Adriana showed yesterday, they're in a little blob, which is bounded by below and above. And that's very good because, you know, we can say they should be in this range. If they don't find them, they're not there. Yeah. But we have to do the one loop analysis. And now they have a residual symmetry, which is really interesting because it means that what our scalar that is not coupled to the gauge bosons could be a dark matter candidate, because it's protected by symmetry, which we didn't impose by hand, but it's from the system. But the symmetry, because it's a symmetry of Lagrangian, is present everywhere. So this symmetry is going to show in the quark and the lepton sectors, and we don't have nice CKM and PMMS. So this was like discouraging until we realized, well, we can break the S3, and then we have to read a little bit, but we have to redo all the analysis for the Higgs sector. It can be done. Yes, and it's not going to be vastly different because you have to break it only a little bit. So it can be done. Yeah, we haven't done it, but it can. There's another nicer way, which is adding or requiring that the S3 is a modular symmetry. We don't have to break the S3. There's a lot of work in flavor physics in modular symmetries, which are a subset on conformal symmetries. So that's, for me, that's very nice. If you require S3 to be a modular symmetry, then you have an extra parameter because the modular symmetry gives you an extra parameter. But it turns out that you can fill up those zeros in the CKM. And if you use the symmetries of the S3 as a modular group, yeah, then you can still reduce greatly the number of free parameters. So this was unexpected, but it was very, very nice. So that can be solved that way. We don't know what, it fits well the CKN, and it has exactly the same nice Higgs potential that Adriana showed yesterday. Or you can assume that there's some non-renormalizable or some terms or some other high energy sector that fills up that zero, that we can do too. You can add 4 Higgs doublets, some work that we did with Felix, which is seated right there. And it turns out that it's going to be exactly as nice predictions as we had before, but we have to do it now with the Higgs potential, or you could add Higgs singles. So the main point is that it's possible to return to the good previous results we found and to keep some of the nice features of the scalar potential. So if you go to 4 Higgses, you have saturated all the irreducible representations. You have, for instance, you can put an inert Higgs doublet. So Bev equals 0, not coupled to the gauge bosons in the antisymmetric representation. And then you have nice one or many candidates to dark matter. So it's a very little symmetry that goes a long way. So I added particles, 3 Higgs doublet or 4 Higgs doublets. I imposed a smallest non-abelian symmetry, and I'm squeezing it, yeah? And every time I squeeze it a bit more, I get another bit of juice from my lemon. Yeah, it's like, wow, it's really amazing. So in my point of view, probably it's not exactly as we're implementing the symmetry, but there is definitely a residual S3 symmetry in our Lagrangian, in our standard model Lagrangian. You know, the facts keep popping up, yeah? The neutrino sector is a lot more complicated, but at least in the quark sector, there's something like that, probably slightly broken with 3 or 4 Higgs. This is the analysis that Catalina, for the 4 Higgs doublet model. In that case, this little red region here is our candidate to dark matter, so coming from the inert Higgs. All of these points here have passed all the unitarity constraints, and all the Higgs bounds. Higgs bounds is a program that, you know, checks everything that we know about the Higgs right now, and checks every single point in the minimal of the potential to see that it really, you know, fulfills all these points. So this part of the spectrum satisfies all the Higgs bounds. The S3, the 3 Higgs part is exactly as we had before. So we know that at least in the standard model limit, our model passes most or all of the phenomenological constraints. And it gives, in this particular version, dark matter candidate, and it complies with the, you know, relic density. This is under the relic density, and with the direct and indirect searches. Here, is the relic density is not saturated, which prompted us to look for more candidates to dark matter, which is what we do now. And the model, you can do it. It's really interesting. You can add a right-handed neutrino, you can add a second scalar, and so on. But this is ongoing work. So in between, when you're guiding what are you doing, you use a lot of experimental and data, because as I said, even with 2 parameters, it's a lot, yeah? If you want to pinpoint exactly what's your region of parameters in space. So G-2, the breaking of mu tau symmetry, and upstairs models that work like SU5 cross Q6 non-FOT. All of those have been giving us guidance. And looking at this 2+1 structure, we have been looking at other groups besides S3, which are slightly larger, like S4, Q4, another add. Catalina is going to talk tomorrow about Q4, which is an ambitious model we did, where also has this 2+1 structure. It's a bigger group, so it has more irreducible representations. We have more singlets, but you can fit the CKM, the PMNS, leptogenesis, G-2, the Gato-Sartori-Tonin relations with some assumptions. So it's an interesting model because what we expect is eventually we're going to be building up the ultimate theory, including in our model that explains more and more observables that have been unexplained. Perhaps not all of them at the same energy level, but at least as many as we can. We have been looking at SA because S3 turned out to be so modular S3 successful. We have been looking at SUSI SU5 non-minimal with modular S3, yeah, and to S3 with 3 and 4 Higgs doublet models plus singlets for dark matter, sorry. So here is a bit cleaner version of the previous slide at the beginning. So we're looking at models could be S3, S4, Q4, Q6, where we can have replicate this nice 2+1 structure in the quark sector with 3 or 4 Higgses, yeah. So discrete symmetries, plus Higgses, plus more Higgses, and then trying to go up and down with a normalization group to unified groups. It could be that there's a lot more here, yes, what here we don't know, but at least trying to find which, first of all, at low energies, which could be the residual symmetries that actually work. We know that some of them do not work, or work at the expense of adding a lot of parameters or a lot of breaking terms, which adds a lot of parameters, which we don't know where they come from. If you have more parameters here, but you know where they come from, a large symmetry group, okay, there are a lot, you have to get rid of them, but you at least know where they come from. Yeah, and then we are doing some of them with supersymmetry, some of them without supersymmetry, and trying to see where could they lead us in this messy path to our quest beyond the standard model. So the outline and conclusions is there are many different ways to go beyond the standard model. Finiteness, these reduction equations, and finiteness proves to be a very good guiding principle. Our theory here, low energy, is not finite or super conformal, but it could be that it shows some residual superconformal symmetry in the quark sector. This would be more evident in the top, which has relatively a smaller hadron corrections, and it will be less evident in the lighter quarks, where the radiative corrections are bigger and messier. It reduces greatly the number of free parameters. Something that was, a free parameter in standard model is for us a number. All of them meet extended Higgs sectors and discrete flavor symmetries, also the finite theories. So that's also very interesting, and that's what prompted us to look at both these mixed approaches, yes? At low energies, we've been concentrating on models, symmetry groups, non-abelian, which have these doublet and singlets, so we can fit well the CKM, and it works properly. We always need extended Higgs sectors. We can be minimal or more horribly extended. I must be honest, not all of them are so pretty. Yeah, I showed them the most economical one, but if you want to be more ambitious, you have to add a bit more, and then they get a bit uglier, okay? You can provide baryogenesis through leptogenesis. You can provide dark matter candidates, one or many, and maybe it is possible to connect both approaches, and that's what we're looking now. We don't know, yeah. We have also left-right symmetries. So if we go in journeys beyond the standard model, there is a lot to pack. You have to find out first what is really necessary, yes, in your suitcase, what size of the suitcase you want and what is really necessary. And then you have to find a way to put order in it. And the reduction of couplings and finiteness, might and supersymmetry, GOTS and so on, give you some guidance at high energies. And at low energies, discrete symmetry, extended Higgs sectors, all of that help us to, put some order and shed some light of where the beyond the standard model, good successful models, because I don't think we'll find one single model soon. We're going to have a class of models and then we're going to see through them. And they all have consequences for the particle masses, not only for the actual, in finiteness case, it actually gives you the value of the masses. In the other ones, it gives you the mixings and the hierarchy among the masses. So that's all. Thank you very much.
Thank you very much, Miriam. You finished exactly on time. So thank you very much. Are there questions?
Pablo is hesitantly raising his hand.
I like it very much. Of course, you didn't have time to discuss everything. And for instance, concerning my question, you mentioned Catalina will give us more details, but in general, for this baryogenesis via leptogenesis, I guess that you don't need always to go to do it at very large scales because you have to extend the scalar sector and all that. So can you comment on, I guess you have different options, right?
Yes, excellent. That's a very nice question. It is, of course, directly related to the neutrino sector. Yes. And it turns out that we have sort of low energy leptogenesis. Yeah. And that is really interesting because first people favored high energy leptogenesis, but we had to live with this. And now it says that, okay, perhaps low energy leptogenesis is nicer. I don't know. We have to work out all the problems because the flavor effects, if you're going to lower is TD, no, it's not 100 GV or net, sorry, it's a T text, yeah, but the flavor effects can be big. So, but we can find solutions with low energy leptogenesis directly related to our neutrino sector. And the fact is that we first fit the PMNS and some of the parameters for leptogenesis get restricted that way. So not like you have all three parameters and then you can go and restrict them more, requiring for the right amount of baryogenesis or leptogenesis. Yeah. So yes, good. Thank you.
Thanks a lot.
Thank you very much, Pablo. Are there more questions? Yes. Could you please press the...
Hello, thank you very much for the nice talk. I was wondering about proton decay. Is it the scenario like included?
Nice. Yes. Very nice question.
What about experimental
Yeah.
limits?
Proton decay is always a problem with with all grand unified models. It's a big problem with minimal SU5. We don't have minimal SU5. We have extended Higgs sector, but we also have to test it. We tested many years ago, and now one of my students for his MSc thesis did a full analysis of the proton decay possibilities with all the Higgses and going even to the MSSM or not going to the MSSM, and we found that yes, it was experimental outcomes. So that was a very important issue. Now we haven't changed greatly, but it is something that we have. So yes, very good, very nice question. There is no problems with proton decay so far with a non-minimal SU5 port. Yeah, you have to make this horrible doublet triplet splitting anyway, which is really fine tuning. So we have a nice predictive theory, and then we fine tune there. So far, nobody has found a nicer way. Yeah, but yes, at least it's not worse than others in that sense.
I have a question. Thank
Yeah.
you for the talk. It's very nice. What about the results from G-2, for example? How can you accommodate, in the future, in the next few years, there will be a very exact result of
Yeah.
G-2?
So in the FOT, the G-2 is in the FOT is the same as the standard model. So we have no solution, but we don't have it better or worse. It's like the standard model. Yeah. In the
But that will imply some new physics at really high scale, right?
yeah, we have new Higgs, but we have only one family so far. Yeah,
Mhm.
so we really had to have much more complete analysis or an analysis of how to include, if we only want to reduce the third family, say make that finite and the other ones acquire masses differently, we still have to include the three to make a proper analysis of G minus. Catalina is going to talk to G minus 2 very briefly tomorrow. Well, she's going to talk more about dark matter. She's giving me nasty looks right now. No, but in the low energy models, you can require or see if you can get G minus 2. And what that does is restrict your parameter space. Yeah? So we find a parameter space where you can get the solutions that are compatible with experimental values. So basically that's what we do. Yeah. Not every model can do it. Yeah. But it doesn't get worse. It gets either like the standard model, or you can find it in more complicated models, so not the very simple models, a solution within the parameter space. And usually they're intertwined because we treat all the sectors like how would I say, like these flattening machines. Yes, all of them horizontally. Yeah, you can get restrictions from neutrinos to dark matter to G minus 2 to leptogenesis. And that's nice, but it makes analysis a bit more complicated. Yep.
So, there was another question.
Yep. In the context of the EAC, it is mainly devoted to study hadronic interactions, but I was wondering if it will be useful to study SUSY, or do you have any prediction that can be tested there?
I couldn't understand you.
In the context of EAC, electron ion collider,
Yeah.
It is mainly devoted to study hadronic interaction, but I was wondering if you have from the SUSY part predictions to be tested there.
Yeah. Okay. We had, yes, the predictions. The problem with the predictions is they're always very high, so they're not available. But we have in a new paper from 2022, all these. I showed a small flow diagram, you know. So we crunched our data through the map graph, yeah, and we have some predictions or some branching ratios for the different models. So some of them are still inaccessible for even the FCC. So basically, supersymmetry is very high, yeah, and the couplings are small. But for the SU3 to the cube model, for some particles, these signals could be accessible. So these spot models in the version we have now, which is only third generation with a lot, with very simplistic models, we haven't included all the others. They already imply supersymmetry that is inaccessible for the next 30 years. So, and perhaps directly and indirectly, perhaps for the next 10, 15, depends, yeah? Because what you were going to see is to find some kind of supersymmetric decays, that are not typical for the, say, constrained MSSM and the usual boundary conditions they put here. And that's what you will start looking. You wouldn't say this is spot immediately, but you will start like saying, okay, this is compatible, this is compatible with this and so on.
Thanks.
Okay, so let's thanks again, Miriam.
Thank you all for your patience.
This talk was very, very complete. So thank you very much. And now have the next talk by Professor Christoph Royon. So please go on. But before giving to him the medal, there is a special request by Javier Murillo, who is connected, and he's going to talk a few words for Professor Royon before the medal award. So please, if you want, you can sit during the talk by Javier. We just wait a bit.
Hello,
So,
can you hear me?
to hide the sound.
Can you hear me, Karen? Hello?
Yeah, we can hear you.
Okay, thank you. Okay, so I So I congratulate everyone there, all the awardees, Dr. Alejandro Ayala and Dr. Miriam Mondragon. So I will present and say a few words on the name of Christophe Rollon. He is a foundation distinguished professor at the University of Kansas. He has had achievements in many distinct fronts. I can summarize in terms of high energy physics, in the understanding of quantum chromodynamics and explorations of physics beyond the standard model, mostly studying diffractive phenomena and physics of hadronization and jets. He has led various groups, mostly in the D0 experiment in Fermilab, where he had interaction with Mexican groups such as the group of Heriberto Castilla, and in Atlas and CMS, he has led groups of forward physics and where they study elastic events and diffractive phenomena. All this work has led him for the discovery of the Oderon state, which is something that he will talk about today, and was spread in different journals and outreach publications by CERN Courier and Symmetry Magazine. Also, he has done some other things like contributing to a silicon laboratory, having implications in medical physics and also solar radiation studies by NASA. So I will pass to the following slide. So he has, as you can see, contributed to different large collaborations such as CMS, Atlas, Torrem, Delphi, D0, and H1 at DESI. He has especially participated recently in Mexican events. I can say that he recently started supervising two students from Simbe staff. And there is one special student from Sonora, so Cristian Valdenegro, who many of you might know, who graduated with him in Kansas, and then is doing a postdoctoral position in Paris, in France. Here we can see Christian and Christophe in a workshop in Guanajuato, Mexico. And here Christophe giving a talk in that same event. Here we can see part of the team that led him to the discovery of the Oderon. You can check these publications in Symmetry and CERN Courier. And here I put the paper. He will describe this more of this in his talk. I just want to remark that as experimentalists, we know how hard, difficult is to get a single publication, a single contribution. And this is why here we have sometimes trouble with the SNI applications in Mexico. But I want to remark here that he actually coordinated the collaboration of the two distinct experiments because for this measurement, they needed the proton-antiproton data from D0 and proton-proton data from CERN by Totem. Okay, I won't say much more details on the other contributions that he had on the QCD understanding of jets and hadronization. But I would just close saying that he started supporting the physics of photon-photon interactions, which we had a lot of talks and contributions on Monday. But right now, after 10 years, this is a central topic of research in particle physics, which is quite remarkable. Additionally, I can say here there is a picture with Cristian Valdenegro. He also has supervised other thesis work from students in Latin America, like in Brazil. Here I put some other work that he has done, like building this device that has implications with the solar radiation studies in a project in NASA. And there is another project with hospitals and medical research. So there are a lot of things that Christoph is involved in. Additionally, I mentioned some of his personal life. So here in Mexico, what he enjoys the most is the food, especially seafood and especially fish. But he also likes very much the Aztec soup, nopales, and this special dish with nopales and tomatoes, cazuela, the tortillas from Sonora. And one of his favorite drinks is the margarita. So maybe you can have some of those later to celebrate. And also he likes the literature and reading novels, especially from Mario Vargas Llosa, who is a famous writer from Peru and with Spanish citizenship. He told me he read all these books, but there are more on the list that I couldn't include here, like this La Ciudad y los Perros or La Guerra del Fin del Mundo, between others. Also, there are other writers he likes, like Borges or Neruda, and he wants to read more about Octavio Paz and Carlos Fuentes. And finally, I close by saying he buys art from different artists, but he has a special interest on Diego Rivera art. He has this picture at his house, and he is a stamp collector. Especially, he has interest on these stamps that were produced in this Chile Peru war from 1881 to 1947. So I congratulate him. And, then Karen, you can go on.
So thank you very much, Javier. So congratulations, Professor Royon. So medal is the medal of this year, 2022. Congratulations and thank you very much. Yes, okay. And slides.
Good. So thank you very much. I mean, it's a great honor for me to get, the medal of the Mexican Society of Physics from the Division of Particle and Fields. So I think I would like to thank, of course, many people for this medal. Let me check. There you go. Yeah. So of course, it's always the work of many people and not the work of a single person. So I should say that many people should be thanked for this medal and not only me. So, in fact, Javier already presented, they did this kind of a presentation of what I did and so on already. So I would like to thank him especially and all the people who supported me strongly for this medal. I would not make a list because there were many, many people. So please, I thank you, everybody, for this. And of course, as usual, so there are a special thanks to my students. So there are 3 of them were linked to Mexico, which are displayed here. First of all, this is Christian Valdenegro, who finished his PhD. It was in August last year, and he's now a postdoc in École Polytechnique in Paris. And he did a very bright PhD. I must say we have 8 publications together for his PhD, so it's really exceptional. And then I put 2 present students who are now also in Kansas, basically. So Luis, who is from Honduras, but he studied in Sinvestav with Pablo, and also Sarai, who also is she's from Zacatecas, and she worked also in Sinvestav, also with Pablo, for a master thesis. And I should mention also Moises, who is from Venezuela, and is doing a PhD in Sonora, so between Sonora and Kansas. So basically, what is the idea? So again, I thank you very much for this. And the idea is that this model will hopefully allow to reinforce the collaboration in Mexico. So there were the CMS and D0 collaboration in the past, where there were a very big group coming from Mexico, and I collaborated with many of these people. And Javier, for instance, is a member of CMS. We have also some application, I will mention it at the end of the talk, in medicine. I mean, it's not directly physics, but we apply our knowledge on detectors of medicine. And I should mention Javier again, and also Arturo, with whom we are setting, I mean, some collaboration, and definitely there will be some nice developments. And also on phenomenology, for instance, with Martin. And this list is, of course, not exhaustive. There are much more people with whom I collaborate, and more collaboration are very much welcome. I think, I mean, with the US, it's a bit natural because we are neighbors, that's clear. And for me, as a French citizen, we have also the same kind of culture, which is Latin culture, which is closer to the American culture anyway. So from this both point of view, I think it's natural to collaborate. So thank you very much again. So now let's come to physics. So what I will discuss today is the physics that we can do with intact protons at the LHC from the Oderon discovery. So basically, this is more soft kind of QCD physics, to also to beyond standard model, again, using this intact proton. And we will see why it's interesting to measure intact proton when we want to study beyond standard model physics. So I will start to introduce elastic interaction and what is the Oderon, because maybe for some of the students, it's the first time that you hear about this word, Oderon, so it may seem a bit barbaric. So I will introduce what it means. I will discuss the D0 PP bar and the totem PP data. I will define D0 and totem collaboration, how we discovered the Oderon, and then I will mention the study of the quartic anomalous coupling and the search especially for action-like particle, which is related to the standard model. And I will mention at the end the ultrafast silicon detectors toward basically the application. So let's start with something very simple that all students have already seen. I mean, I guess all students here have already played pool. So when you play pool, you send a ball against another. And what happened is that the balls are definitely scattered. They are not destroyed in the final state after the collision. So this is exactly what we do when we study elastic interaction. So we have two protons, for instance, they collide, and we have two protons that are intact in the final state and nothing else. Or we have collisions between proton and antiproton, and again, the proton and the antiproton are intact, and there is nothing else which is present. So this corresponds to the elastic interaction, and as I said, it's exactly the same kind of process as you see in the pool game, because the particles or the balls, they can lose or gain some momentum as rarely in the pool game. So now if we think in terms of physics, how can we interpret this kind of elastic event? So the way we see it, I mean, as I said, there are two protons colliding and you have two protons intact in the final state. So you need a colorless object, which is represented by this double bar, which has to be exchanged in order so that the protons are not destroyed in the final state. So how does this event look like? You have these two protons which are scattered at very small angles, at very large rapidity. For instance, this red proton and this blue proton, which is here. And there is nothing else inside the detector. So the idea, if you want to measure this kind of events, is to measure this intact proton in the final state. So how can we explain what we see? When we have two protons that collide, and again, we want the proton to be intact in the final state at the LHC, there is a gluon which is exchanged between the two protons. In the case where we have a single gluon, it can emit many gluons, and in most cases, in that case, the protons will not be intact in the final state, but they will be destroyed. So clearly, this diagram is not good to explain elastic interaction. So let's consider this one, which is here, where I represent these strings between my two protons that correspond at least to two gluons. Because as I said, you cannot get one gluon exchange, because if not, it will not be a colorless exchange and the protons will be destroyed. So it can be here 2 gluons, 3 gluons, 4 gluons, 5 gluons, as many gluons as you want, but not a single one. And this will explain why the two protons are intact in the final state. And in the case of elastic events, there is no system X here. You have the two protons that are intact and nothing else. So what tools do we have? So concerning proton-antiproton interaction, as I said, there was a very strong group from Mexico in the zero collaboration. So we have the PP bar collider that was called the Tevatron, that was located close to Chicago. And we had 1.8 TeV or 1.96 TeV at the center of mass energy. And there were two main experiments, CDF and D0, and I am still member of the D0 collaboration. About the proton-proton collider, I mean, all of you know about it. I mean, there is the Large Hadron Collider, which is the highest energetic collider now in the world. So there are many experiments, 4 main experiments that are ATLAS, ALICE, LHCb, and CMS. And what we will be discussing are the data from CMS and TOTEM, which is located at interaction point 5, as a jargon kind of a way. What we need to know, this is a view from the accelerator. So this is at the border between France and Switzerland. The circumference is about 27 kilometers, and it's located underground between 50 and 100 meters. So what tools do we have in order to measure this impact proton in the final state? And these are the kind of a schematic of the tool that we are going to use to measure this impact proton. The idea is very simple. You have the beam, which is here. You see it is in the middle of the beam pipe, which is here. And what you want is to measure intact protons that are very close to the beam. You should imagine that, for instance, the collision point was here. The protons are scattered at very small angles because they lose part of their energy. And we need to move the detector as close as possible to the beam so that we can measure the protons that are scattered at very small angles. So the idea of this kind of detectors is to have a detector which is far away from the beam when we inject the beam, because then the beam is not stable and we have lots of background. But when the beam is stable, you can move it very close to the beam, as close as possible. And what I am talking close possible to the beam is up to 3 feet now from the beam. So it's really very close to the beam. So, and typically, the typical motion for this kind of detectors is around 2 to 4 centimeters, depending on the experiment. So you see the kind of level of motion that we are talking about. And why do we call it a Roman pot? Roman is in fact because the first detector like this was built long time ago by the Rome group, and the pot simply because it looks like a pot. I mean, that's why people call it a Roman. So this is a view of the tunnel, which gives you how it looks like in reality. So again, the beam line is here. There is here a bellow that allows to move the detector, which stands just on the top, as close as possible to the beam. And this is the location in the tunnel. And these detectors are in the middle of this green rectangles that are here. It's probably not easy to see because there are lots of cable. I mean, the tunnel is very busy, but you might guess this kind of Roman pot detector that are here. So now let's see a bit what is this kind of Oderon that we are talking about, that we want to look for. So as I said, I mean, what we want to look to study is the events where both protons are intact in the final state, and there is a colorless object that can be exchanged between them. And in fact, for this colorless object, there can be Pomeron and Oderon, and it depends on the value of the charge parity, which is the charge conjugation that changes the sign of all the quantum charges. And in fact, Pomeron and Oderon, they correspond to different values of C parity, positive for the Pomeron and negative for the Oderon. Which means if you want to think this in terms of QCD, so in terms of gluons, the Pomeron is made of an even number of gluons. It can be 2, it can be 4, 6, 8, whatever you want. And the Oderon, which has a negative parity contrary to the Pomeron, which has a positive parity, correspond to an odd number of gluons. Well, that's why we call it Oderon. So this can be 3 gluons, 5 gluons, 7 gluons, 9 gluons, and so on. So, and what it means, in fact, this is the kind of very simple equations. That is the amplitude of the proton-proton interaction. For proton-proton interaction, this is the sum of the even and the odd part of the amplitude. Whereas for PP bar interaction, this is the difference between the even and the odd part. So from this very simple equation, you see that if we see some difference between proton-proton and proton-antiproton, maybe we could have some evidence on this other end. So this was the basic idea, the starting point of all this study. So, and again, from a more modern way to see the things in terms of QCD. So this is the way that we have hadron interaction. So there are multi-gluons that can be exchanged between the two hadrons. And this is driven by the so-called Bartel-Krishinsky-Prasalovich equation. And from this image, you get, for the leading diagram, for these two pomerons, as I said, there are the two gluons that can be exchanged. It's a gluon ladder, so there are many gluons that are here. And for the deuteron, it's dominated by this two gluon exchange. And what we are going to look at is some potential differences between proton-proton and proton-antiproton interaction that might be an indication of the existence of the deuteron. So let's see what the data will tell us. So before we move to the data, let me explain, especially to the students, how we do the measurement. So it's always a bit the same when you want to measure some cross-section in high energy physics or in nuclear physics, you want to count the number of events as a function of different variables. So this is what we call the cross-section, or this is the number of events, and here we measure it as a function of t, where t is the quadri-momentum transfer square at the proton vortex, and this can be measured by tracking a proton or the amount of it. And we explain there are different sources. We have this which is the nuclear region. Between the two, there is an interference region. There may or may be not some structure, and then at higher T, we reach the perturbative QCD. So this is what we expect if we measure the number of events for elastic interaction as a function of T. So, and indeed, there were already, before the LHC, some previous measurements. So this is, for instance, a measurement at the ISR, which was 53 GeV. So they measured the sigmoidity, so this number of events as the function of T. And what they did, they compared between PP, which is in black, and PP bar interaction, which are the empty circle. So you will tell me that, I mean, there is already a difference here. So why the deuteron was not discovered at low energy? Because we see indeed some difference between proton and antiproton, PP and PP bar interaction. And it's in fact because the situation is not that simple. Let me go back a couple of slides maybe. When I discussed this with the exchange of the pomeron and the deuteron, is that there could be many more exchanges actually, so it's not that simple. Especially there can be some vector meson or what we call region, kind of barbaric name exchange. So what we have to know is that it's not only pomeron and deuteron exchange, which means that the situation is more complicated. And this kind of difference could or was interpreted as the exchange, for instance, of the omega naught. So that's why it was not interpreted as the exchange of the deuteron. So that's why finally this difference is not a clean proof of the existence of the deuteron. Okay. So now what is going on at high energy? So before I show the results, I just want to show you what were the predictions before we turned on the LHC. So this is again the sigmoidity as a function of T for different parametrization. And you see that basically these parametrization, they go all over the place. This is in logarithmic scale. See that some of them are very flat. See that this black one, for instance, doesn't have any maxima and minima. This blue one shows some minima and maxima, like for instance, the other one, which is the reddish one. And again, many orders of magnitude in the prediction. So this is before the LHC, so the situation, to say the least, was not clear, and almost nobody thought about the other. So now let's come to the measurement. So these are the sigmoidity data as a function of T for different square root of S, so 7 TV and 13 TV measured by totem. I will come back to what are the measurements by totem. But what I want to illustrate of this figure is that in fact the behavior as a function of T, you see that it's basically flat. We don't see any minima and maxima as some, basically some parametrization factor. And what does it mean? In fact, is that LHC energy, we are dominated by pomeron and deuteron. And this is a fundamental point, because we can forget about meson exchange and also region exchange at high energy, at the LHC energy. That's why we can look for the Oderon as a potential difference between proton-proton and proton-antiproton interaction. And this is indeed what we do. So let me come in the data set that we have. As I said, so the data that we have for PP pair interaction is coming from Fermilab, from the Tevatron. So this is from the D0 collaboration. The data are shown here. So this is the sigma dt as a function of T that were published with about 30 inverse nanobar. So now, if we go to Totem, so Totem is a collaboration that is installed some Raman pot detectors that are close to the CMS detector. And in addition to the Raman pot, which is very important if you want to measure elastic interaction, they have two telescopes, which are called T1 and T2, that cover the very large rapidity domain of the collaboration. Why is it important? Because you want to study elastic events. So in addition to the two protons, there is no particle that has been produced. So you can use this very forward detector as a veto to be sure that these are indeed elastic interaction and there is no particle that is produced in the forward direction. What is also the advantage of the LHC? The advantage of the LHC is that we can run, first of all, at different center of mass energy. The LHC run, in fact, at the highest energy so far at 13 TeV for the data. We are using also a bit slightly higher energy, 13.6 right now. But we have data at 13 TeV, 8 TeV, 7 TeV, and 2.76 TeV. And as we will see in a minute, this will be crucial for the Oderon discovery. And also something which is important for the LHC, which is illustrated on this plot, is that we have different methods to inject the beam at the LHC. Or in other words, what we call different beam lattice. And this allows to cover different domains in T. I will comment only this green part, which is here of the figure that corresponds for 13 TeV. So this is a so-called beta star, which describes how the beams are parallel between each other. So if you are at very large beta stars, you cover this region 10 to minus 4 up to, let's say, 1 or 2 GeV squared. And if you are at a beta star, which is higher, for instance, 90 meters, which is here, you see that you can cover the region 10 to minus 2 up to 3.5 for GeV squared. So this is basically different ways to obtain a very good coverage in T for the measurement of the elastic cross-section. So let me just show you the data. So as I said, so we can run the LHC at different center of mass energy. So this is the data at 13 TeV, so it's probably not very visible because the error bars are so tiny that you don't see the error bars on the point at 13 TeV. Then you have the data at 2.76 TeV, and here you have the data at 8 TeV, and we have, in addition, also some data at 7 TeV. So just I show the data around the dip and the bump, which show what we call the minimum and the maximum of the sigma dt data for the different values of square root of this. So what is the feature or the characteristics of this data? What we see is that the sigma dt decreases, it reaches the minimum, but it increases, which is a maximum, and then decreases again. And this pattern is found for all values of square root of x of the measurement. And if you remember for 1 minute what I showed you for the wrong direction, for the PP data, you don't see this kind of minimum and maximum. Cross-section decreases, and it reaches a kind of plateau, maybe decreases for the latest point, but the uncertainties are very large. But we don't see this kind of structure for PP bar interaction. So what does it mean? It seems that there are some different characteristics between proton-proton and proton-antiproton interaction. And this is what we wanted to use to express the difference between PP and PP bar, because this, again, our goal is to show some differences in order maybe to see the other. So this is the way we defined it. So this is for PP interaction. As I said, there is a minimum and the maximum. So it's already this kind of structure. And we defined 8 characteristic points of the behavior of elastic PP interaction as a function of. So there are 2 of them which are obvious, like the tip and the bump. And we define 6 more. For instance, the same value of the cross-section at the dip, but at higher T, which we call dip 2, mid 1 and mid 2, they are just in the middle. Bump 2, the same cross-section as at the bump, but at lower T. And finally, bump plus 5 or bump plus 10. That corresponds to 5 times and 10 times the difference in cross-section between the bump and the dip. So this gives us this kind of 8 characteristics. So what does it give us? So it will be a kind of characteristic behavior, again, of the elastic cross-section as a function of T for different square root of it. Why do we need to do this kind of gymnastics? It's because if we want to compare PP and PP bar data, PP bar data was measured at 2 TeV, let's say 1.96 TeV, which is the square root of S of the tevatron, whereas the LHC measurement are at 2.76, 7, 8, and 13 TeV. So we don't have common measurement at the same square root of S energy. So we need to extrapolate the LHC data down to the tevatron energy. That's why we need to do this kind of gymnastics. So what is the first observable, which is the simplest one? You measure the ratio of the cross-section of the bump divided by the dip to compare between PP and PP bar interaction. So PP data, this is basically these points which are here. These are the measurements from totem that are here in black, and the measurements at the ISR, which are here in gray. And they are compared to PP bar interaction, which is something which is compatible with 1 for all square root of S, because we don't see any dip and bump. So definitely, only with this simple observable, we see a difference between the PP bar and PP interaction, and this ratio is about the difference about 3 sigma between the two. So in order to do something a bit more complicated, what we did is to plot how this kind of characteristic point that I introduced before, the bump and the dip are the most obvious one, but all the others are here. They are measured for all the square root of S that we have, 13, 8, 7, and 2.76 TeV data. And here we display the T value and the cross-section value. And what we need to do in order to make prediction at the same square root of S at the tevatron energy is to extrapolate this point down to the tevatron energy. And these are the stars that are shown here. So what can we mention about it? First of all, the data at 2.76 TeV are really crucial to make this extrapolation. Because in fact, the difference between the tevatron energy of 2 TeV and 2.76 TeV is not that large. So this was really important to get this data of 2.76 TeV. So what do we get? So now we have all these characteristic points that are predicted at the same energy at the tevatron. And in order to compare directly with the D0 data, we just need to compute what are the value of elastic PP cross-section extrapolated from totem data in the same T bins as they were measured by D0 for PP bar interaction. So how do we do this? In order to predict this PP elastic cross-section, we fit this reference point, and we're using this double exponential formula. And we take, in fact, potential differences in normalization between totem and D0 data, because there may be some difference in normalization that are related especially to luminosity uncertainty, which amounts at about 14%. So for D0, so there was a large luminosity uncertainty for D0. And to take this into account, we adjust the data set to have the same cross-section at the optical point, which is d sigma dt at t equals 0. So this allows to make a direct comparison between PP and PP bar data. So I don't want to enter into all the detail, but I want to mention that this renormalization factor between the D0 and the totem data is that we rescale the totem data by about this factor 0.954, which is well below this kind of luminosity uncertainty. Again, this is in order to adjust normalization. So now it comes directly to the Bonney plot, which is the comparison between the PP bar measurement by D0, which are the blue circle, and also in red, you see the predictions coming from the extrapolated totem data, which are the red triangles with their uncertainty. And immediately, you see on this plot that we have indeed some differences between the PP bar measurements and the PP extrapolation data. And this difference leads to a significance, which is of about 3.4 sigma. So the comparison of both these data sets leads already to a kind of significance of the existence of the Alderon or the 3, 5, 7 gluon exchange from the QCD point of view. So now it was possible, in fact, to combine this data with a previous measurement by Totem, which was to measure the elastic cross-section in the long When I mentioned diagram, school region was basically a very low T, 10 to minus 3, 10 to minus 4, where for now we compared the elastic PT and PT bar cross section in the deep and bump region. So in the region which is more in the order 1 G. It's a completely different domain in T where we perform the comparison. That's why we can combine the significance of the Alderon for these two domains. Everything. So, as I said, so in this Coulomb and nuclear interference region, so this is the sum of the amplitude for the Coulomb region and the nuclear amplitude, which is here. And in fact, you can show that it's possible in this region by measuring the cross-section to measure what we call the rho parameter, which is the ratio of the real part of the nuclear amplitude at T equals 0, divided by the imaginary part of the nuclear amplitude also at T equals 0. And this is an independent evidence for the Alderon. Let me show you two values, the total cross-section and the zero parameter that I just introduced. And they are compared, the measurements from Totem are here in red, and they are compared with different set of parameterization. The blue one is we express the total cross-section as a log S, log squared S term. And for instance, the green one is only a log S term for the total cross-section. But what is important is that you see that the total cross-section prefers this kind of blue parameterization, whereas the rho parameter definitely prefers the green kind of parameterization. And I should mention for none of this parameterization, there are about 150 parameterization in this plot. They had an Alderon, which was included. It's only a Pomeroy. And the easy way to interpret these differences is by introducing also the Alderon. So this was considered as an independent way to have some evidence of the Alderon. So we can combine them because, in fact, they correspond to different data sets. And if you combine them, you get a significance which varies between 5.3 to 5.7 sigma, depending on the model, because again, the previous plot I showed you depend on the model. So it means that the models without colorless C-odd gluonic compound, or what we call the Alderon, are excluded, including all the different set of models that I just showed you. So far, there is no other explanation of this difference, if you want, without adding the Alderon compared to the Pomeroy. So this was the result that was basically discovered about one year ago for now, so published in Physics Review Letters. And this was the kind of a big discovery, which was done by the Totem and the Zero collaboration, which are the two collaborations across the Atlantic, which is also nice that we needed some collaboration across the Atlantic. So now, let me come to the second part, a bit of the talk, which is to discuss how we can be sensitive to beyond stellar model physics using the same kind of method by detecting the intact photons in the finite. So, as I said, I already mentioned this kind of detector, what we call Raman plot detector, to measure these intact photons. And now we are going to run this detector not only at low luminosity to measure elastic events, but in standard runs at the LHC. So it means that we are sensitive to very high luminosity, and the method to inject the beam is quite different. Just to give you some ideas of the difference, this is the acceptance in mass of the two photons. So what I'm calling this mass, if you have this kind of QCD events where you see you have two gluons that are exchanged in order to get a colorless object, and they can produce two jets, or the way another method to get a colorless exchange is, of course, to have an exchange of photons. And you can produce a system of mass X, which is here. So in terms of mass of the two jets of the photons which are here, this mass X, so we see that the mass at high luminosity varies between 450 GeV up, let's say, to more than 2 TeV, about 2.3, 2.4 TeV. It means that the acceptance of this forward detector is going to very high mass, which is quite important if you want to study beyond standard model physics, because you want to be sensitive to high mass production. So what are the kind of diagrams that we want to study? So this is, again, two protons are intact in the finite state. The protons, they emit quasi-real photons, and as an example, they couple to produce two photons in the finite state. This is what we call quartic photon couplings. And here it could be two photons, or we will see two Ws, gamma Z, for instance, or 2T bar. Many other particles can be produced in the same way. But what is important, I mean, this is, for the student, it's a pure quantum effect, because what we are doing at the LHC is that we are colliding light against light. I mean, without quantum mechanics, this doesn't exist. We cannot collide light with light. So what we see every day using this kind of diagram at the LHC is light by light scattering. And again, we will measure and we'll detail, for instance, when we produce two photons in the finite state. And there are many papers that I put here, which were published with my students. Okay, so why are we interested in studying this coupling? You can have a loop of new particles that can be produced, or also there can be a resonance that can be produced. In case of loops, you have the coupling between this four photon is proportional to the force power of the charge of the particle in the loop, divided by the mass also of the force power, and it's also proportional to the spin of the particle. For typical beyond standard model theories, we expect couplings which are of the order of 10 to minus 14, 10 to minus 13, GeV minus 4. So this is the kind of value that we will get. In the case of resonance, you can have this kind of a diagram, as I said, and in that case, the coupling is the coupling gamma gamma to x to the power minus 2, the mass to the power minus 2, and also proportional to the spin of the particle. And in the same way, you can expect some couplings of the order of 10 to minus 13. So now let's come why it's interesting to measure the photon in the finite state. Let's discuss what is the standard model component. Like I said, there are two diagrams. Gluon diagram, which is QCD diagram, and this QED, where you have a photon-induced process. The cross-section is shown here as a function of the cut on the two photon mass, which is here in the finite state. This purple line, which is here, corresponds to the QCD diagram, and the black dashed line correspond to this diagram, where in the loop, you need, of course, to have charged particles. So it can be quarks, it can be leptons, or also W boson. So we took everything into account. And you see immediately that as soon as you are above, let's say this is 200 GeV, you can forget about the QCD curve, which is here, and only this right diagrams is really to be relevant. So what is the conclusion? If you remember the acceptance in mass of our forward detectors, the Raman pot detectors, to measure the proton, it starts something at 400 GeV. So it's even outside this plot. So it means you can forget about the QCD diagram. So it means that if we measure two photons and two protons, we are sure that it is a photon-induced process. So the conclusion, two photons and two tag protons means we have a photon-induced process. So we consider the LHC as a gamma-gamma collider. And this has many advantages. Why is it like this? So let me maybe go back once again to the signal events, which are here. So you see that we are getting very clean events. I mean, the two protons are intact in the finite state. You have two photons and nothing else. It means that big kinematical conservation, the mass of the two protons and the mass of the two photons should be the same, and the same for the angular distribution. So this will be an extremely powerful way to get rid of the background. So what is the main background that we need to consider is what we call pileup. Pileup is when you have two photons that are produced, the photons are destroyed, plus we have to consider events in which, for instance, one of the protons is destroyed, one is intact, and there is a photon exchange between the two. So this corresponds to soft QCD. And why do we need to consider this kind of events? It's because at the LHC at high luminosity, we don't have a single proton-proton interaction, but we have up to 50 proton-proton interaction within the same Wald process. And what is illustrated on these two plots is the ratio of the proton mass divided by the two photon mass, and the difference in rapidity or difference in angular variable between the two photon and the two proton system for the signal, which peaks at 1 and 0, because of course, both of them are related, as I mentioned. And for the pilot background, it's almost a flat distribution, because again, my intact photons have nothing to do with my two photons for the pilot. So this is a very clean way to get rid of the background. And this is what we proposed, in fact, more than 10 years ago when I was still in France, in Saclay. And now it's becoming a reality. So especially I will show you some results from CMS and Totem that just came out very recently. So now this is for the search of the two photons, as I said, and you have this correlation, difference in rapidity, here difference in mass between the two photons and the two photon system. So this is with about 100 inverse centoband of data. And the signal events should be in the middle of this green square, where we are getting 0 for the two. And you see that we have basically one candidate. And we expect one background for this 100 inverse centoband, so there is no signal. So this led to these limits, which were the best limit so far on the quartic photon anomalous coupling that were achieved at the LHC using this kind of method. And this is the correlation plot on the sensitivity, the limits, zeta 2 versus zeta 1. So now, so this is basically what we obtain in terms also looking for axion-like particle, what there can be gamma-gamma going to axion, decaying into photons. So this is the present limit from CMS and Totem coupling versus mass of the axion. So again, the first time that we get the sensitivity at the LHC. And this is the same coupling versus mass extrapolated using 300 inverse centoband of data at the LHC. And you see that we gain quite a lot in sensitivity, about 2 orders of magnitude for a mass, which is, let's say, around TeV, and we even extend the domain of higher mass. So that's why it's very interesting to look at this kind of processes. And I must say that we gain about 2 orders of magnitude with respect to the standard method of the LHC. This is a very powerful method to be sensitive to this beyond standard method. So now I just want to mention very briefly that this complementary to the heavy ion run at the LHC, because in fact for heavy ion runs, the cross-section is increased by a factor z to the 4th. I will not enter into the detail, but that's why in that case you have much less luminosity, but you can be sensitive to axion-like particle in the domain of 10 GeV, 100 and a few 100 GeV, which is. So I want also to mention, as I said already, there can be also in the same way to produce some W pair production. So we are sensitive to quartic anomalous coupling, gamma gamma WW as an example. And again, the same method. You look at the correlation between the two photons at the WW information in rapidity and in mass. The signal is expected to be here just around 0, which is here. We do not see any signal. So this led to the first limit from CMS to 10 that are shown here, as for instance, for this quartic anomalous coupling. And all the numbers are here, so I will not detail all the numbers. But again, they are the best limits to date using about 53 inverse centoband of data. And this allowed to put a limit also on the standard model exclusive W pair production to be less than 67 femtoband and the same 43 femtoband for Z production. So using, again, the same kind of method. So what I want to mention is that also from the future point of view, it would be possible to measure the standard model production of exclusive WW, so gamma gamma going to WW. So this is the process. So I can show you the result of pure standard model. So this is at high mass. So whereas for the standard model, you see that it appears at much lower. So while we looked in a pure jet channel of the W pair decays for the high mass events, because this is what gives the highest cross-section, it's no longer possible to observe the standard model events because of the high dijet background. That's why in that case, we will look for it in the leptonic decay of the W impulse. And using this, we predict about 50 events that can be observed in the leptonic decays with the tagged protons with 300 inverse Linke for 2 events of background. So wait for the data is definitely promising to be able to do this. I will just mention briefly, so I'm just toward the end of the talk. In the same way, we can measure the gamma as gamma Z production. So it leads to a very good sensitivity, which is 3 orders of magnitude better than the usual method of the LHC. The usual method of the LHC is to look for the Z boson decay in 3 photons, which is very difficult to do. Same way, we can look for gamma gamma to TT bar, so I will not enter in the detail, but I will just mention that we looked for it. So far, there is no observation of this exclusive TT bar production with the luminosity that we had. So we obtain an exclusive TT bar production, which has to be less than 0.6 microbar. So I will just finish by discussing briefly a bit the hardware measurement that we can, development that we can do. And this is related to the measurement of the time of peak. Because what I was telling, I mean, one way to get rid of this pileup background is to measure the mass of the 2 photons and the mass of the 2 photons. Another way is to measure very precisely the time of flight of the proton. Why can we do this? Because if you see the protons originate from secondary interactions, we know, of course, the position of the detector, the Raman plot that are far away. So if you measure very precisely the time of flight of the proton, you can constrain the protons to originate from the same vertex, for instance, as the W pair production that we see. So this is why we developed new detector to measure precisely the time of flight of the proton. And when I am talking about precision, we need a time precision which is of the order of 10 picoseconds. So this is extremely good precision for the time measurement. How do we do this? It's very simple. So you have this ultra-fast silicon detector. A proton is crossing this detector. We measure the signal through the silicon detector. And what is very important is that this signal is very short. It's basically just a couple of nanoseconds. We will see in a second why it is very important. So what do we do to analyze the signal? So you have the signal. After some amplification, we do a very fast sampling of the signal which is here. So how does it work? We have this very fast sampling, so we can reconstruct, for instance, here precisely the decreasing part of the signal or the full signal. And this very fast sampling gives you a time stamps when the signal arrives in the detector, and when the particle also arrives in the detector. So what I want to mention is more the application, because this is a bit the idea that we can have and collaborate also with Mexico. Either, for instance, what we have one project, which is with NASA, which is to measure the cosmic ray which are produced in space using the same cosmic ray detector, using the silicon detector. The idea is basically simple. We have different layers of silicon detector, and we measure the signal when the particle stops in the given layer of the detector, what we call the bright peak of the bright peak emission of that particle. And by measuring, using this very fast sampling method, the time of the signal or the duration of the signal, which is again a couple of nanoseconds, and also the amplitude of the signal, you can relate it to the type of the particle that has been emitted and also to its energy. So this is the way that we measure the kind of particle and the energy, which is basically, which will be produced in cosmic ray in space. So this is a collaboration with NASA. So it should have been launched actually originally in spring 2002, but there were some delays due to COVID, and because this has to be launched, in fact, by the Air Force in the US. And this will be more towards now the beginning of next year. But at least the detector is ready to be launched. So we are just waiting for the launch. So another application that we were thinking to develop, and we are starting to develop with Mexico, is to use the same kind of detector, but to measure radiation where people are treated for cancer, especially for flash beams. The idea is, again, very simple. You use very intense beam, you send in to a tumor, for instance, a tumor in the brain, and want to measure the dose that is received by the patient with high precision. And so far, people don't know how to do it with high intensity beam. I mean, with very short beam, but high intensity, nobody knows how to do it. So the idea is the same. We use the same silicon detector with a very short signal. We do some phase sampling, and we can count the number of protons that have been absorbed by the body, by the human body. So from this number, we can relate it to the dose that has been delivered to the patient. So this is for now just an idea on the table, but definitely we want to have development. And again, this is very promising because there is a huge market in the world, the full world, and nobody did it so far. So this is something that we can develop together. So I just want to conclude. So I guess I spent a lot of time on the Oderon discovery. I mean, this was also the point of one of the points stressed by the medal. So that's why we got some range of 5.3 to 5.7 sigma comparing PP and PP bar interaction. So this is how we got the discovery. Then I discussed a bit some beyond standard model studies to study quartic anomalous coupling by tagging also the proton in the final state. That leads to a very good sensitivity because in fact we measure like at length all the particles that are produced in the final state. And finally, I mentioned very briefly some kind of detector development that we can have in medicine and cosmic ray physics. So where we can have also some collaboration with Mexico in addition to the CMS collaboration. So this is, I just want to show you a small cartoon to finish. So this is, you see, these people, they are in a safari in Africa, so they are looking for animals, but definitely they are not looking in the right direction because they don't see even the lion, which is sitting just in the back. So we should not do this as physicists. We should look everywhere. And who knows, maybe in the LHC data, there is a lion sitting somewhere, which we should not miss. So thank you very much.
So thank you very much to Professor Royon. We have only few time for questions, but we can ask one or two questions and then we can continue talking with Professor during the coffee break, which is right now. And also there is a photo of the event. So Pablo, who is you? Okay.
Thank you very much for your nice talk. I wonder about the production of these exotic states, Oderon and Pomeron, but in this time not from the elastic collision of protons, instead of maybe electron-positron collision, scattering collision, for example, or what about the possibility of the production of these states, but directly from the case of heavy particles, for example, B mesons. I am thinking in B factories, for example.
It's completely true. I mean, it's another way to look for the Oderons via the decay of vector mesons or the production of vector mesons that can be produced only via, for instance, Pomeron-Oderon interaction. And people have started to look into it because we accumulated millions of events in the data at the LHC, so especially using the totem and CMS data. So the data are being analyzed, but there is no result for now, no official result. People have been looking for this also in previous data at ERA, for instance, and there was no signal that was found. So, but this is more for the perturbative way of producing the Oderon. And again, data are there, so we need to look at them. There are not that many people that are involved in this measurement, unfortunately. So that's why it's a bit slow. I mean, it's a small number of people, but hopefully we will see also something there. And people also will look, I know, also at RIC, for instance, independently, if they see a signal also.
Thank you very much. Now we have the coffee break. After that, we have the peak of the event, but also an announcement. There is some sponsors outside that you can go close to them and they have their catalog and so on. So in case you need to buy something, some electronics devices. And the photo is now, Arturo told me. So it's going to be outside, I guess. Okay. Thank you very much, everybody. Thank you again, Professor.
Sí, por ahí. Bueno, ok. César, es solo un micrófono, ¿verdad? ¿Dos? Sí, es lo que... Alejandro. Ah, ok. ¿Verdad? Pues sí. Okay, hello. So welcome to the second session of this morning. We have to shorten a little bit the coffee break just to try to be on schedule again. Okay, so this second session we will be starting with a talk from Genaro Toledo, that is from the Instituto de Física at UNAM at Mexico City. And he will be talking about the role of RO 1450 in low energy observables. So, Genaro, go ahead.
Thanks. Okay, thank you everybody for being here. I'm going to present our recent research that we have been doing with the students Gustavo Avalos, Antonio Rojas, Marcel Sanchez, and myself. And it is interested to present about the RO 1450. We usually call it just the RO prime. And the idea is to first to present why is it important. Given the precision measurement that we are finding in experiments, now we are reaching the precision where you have to go to other states besides the usual hadron states in low energy experiments. So I will go on that. Then I will present a brief description of low energy processes, a set of processes that involve these parameters and allows to fix where the couplings are. And then I will go to a global analysis. This is going to include decay modes and cross-section data. And I will try to split each contribution to show how the parameters are involved in each case. And at the end, I will present results and conclusion. So this is the RO prime. Basically taken from the PDG, you see this is the hadron spectrum. This is the usual low energy hadrons that we know. Here is the RO. So the RO prime is an excited state of the RO 700. And the parameters are not settled in the PDG. So although we know that it's there, we know the mass, the width, the total width, most of the decay modes are just seen in the PDG codes as seen, but if you go to the experiments, of course, you find the values that they have measured. So, but this is important because in this case, if you know the decay modes of these particles, then you can go and do predictions. Right? Of course, the contribution which comes from this kind of particles is small at low energies, but anyway, given the precision, as I said before, it can be important. For example, here you can see the effect in tau decays and E plus E minus to hadrons cross sections. This is the description of E plus E minus to pi gamma. And this is the experimental data. And if you include only the raw contribution, which is the dominant part, you cannot explain the remaining data. So this difference is driven by the raw prime. In a similar way, in tau decays, this is also dominated by the raw. And if you include the raw prime and even the raw biprime, you can properly describe the data. If you omit that, then you cannot account for that region. You can also notice that there is a large error bars. While you can identify the mass and the width, as I said, the more detailed description of this kind of particles is still not settled. So let me exhibit how is the procedure that we follow to describe this kind of particles. We can follow the vector meson dominance approach. The idea is that the hadrons are the relevant degrees of freedoms at low energies, and then you have couplings. So you have to fix the coupling somehow. You can have an approximation from, for example, chiral symmetry using remaining symmetries of QCD, and then you can have a equivalence in the couplings, and then you can draw some analogies between them. So this, although vector meson dominance has not that broad implication in relation of the symmetries, anyway, you can always draw relations with other models. So basically, this is the Lagrangian. Let me just focus in the couplings because this is the main point of the work. Here you have the coupling between the vector and two pions. You have the omega meson with a vector and another pseudoscalar. In general, it's going to be also pion. Then you have couplings. These are kind of Westomino with an anomaly contribution, which is called the G3 pi, which couples the omega meson with three pions. And this is one of the main characteristics of vector meson dominance, where you couple a photon with a neutral vector meson through this kind of couplings. So that's the basic description. So using this basic Lagrangian, then we can go to describe low energy processes and try to see if these couplings are well settled or not. So the idea is that we can go further in many processes. So the rest of the talk is to present a set of processes where this description can be made and point out to the couplings that are involved, and then I will go to a global analysis of these couplings using experimental data. So for example, for vectors going to two pseudoscalars and vectors going to a pair of leptons, you can write the amplitude, and you see again, here is the vectors to pseudoscalar couplings, and this is the vector to photon couplings through this part of the vector to photon couplings. So basically, then you can compute the width, the decay width, and you know the relation between the width and the couplings. This is the experimental information. Then you can extract which value corresponds, provided that you know the mass and the width of the particles. So for us, the masses and the widths are not pre-parameters. You can also have radiative decays, vector to pseudoscalar photon or pseudoscalar to two photons. Again, you can write immediately the amplitude and go to check what is the form of the decay width. There are more details in the description. It can be refined, including higher resonances and other contributions. We are thinking that we are in the low energy regime. So what I'm presenting is the dominant part. So for example, using the previous equations, you can check for the rho going to two pions, the neutral and charged one, and then you extract the rho pi coupling. You can see the precision is relatively good, and you have a weighted average in this region. notice that this is just from one single experiment, and then you take the information. If you do the same now for the radiative processes for the omega going to pions and rho to pi gammas and pi gamma gamma, then you notice that you have this rho omega coupling, which is common to all these processes, but then you have a split on the values that you have. Then you can wonder what is happening there. So you have to go deeper in the description of that in order to see if this value can be made in agreement with all the experiments. And this is the next step in that process. You have to see if is there anything missing and if the correlation between these contributions is taken into account or not. For example, for the omega going to 3 pions, as I said before, if you consider only the rho contribution is the omega going to rho pi and rho going to pi pi, that is the dominant one. So the same diagrams can be drawn or the rho prime pi, but we need now the couplings for the rho prime pi I. The G pi that I mentioned before. So if you do this description and compute without including the rho prime, then you cannot account properly for the decay width, and at the same time being compatible with other with the previous measurements in other channels. So now requires the inclusion of the rho prime and the contact term. Once you include this, of course, you are increasing the degrees of freedom somehow, but then now you are in better agreement. Here is the amplitude. The way we proceed is to, once you write the amplitude, here are the details, but then what is important is to see that the decay width can be written as an expansion on the couplings that are involved. The usual way is to write just the square of the amplitude and the phase space and integrate. But in order to do a global analysis in the numerical sense, the better way is to do this expansion, leaving the free parameters, which are the couplings as coefficients, and the A1, A2, and so on coefficients can be computed in a single run, and then to determine what are the couplings corresponding to the. Another process now, those are decay modes. Thanks. If we go to hadronic processes, for E plus E minus going to hadrons, then you can do the same game and do the expansion and compute the cross section. Again, let me go back. You have the cross section coefficients and all these contributions for the couplings. Then you can compute all of them. You can see Leonardo Esparza's poster for the details of the E plus E minus 2 pi pi gamma. So what is the global analysis that we have performed? So we define the chi-square function to minimize, and the way to implement all these contributions is to do first an analysis for 10 decay modes for the radiative that I mentioned before, and the hadronics and leptonics, and the decay modes for the omega to 3 pi. We will notice that there is this need that I already mentioned for the inclusion of the rho prime and the contact term. And then we can implement a data for E plus or minus 2 pi pi from SND. They have published in 2015 and 16, and also CMD2 has data for this one. And for E plus E minus 3 pions, we have SND, Bavara, CMD2, and BEST3, which is preliminary result, which is the process. So for the decay modes, if we include only a reduced section of information of the experimental part, we obtain the parameters, and we see also this in this heat plot, the correlation between them, which is important because, as I said, when you do a single observation, you are missing the correlation with other experiments and also in the couplings. If you do now the inclusion of the omega to 3 pions and the data for E plus E minus to pi pi gamma, you have to extend the coupling. Now you see here are the rho prime involved. Also a phase which becomes very relevant in the fine description of the spectrum. And the correlation again, is the one is the maximum correlation between the particle itself, is a square matrix, and then the lighter the color is the less correlation between them. Here is the comparison that we obtain when we do that fit for E plus E minus to pi gamma. This is the experimental data, and this is the result that we obtain from the global analysis. So we have the total of the parameters are compatible with all these previous measurements, which are here in the 11 decay modes, and in addition to E plus E minus to pi pi gamma. You'll see the very good description. By the way, I have to say that the SND 16 is the updated of SND 00 and 15. And they included missing terms that were not incorporated in the previous analysis. But anyway, the difference is still very good at that. And TMD2 was also there. If you consider E plus E minus to 3 pions, then you also can do, again, the same analysis and check the correlation between them. Here you see that it's even lighter. Meaning there is less correlation. And we can also compare with the experiment, the fit. So this is the global fit, and then you just take the parameters and try to see if it is possible to compare with them. And basically the description is very good in all the cases. Just to summarize the result, because the tables are not easy to follow, but here I'm presenting the behavior of each parameter as we include different data information. And you see, for example, G rho pi pi is very stable no matter which kind of data you include. In this dotted line, you can see is the case where you omit the rho prime and the contact term, and you see that this is a jump signaling that there is a incompatibility between all the rest of the analysis to that case. And it is reflected in the G omega, G rho pi pi, and rho omega pi, which is here, which clearly is far from that. So that result was signaling the need of the rho prime and the contact term. And the rest, you can see that it's very flat in general, within error bars, of course, but at least now we have values for the rho prime pi pi, which is now presented here as a global term, and omega rho prime pi, pi, and this G rho prime, which was also not quoted in the literature, at least not as a final result. So that's basically the main result. As an application, once you are there, then you can go and apply this and see if you are able not to fit another result, but just to do a kind of prediction somehow. And this is the omega channel. You can see these details on Antonio Rojas' poster later. But this is the so-called omega channel. This is plus E minus to 4 pions. And basically this, you see the symbols are the data, and the rho prime is the green one, you see there. But our result is the solid blue line and the dashed black, which are almost one on top of each other. And the description is very, this is not a fit. This is what parameters. So this is important because it gives us confidence on how we are going to treat these kind of channels. I was going so fast, but this is important for many different contributions in other observables, for example, E plus E minus for G minus 2, or a prediction of magnetic dipole moment of the rho and so on. Okay. I think that's it. Okay, thank you. Let me conclude here and I won't go over to the conclusions.
Okay, so thank you, Genaro, for this talk on low mass vector mesons. So we have okay, so first, Pablo.
Thank you very much. It's very interesting and already very solid. I don't know if you will split the thing between different papers, but it seems like finished in some sense. Also for the application for the E-2, this will take time. Just a short question. Yeah, so E plus E minus to pi pi without the photon should be very sensitive to the rho prime alone. So perhaps you could just
E
check
plus
that
E minus
everything- E plus E minus to pi pi without the photon.
Sure.
So just to check that everything matches, perhaps you have already done this.
We didn't that. Yeah. In principle, it's similar to tau to pi pi, which I show you. Yeah. By the way, we have not included data from tau decays because we have to deal with other conditions. And also, this is a kind of work in progress. Our aim is to grow in this kind of analysis and to maintain this kind of analysis for low energy hadrons. So eventually we will be there.
Okay, and a final question from.
Thank you. Thank you. I guess this is a little bit outside your field, but I wonder, there may be consequences for the dilepton spectrum, say the mass spectrum at finite temperature and or density. In other words, typically around the rho peak, the rho is the only thing that is considered. Of course, rho prime is a little bit higher in mass, but still for the intermediate part of the spectrum, it may have consequences. Have you, I understand that it may be far away in your program, but can you, or have you thought about it?
I know you have worked on that, on finite temperature contribution for the parameters. No, we haven't done anything on that side. Well, it would be interesting to check, to extend now to temperature contributions for the parameters. That is mainly on the mass and the width. That's the part. Here is focused on the couplings. We are not using the masses and width as a free parameters. If you check the experimental data, they can take this as a free parameter, and there are some deviations even between experiments for the mass and the width. We are not going to that because that is more complicated that we can do with the available information.
Okay, so thank you, Genaro. We will have to cut the question, sorry, because we are quite
Thanks.
behind the schedule. So we thank Genaro again. Okay, so now we have another talk for mesons, also low mass mesons, excited mesons from Gustavo. So just hold on a little bit. So this is the talk from Gustavo in collaboration with Adnan Bashir and Laura Xiomara Gutierrez from MCTP. Okay, so go ahead, Gustavo.
Thank you to the organizers to give me the opportunity to be here. And this is the content, a little introduction, the model we use, Schwinger-Dyson equation, Betzel-Peter equations, meson, and the first radial excitation, some results and some conclusions. We can distinguish two different types of masses between the hadrons, the current quark mass that appears in the Lagrangian, and due to interactions, the quark constituent of rest mass. And this is the reason, for example, why the if we assume the mass, the current mass on the quarks between the inside of the proton, we obtain 10 EVs, but we know that the proton has this mass. Well, let's see for the breaking or chiral breaking, and this is the mass generated, for example, 300 MeVs, depending on the model, and DCSV is the mentioning that generates the 98% of the visible matter. We can see, for example, the generation of the mass for these quarks. We use the Schwinger-Dyson equations to solve this generation. I'm sorry, this thing don't mention it, but this is the Schwinger-Dyson equation that depends on the there's a gluon propagator, there's a quark gluon vertex, and so this. Don't worry. Well, we use this model, contract interaction model, that is a simplification for QCD, and we make this assumption. For example, for the gluon propagator, we consider this propagator as a constant in the infrared because this is a Dirac approximation, but with knowledge in the Landau gauge, we know that the gluon propagator becomes or behave as a constant in the infrared. And then we are interested in to calculate masses in this ultra infrared. And to the vertex, we assume that the 3 level, we consider the vertex. For the Feynman diagram from like scattering, we have the spectre. This is so easy to implement in the calculus. For example, when we calculate masses, the chi constants, but if we can calculate the form factors, we need to be careful because we only can calculate it in this region from the infrared. With this model, the Schwinger-Dyson equation is this one, and this equation has quadratic and logarithmic divergences. We need to regularize it, and we use a proper time regularization, and we obtain the equation that depends on the Kutz and the gamma function. We use these parameters to calculate the masses of the first radial excitation and the bond states. For example, we obtain these masses from different quarks. And to calculate the bond states and the first radial excitation, we use the Betz-Salpeter equations. This is the equation diametrically. And this equation has the quark propagator, the interaction kernel that tell us what is happening inside of these mesons. And according to the quantum numbers, we can distinguish different types of meson: scalar meson, pseudoscalar, vector, axial vector. For example, if we consider a pseudoscalar meson, for example, for the pion, this equation has 4 Dirac structures, but in this model only have 2 structures, in the other 2. With this equation, we have an eigen equation. We need to solve it when the eigenvalue is equal to 1. And this is the kernel of iteration depending on the C function. And when we make a more stronger analysis for the first radial excitation, we have a 0 in the amplitudes. But with this model, we can obtain a 0. And this is the reason we put a 0 by hand in the last equation. We need to find a parameter, this parameter df, to tell us what is happening with this 0. The kernel changes a little bit. The function c becomes in a function f, according to the final equation. We need to fix the parameter df. making an analysis, data analysis, we find this equation from this parameter df depending on the reduced mass from the bond states or the free radial excitation. And we find this function is very close depending on the channel of the mesons, but we can use the same function for all the types of mesons. Well, this is the results for the bond states. You can see, for example, for the draw meson, pi, etc. Vector mesons and axial vector mesons. But this word is for the fifth radial excitation. For example, you can see for the pion, for the fifth radial excitation, we have a little short error, and some of these particles doesn't have experimental result, but we can compare it with another approaches. This is for scalar and axial vector results. You can see we don't have experimental results to compare, but we can compare with another approaches, and we have a really good results. And for example, we can obtain a relation between the masses of these particles using the Gelman-Okubo formula. This formula depends on the quantum numbers. For example, you can see these two formulas, and we have a really short error, and we have a lot of these relations. We can make this analysis from the fifth radial excitation of the bond states, and we can obtain really good results, and we can make prediction about another particles. And this model is really easy to implement and teach us a lot about these kind of particles and hadrons too. For example, the proton, nucleon, and for example, this function we need to understand in a good way what is happening with this function. For example, we can use these parameters to calculate the fifth radial excitation for hadrons, and we have a really good approach, really good results comparing with the experimental results or another approaches. And this is all for me.
Gustavo, do we have questions? Okay, from Genaro, of course, related subject.
Yeah, at the beginning you mentioned about the dike works, but then you went really fast. Can you go a little bit on the dike variance part, the dike works part, please?
I'm sorry, I did a mistake, but it's because when we need to understand the hadrons, we use a model that considers a quark interacting with a diquark, and we need to be careful with the diquarks because they are not observable states. And the only thing we have to understand if the diquarks are in a good agreement is when we calculate the variance, and we can say, okay, the diquarks are okay. But for here was a mistake. But this is the reason why we study diquarks.
Thank you. So I would like to ask you about the difference between the sets of parameters for light and heavies. So in principle, I would expect, no, maybe not here, from the very beginning. Yeah, here. So in principle, you should be able to understand the difference, for instance, for C and B quarks, as an effect of running between the scales. Can you comment on this, please?
Okay, the different parameters here is because, for example, if we can obtain a really good results for the light variance, we use the first parameters. But when we use the heavy parameters, we obtain an error inside of 5% of error. And for all our calculation, we use the second parameters, but the really difference is in the cuts on the infrared and the ultraviolet.
Okay, so we have time for one last question. Again?
So, and I would like to talk to you later on the spin 2 case. Okay, because I think it is subtle. Perhaps you can just flash the results so that we see it and we can discuss later because it's lengthy. Can you show for spin 2? You had the current, the antisymmetric one.
Okay, can you repeat, please?
Yeah, when you were showing the interpolating currents for every spin and parity of the mesons,
Okay.
you also had this spin 2. But you didn't show the results, right? For
I'm
this
sorry, the
particular
computer
case.
doesn't.
It doesn't work. Okay, we can discuss later.
Okay, thank you.
Okay, thank you, Gustavo. So we thank again to Gustavo. So the following presentation, it's an online from Axel Weber that he's already there. He just, so Axel, can you hear us?
I can hear you. Thank you. Can you hear me as well?
The volume is quite low. Está muy bajo el volumen. No sé si.
Okay, my microphone is usually working well. So if you could crank up your volume, maybe. And
can you share
yes,
your?
I'm trying, but I think I only have the option to share the entire screen. Is that right?
Okay, so now we can see.
You can see a lot of things, but not. Let me see.
But it is overlap with
Yes. Yes, I have a kind of a mess on my desktop right now. Okay, let me see if I can do something better. So this is my entire screen, and now I'm trying to. Oh no. I try again. I'm sorry.
Yes, okay, much better.
Okay, but I'm unable to get down. Okay. So now I hope you can see my presentation.
Yes, we can.
Thank you. I'm sorry for that problem. Is there also sorry I couldn't be there with you in person. Now this is what I'm talking about today, gluon mass generation, and that work is based on this publication. And you also have my collaborators here, my colleagues from Heidelberg, Jan Pawlowski and Christoph Wetterich, Jonis Papavasiliou from Valencia, and two PhD students, Jan Horak and Friederike Isen. So I hope the slide changed now for you as well. Everything all right?
It changed.
It did. Yeah, thank you. Yeah. Okay, just to make sure, because it has happened before. It didn't change. Okay, so I'll be talking about infrared QCD here, going right into matters because I don't have a lot of time. So specifically about SUN Young-Mills theory and always in the Landau gauge. This has been scrutinized with different methods. In the continuum, there are Dyson-Schwinger equations and also functional renormalization group equations. And there have been, importantly, lattice simulations in the minimal Landau gauge. And in all these analyses, a massive behavior of the gluon propagator was found. And also I want to mention a very simple and easy to understand description in the continuum, which was first suggested by Tessier and Boschebor in 2010, which is just you take the usual Faddeev-Popov action and you add a gluon mass term, which is here. So you get the Curci-Ferrari model. This is the usual gauge fixing sector, and I've used the Kanishi-Lautrup field to implement the Landau gauge. And the result is quite satisfactory. So here I have a, trying to get that away now. This is a plot of the gluon propagator, the lattice data in color, and this is our result actually in collaboration with Pietro Dall'Olio, where we just take one loop perturbation theory with the action you saw on the last slide, and we renormalization group improve that with Cohn-Semantic equation. Then you get a quite impressive fit to the lattice data, and also the ghost propagator is actually perfectly fitted by this method. And admittedly, we use a certain renormalization scheme. We have been playing around with different schemes, and the initial value for this running mass parameter for the gluon is also adjusted, but still it's a very good result. Now, what I'll be talking about today really is what causes the gluon mass term to appear in one way or another. And the standard argument is that you can't have a gluon mass term because it is forbidden by the BRST symmetry of the theory. And then there are currently, I think, the most popular mechanisms to generate a gluon mass is the refined Gribov-Zwanziger scenario, where you take into account the presence of Gribov copies, and you restrict the integral over the gluon field to the first Gribov region. And this restriction is what explicitly violates BRST invariance. So one of the effects is that you get a gluon mass term. And another popular mechanism is the Schwinger mechanism. And that points to kind of a loophole in the usual argument, because you actually can have a gluon mass term and preserve BRST symmetry in the form of the Slavov-Taylor identity if you happen to have some poles in the longitudinal parts of the vertex functions. So that has to be generated in a non-perturbative way. So these are the, let's say, nowadays standard mechanisms. And we would like to propose a new, quite simple mechanism, which works by the dynamical breaking of BRST symmetry. And well, here's our mechanism. So I start with the effective action. Actually, this the effective Lagrangian. So you have a space-time integral over this. Everything is in Euclidean space-time. So this is part of the classical action. And then this is a quantum correction, the one that we will consider. Of course, there are many, many more, but this is one of the terms, and it is the one that, the simplest one that gives a contribution to the gluon mass, as we shall see. So this is, and a part, of course, you have gauge fixing and all the other quantum corrections. So here I've written down for completeness the definition of the field strength tensor and the covariant derivative of the field strength tensor, which is what appears here. So I will focus in particular on the following terms. From the classical term, this one, I take the contribution quadratic in the gluon field. And also from the quantum correction, I will take the quadratic term, which comes from isolating here this contribution, but the partial derivative, and from the field strength tensor also this contribution here. And the other term, which will be the most important one, as we shall see on the next slide, is the term where I take this contribution to the covariant derivative of the field strength tensor in both these terms. So without expanding here the field strength tensor, we have this contribution to the effective action. And there's a prefactor ZF that in principle can be calculated. So now if I focus on SU3 for concreteness, then I will suppose, and there's many indications for this, the existence of gluon condensate, and it has to be of this form if we want to maintain global color symmetry. And the F squared here is just a constant that has to be determined. And so if you suppose this, and then you go back to the last term on the previous slide that I emphasized, and you make this very brief calculation. I've tried to make it a bit easier with the colors here. So first of all, you have this contribution, and then the contribution to this term from the condensate is the one I wrote here. Just replace F squared by the vacuum expectation value. You get this here, and then you just use the usual identity for the structure constants of SU3, and then you get a delta, a Kronecker delta from this, and you just get this term. And this is, well, merely a mass term for the gluon field of this form, where we identify the mass squared with these quantities. So this is the basic mechanism, which is, I hope, quite simple to see. And now we also want to obtain, of course, a numerical value for that. And I will be a bit quick here, not to take too long with my talk. So we have to determine this, this F squared. Actually, we will determine the combination G squared F squared and this constant ZF. And to do that, we calculate the effective potential for the field strength tensor. So here are some details. Never mind for the moment. So we used the functional renormalization group, and this is our result for the effective potential. So this is basically the square of the field strength tensor times G squared in a certain direction in the field space. And well, there's a non-trivial minimum that we find at about 1 GeV to the fourth. And now, and that is actually for G squared times this constant F squared. And the other thing we need is this constant ZF. And then we use that the term I was considering in the effective action actually also gives a contribution to the gluon propagator. So here's a little calculation that shows you that it gives a p to the momentum to the fourth contribution to the inverse propagator, to the gluon propagator. And since we know the propagator from lattice simulation, and also we use the results of the functional renormalization group here, then we can fit this parameter to the form of the inverse propagator in the infrared, and we get an estimation, which is this one. And so that leads us to our result. So if we put in just these values that we find, we get this numerical result for the gluon mass parameter. It's a little less than what you would usually expect, but it's certainly in the right ballpark. So actually, it's not too much of a surprise that it comes out a bit small or a bit off, because there are a lot of approximations and assumptions still involved in the calculation that we want to make better with over time. Particularly the determination of this constant ZF is not too precise at the moment. But so you should take this value just as a first estimate. But what I want to emphasize that the mechanism that we propose is quite robust. because it is based on two things. There's this radiative correction term in the effective action, and there is it is a gauge invariant term, and there's absolutely no reason why it shouldn't be there. And in fact, we have seen that there's a contribution to the gluon propagator, and that has definitely been seen. So the term is there. And we also know that there is a gluon condensate, so that makes the mechanism quite solid. So it should be there. It should contribute to a gluon mass parameter. It may not be the only contribution, though. And we have already seen there are some other condensates with higher powers of the field strength tensor, and that should also contribute to this mass parameter. We don't know at present how much. And there are, of course, the other mechanisms that I mentioned earlier that may also contribute to this parameter. And well, there is still some work to do on this estimate for the number. And well, I think there should be some interest in this calculation. It should be relevant for finer temperature calculations and even for the Hilbert space construction, which is one of the things that is being discussed. So that's all I wanted to tell you for now. Thank you very much for listening, and I'm taking your questions.
Thank you very much. Thank you very much, Axel. So is there any question? Okay, Axel, can you hear us?
Yes, I hear you well.
We have a question from Genaro.
Okay, go ahead, Genaro.
It's just regarding just the last point that you have in your conclusions.
Yeah.
Control, or you could control the higher powers contributions. You have also it's not a perturbative calculation. So how you deal with that?
Yes, we haven't done anything on this. I mean, there are some candidates we have for these other condensates, but yeah, I still working on an alternative way to calculate that. But what we really used is the functional renormalization group. So that basically, let me see, I have not much of a detail here. So we go into a certain direction in the space of constant field strength tensors, and then we integrate this functional renormalization group equations starting from the classical potential at a high scale. So this K, which is kind of an infrared cutoff, but it starts out at high values, and then you integrate the potential down up to 0 in principle, and you end up with the true effective potential. So there is a functional method that works particularly well for these effective potential calculations. If that answers your questions.
Okay, so any other question or online, but on Zoom? I don't know if there's someone willing to ask a question on Zoom. Okay, it doesn't seem to be the case. Okay, so we thank again, Axel. Thank you very much, Axel.
Yeah, thank you. See you soon, I hope.
And okay, so now we proceed with the last presentation of the session by Livio Bianchi. So just take 1 minute to introduce him. He's a faculty from the Istituto Nazionale di Fisica Nucleare at Torino. And he was the analyzer of a pretty famous paper from the ALICE collaboration on the strength enhancement in small collision systems that was published like 5 years ago. And that without being exaggerated, I can tell that this paper really paved the way for many other analyses, only in ALICE, general at the LHC, to exploit the physics of small systems. So let's listen him. And okay.
Thank you very much. Thank you very much, Lizardo. It's a real pleasure being here in this wonderful city. So thank you very much, the organizer, for inviting me in this wonderful warm winter that in Europe we would call spring, probably. Actually, in South Europe, in North Europe, you would call, I don't know, Martian weather. So yes, so thank you very much also for introducing so well the concept that I'm dealing with. Basically, it's a big topic that I will try to cover in not large amount of time, also for the sake of your lunch. But it has large implications in many fields at the LHC, I would say, and even in general for high energy physics. So the title is QGP in Small Systems. And since I think that in the audience, many of you probably are not very much familiar with the topic, I will start introducing it from the basics, basically treating QGP, which stays for quark gluon plasma, so a plasma done with quarks and gluons, starting from the system that we were expecting to observe QGP at the beginning, which is the collision of heavy ions. And I mean, experimental efforts have been done since the beginning in heavy ion collisions, as we know that heavy ion large colliding systems, which means basically heavy ion collisions at ultra relativistic energies, lead to huge number of partonic collisions inside one of the nuclei collision, which are softening through the time of the evolution, and this leads to collective partonic motion, and this can be treated with the hydrodynamic approach. At the same time, you produce so many particles that in general, a statistical approach to particle production can be adopted. I will talk a little bit about this. This is, let's say, another important way of simplifying the theory in predicting how many particles you can expect from a collision of heavy ions. And this, in case of QGP formation, has some effects, let's say. And then you have a big system, which is of the order of hundreds of Fermi, of dense partonic medium that you can use with other probes to test for energy loss, partonic energy loss, quarkonia melting, and so on. So this is in general what we are expecting from heavy ion collisions, what we observed in heavy ion collisions. I will go through that in detail, as opposed to what we were calling elementary collisions. I know we were naive, but in general, the idea in proton-proton collisions, or even in E plus, E minus, if you want, is that you don't have this transition into a plasma of quarks and gluon. You start with the hard scatterings, and then you end up with an hadron gas, which evolves and gives your observable in your final state. Now, with the time, not really at LHC, even before that, I think this is stuck. Okay, cool. That's fine. Okay. Thank you. So actually, proton-proton collisions are not as easy as we were expecting, okay? In the time, we realized that, first of all, as we were expecting, that early times are dominated by hard jet production. This is well known. But then, especially at the LHC, you have presence of several partonic interactions, which set a semi-hard scale to your calculations that we will call MPI, multi-partonic interactions. Then on top of this, also coming from this, you have what we call underlying event, which sets your soft scale, and where you could, in principle, develop something like a quark gluon plasma. And so you have to describe hadronization through effective description of QCD potential, as in the string fragmentation approach, as for example in PITIA. But then you can have a crosstalk between these scales, the underlying event scale, and the hard part, which further complicates all the stuff. And I will go through this, but just to introduce the matter, the interesting question now is, okay, as proton-proton collisions are not that easy as we were expecting, isn't it that heavy ion collisions are just very large proton-proton collisions with large number of multipartonic interaction? Or do we expect, or we do observe something more? I mean, the fact that proton-proton in certain conditions are not exactly just a superposition of elementary collisions, but as in heavy ions, they developed something like what I reported on right. Or on the other side, isn't it that in heavy ion collisions, actually, we don't produce a plasma core congruence. It's just something that is reminiscent of what we have in proton-proton collisions with no need of establishing if we have collectivity or, let's say, thermalization in the final system. Now, I would like to start from saying the letter no, basically. So I will start from this assumption, which for some people is an assumption, but for the very large majority of people is exactly the interpretation. We had two announcements of discovery of QGP, and I mean, normally two is better than one. But also the fact that we had two announcements means that in general, you don't have smoking guns for the let's say, the discovery of a so complicated state of matter of quark-gluon plasma, but you have to put together several observable, and all together they line up to demonstrate that you produce a quark-gluon plasma. And in general, I will be talking quite extensively about collectivity. So, as I said, the fact that you have a so large medium with partonic degrees of freedom, this can lead to let's say, correlation in momentum, and this is in contrast with random thermal motion. And this develops radial and anisotropic flow, which can be modeled by hydro. You can have differences in the hydrochemistry, which means how many particles of each species you produce. And this is actually the result that Lizardo was introducing and that I will be talking about. If you have this large system, you can have partonic energy loss, so leading to what we call jet quenching, and this effect can be exploited for measuring the physical properties, as for example the density of the system, and you can have such things as quarkonium suppression due to the biscreening of the color inside the system. And so with this, you can, for example, measure the temperature of the system that you produce. So just to say with this, that you have to put together all these observables to be sure that you are actually looking into something which is just not a superposition of elementary collisions, okay? So I will try to go through all this, starting from what we observe in heavy ion collisions, and then showing what we observe in proton-proton collisions, trying to advocate on whether this is similar or not to when we produce a quark-gluon plasma. So let's start from collectivity. So concerning collectivity, you have to use models to understand what comes out, which are basically of the kind of hydrodynamic models. So in principle, in the hydro picture, you can expect that so strongly interacting medium at the partonic level can develop radial flow, which is important when the collisions of the two nuclei are head-on, because in that case, you have a large gradient pressure, and this at the partonic level. And so you have a common expansion velocity of the partons, which can translate into spectral shape modification. And this is shown, for example, here from the ALICE experiment in heavy ion collisions for different particles. You can see that when you are in blue here, you have, let's say, non-very central collisions, so peripheral collisions, where you expect that the radial flow is less important. And when you are in red, you are approaching the very central collisions. And you can see that actually the peak of this PT distribution is shifting on the right, which means basically that particles get this flow hit in the medium, and the PT spectrum gets harder. And you can quantify this by looking at the average PT that indeed enhances as a function of the centrality of the collision, or if you want, as a function of the multiplicity which comes from the collision, which is proportional to the centrality in heavy ion collisions. Okay. At the same time, one other observable that we'll be using is the so-called baryon over meson anomaly, which is actually not really a baryon over meson, but which is a high mass over low mass particle anomaly, which is this plot as a function of PT of the number of lambdas, for example, divided by number of K0 shorts, which shows this bump at intermediate PT, which then goes down, which comes from a hit that baryons or better higher masses have from the radial flow, which mesons have less. And indeed, you can see that in central collisions, you have this large bump, which is very well described by hydro at low PT, and which models like, for example, EPOS, which implements a quark-gluon plasma phase on top of many other things, can describe all over the place here. Okay, so just to keep in mind, in heavy ion collisions, we can observe radial flow, and this radial flow is observed through these observables. Okay, sorry for the repetition. And then you can have anisotropic flow, because when you don't have head-on collisions, but you have semi-peripheral collisions, for example, the two heavy ions cross this way, and the matter that you produce is not isotropic in space, and this can translate in an anisotropy in the momentum distribution. And this anisotropy can be quantified by the Fourier transform of this distribution, and with the Fourier coefficients Vn, which are V2, V3, V4, which basically tell you how much non-isotropic is the distribution of the PT of the momentum across, let's say, the phi coordinates. Okay, and indeed we observe in heavy ion collisions in all experiments from RIG to LHC non-zero Vn. So V2, for example, here is V3, and also the isotropy in the momentum distribution that you observe. Okay, so this can be very well described by hydrodynamic models, and so this is one of the largest supporters for this kind of models in the description of what happens in heavy ion collisions. Not only this, but if you do the V2 for identified particles, you can actually see some hierarchy that's a very fine hierarchy. For example, at low PT, here you can see that higher mass states, for example, protons, have lower V2 with respect to pions, and this is expected as an interplay between radial and anisotropic flow. So this is a very detailed thing that can be described by hydro, at least at the 10% level, which is okay, let's say. And then at higher PT, you have baryon meson grouping, as in this case, coalescence starts to be the main production mechanism. So you can see that, for example, the phi meson, which has a mass which is similar to the proton one, follows the proton one here, and then it switches line to the mesons at intermediate to high PT. So indeed, analyzing identified particles, we are really able to nail down all those tiny details that hydro can explain very well. So this is collectivity in large systems. Then we can go to small systems and see what comes out. First, spectra. As I said, modified spectra as a function of centrality or multiplicity show you that the presence of radial flow. Then you go to proton-proton interactions, and you look, for example, the spectra of the protons. From low multiplicity, here centrality, we cannot really define centrality in proton-proton. We will study this as a function of the multiplicity of the collision, which is an universal, let's say, quantity which links all systems together. And if you are at low multiplicity or at high multiplicity, the spectrum is very different. Actually, from the top part, you can really appreciate, but if you do the ratio with respect to the minimum bias spectrum, you can see that actually in central collisions, you have much harder spectra than in peripheral collisions. So, of course, I mean, the first time we saw this, we said, okay, look, isn't there hydro in small systems? Of course, I mean, just observing this, it's not sufficient to conclude on this, all right? So one can quantify this, as I said, with the average PT, and we measure the average PT of protons, or these are for pions, for protons and K star, okay? That's not very important. We observe the same thing for all identified particles with different magnitudes. And you can see that indeed, as I showed you before, the average PT increases in heavy ion collisions, but it increases also in small collision systems. And for systems like proton-proton or proton-lead, it enhances in a very consistent way. So even quantitatively speaking, we see this evolution of the spectrum. So we can also study the other observable, which is the baryon over meson anomaly. This is what I showed you before in heavy ion collisions. This is, for example, lambda over K0 short in very central red and in peripheral in purple. And then you do the same in PLED and in PP for low multiplicity and high multiplicity respectively. And you can see that at least quantitatively speaking, you show the same thing. So indeed, there is a baryon over meson anomaly even in small colliding systems. But of course, the magnitude is very different in the three systems. But not be tricked by this, because the multiplicity span of these measurements is very different in the three systems. So one should analyze this as a function of the multiplicity in the collision. So what we did was basically to cut our spectra for low PT, intermediate PT, and high PT, and to check as a function of the multiplicity this time for all the colliding systems, what is this ratio lambda over K0 short? And you can see that, okay, we did it for low PT, intermediate, and high PT. And what is shown is that actually there is a continuity, especially in the peak region, which is the one that we know how to interpret, at least in heavy ion collisions, as I said. There is a continuity from very low multiplicity to the very highest multiplicity that is probed at the LHC. Note that here we are talking about like two particles, charged particles produced at mid rapidity, 1 unit of rapidity. And here we are talking about 2000 particles. Okay, so there is a huge range in multiplicity, which is very well covered by this observable in a very consistent way all along. So, of course, this raised the question in us, okay, but so is the mechanism which is underlying this evolution with PT of the lambda over K0 short ratio the same in small colliding system as in large colliding system? Is hydro at play in PP? Let's stay like that for a minute. Because this triggered many other questions. Okay, people were saying, okay, it's impossible. I mean, hydro needs large systems to be developed, okay? So another thing that we are actually trying to explore is to which extent we observe these things in the underlying event in proton-proton collisions and in the jet in proton-proton collisions, because we know, as we said at the beginning, that proton-proton interactions are not that easy. I mean, you can try to simplify it. It's not simple at all, but at least what we can do. The picture with back-to-back jets together with the underlying event. Okay? It's very easy description, let's say, but still, this implies that, of course, you cannot imagine to have QGP-like phenomena in the jets, as this is the perturbative part of in the collision. So the objects that are created there tend to escape your system, while you can expect to have something in the underlying event. So you have to try to, from the experimental point of view, define your jet region, and you can do it in many ways. Well, okay, you have the definition of jet, so the anti-KT algorithm, and so you can exploit the jet region. I mean, you can check for the jet region in the idea that all collisions present a back-to-back jet, while you can have 3, 4 jets, but these are very much depleted in terms of frequency at the LHC, even at the LHC, so also more importantly at RIC, for example. So you can define the jet cone as some cone of a given radius near to the jet axis, and then a perpendicular cone. So you can measure, for example, strange particle production, lambda and K0 short, in the perpendicular cone, in the jet cone, and then subtract what you expect from the perpendicular cone in the jet cone, and measure what is the lambda over K0 short ratio in the jet and outside the jet, which you would imagine that it's dominated by the underlying event. Or if you need more statistics and you don't want to be so sophisticated, you can use the proxy for a jet, which is the highest PT track in a collision. It has to have at least 4 or 5 GeV over C. So it's a very rough definition of jet, I know. But this allows you to define also transverse, underlying event dominated, toward and backward recoiling jet regions. And given that you lower the PT threshold for your jet here, at least you have to have 10 GeV, which is already quite low in terms of jet energy. Here you can save a lot of statistics, and so you can make studies as a function of the multiplicity that I showed you have very interesting implications. So let's start from our jet algorithm results. These are the spectra for lambda K0 short. Actually, this is for V0s, but it's for lambdas. Okay, I put the one of lambdas in the jets in red and in the perpendicular plane, I mean, the underlying event in blue. And you can see that we have indeed this large difference in terms of hardness of the spectrum. So in the jet, the spectrum of lambdas is harder, in the underlying event is softer. And you can tell me, okay, this was expected. You have a boosted environment in the jet, you can expect lambda to be higher in PT. Fine. But then you do the lambda over K0 short ratio, as we were showing before. And what you can see is that actually in the underlying event, which is this blue points here, you have this evolution that we were showing before in proton-proton collisions, okay? While in the jet region, you have something which is very flat. So this baryon over Mason anomaly is indeed observed in the underlying event and not in the jet. So enforcing our idea that this has to come from something which has a collective motion origin and is not present in an environment which has high PT tracks springing from the jet. Okay, but as I said, this is a statistical aggregate analysis, so we have to change our definition of the jet to be able to do this as a function of the multiplicity. And we did it. And here it's what I show is the multiplicity dependence in a very high multiplicity region, very limited high multiplicity region of the spectra in the out of jet region here, softer, and in the jet region here, which is harder. So this again supports what we were showing before with the other definition of the jet. But then if one looks at the evolution of this spectra as a function of the multiplicity, naively speaking, if we have hydro, we would expect to have spectra which do not evolve in the jet, but in the underlying event, you would expect to have something that from low to high multiplicity show this huge difference in the spectral shape, while we don't observe it. So again, this will have to be finalized, also enlarging the span in multiplicity. But this is maybe the only thing in this, let's say, chapter that leads to the impression that what we observe in small systems is not exactly the same as we observe in large systems. Okay. By the way, another small point, which is not a small point, triggered by these observations that we found striking, we said, okay, but we also have lambda C. We have states which are much heavier with the charm quark, and the charm quark we could expect not to participate really to the collective motion in a QGP, even in heavy ion collisions. This is disputable at the LHC, but still, this was our first assumption. I will die with this, but no word. You can continue. So we did the lambda C over D0 ratio, which is analogous to the lambda over K0 short ratio that we were doing before. And maybe by chance, but maybe not, if you show this together with the lambda over K0 short for low and high multiplicity, matching the multiplicities of the two analyses, you show that actually these two superimpose very well. Now, I will not give interpretation here. There are some considerations that I did quite some time ago with my colleagues, but I will not go into the details of this. To me, this shows that indeed in small colliding systems, it's difficult to say that this ratio shows hydro at play at the LHC, but okay, we can, this is questionable. Then we can try to measure anisotropic flow. And this is a very, okay, as I told you, we observe as an anisotropic flow at the LHC in heavy ion collisions. But then we can do the same thing that I was showing you before as a function of the multiplicity of the collision. This is a very intricate plot. Let me drive you through this. This is the multiplicity that you produce in the collision. And you have all different systems that we exploited at the LHC. You have at very high multiplicity lead, and xenon that we had for some time at the LHC. And then you have P-lead point in red and blue point are PP points, okay? So let's try to put all together. So what we observe is actually that the V2 here on the top plot, the V2 is different from 0 also in small colliding systems. So we observe anisotropic, let's say, we observe V2 that we normally connect to anisotropic flow in small colliding systems. But if we look at the V2, this is rather different from what we observe at the same multiplicity in heavy ion collisions, which is the red point, the green point, sorry. This is actually expected because even in heavy ion collisions, if you compare lead, and xenon, which are the green and the black points, they are not green. Because one thing is that okay, the peak comes from the elliptical. Let's say it's also called the elliptical flow. It comes from the elliptical shape of the colliding system, of the producing system. So even in xenon, you don't have agreement between the two. You expect it, and actually, hydro calculation expect this very well. I mean, they show a perfect agreement at high multiplicities. So indeed, where eccentricity is important, and of course, in proton-proton interactions, you don't have eccentricity. Questionable, but okay, we can think about that. V2 is not actually joining at intermediate multiplicity. But then if we look at the next orders expansion, V3 and V4, for example, that are much less dependent on the initial state eccentricity, there is a perfect lining of the data from low multiplicity to the highest multiplicity for the two observables. And this is very nice, very interesting. And of course, theorists try to extend their models from the highest multiplicity to the lowest, hydrodynamic models from the right to the left, and for example, Pythia models for proton-proton from the left to right. So you see, this is very interesting because it's the cross point of two very different ways of looking at interactions, from collectivity to, let's say, pure QQ bar formation in proton-proton collisions. And the two, let's say, philosophies are trying to understand if they find a common ground in the intermediate multiplicity region. So, but interesting is that actually it seems from the theorists that they can apply hydrodynamic picture even in a far from equilibrium environment as in proton-proton interactions. Okay. So far, a lot to digest, but I will add something more. Do you remember that I showed you identified particle V2? And I was discussing the fact that at low PT, you expect mass ordering due to interplay of radial and isotropic flow. And at the intermediate PT, you can expect this baryon-meson shift. Well, we observe exactly the same thing in P-lead collisions here and in proton-proton collisions for all the particles we could do. So again, even this characteristic, which is very peculiar of hydrodynamics, is actually observed in small colliding systems at the LHC. Is it hydro at play? We will see. So much for collectivity. I will switch now to hydrochemistry in this, let's say, coherent review of all the observables that we have in heavy ions that we then check in proton-proton. So hydrochemistry, so the relative abundance of different hadron species coming from the interaction, comes along with one concept which is rather famous in our field, which is the concept of strangeness enhancement. Why? Well, because you produce a lot of pions, you produce a lot of UD particles, but strange particles, especially in proton-proton collisions, well, in proton-proton collisions and as in all other collisions, the strange quark is suppressed in the initial state, while you can produce it abundantly in heavy ion collisions. So this triggered a lot of works. The first one I would say is the one from Rafalski and Müller from 82. And they were expecting actually to have strangeness enhancement, so a larger production rate of strange particles in heavy ion collisions with respect to proton-proton collisions, because you have a lower Q value to produce a bare SS bar pair in a let's say in a partonic related system, with respect to producing two strange hadrons, for which the Q value is much larger, of at least 2 orders of magnitude, 1 order of magnitude, let's say. So you can expect larger production of strange particles in the presence of a quark-gluon plasma, and also because of faster equilibration in a partonic medium, because the number of interactions is much larger than through hadrons, okay? So this is the first approach. Then there is the statistical hadronization approach, which is kind of not asking for the presence of a QGP, but trying to describe the hadronizing system at the limit of the hadronization as let's say a hadron resonance gas at a given temperature, at a given potential, let's say, and then the production of the enhancement of strange is actually coming from the fact that in low colliding systems, you have what you call canonical suppression, which means that when you produce many particles, you can use the grand canonical ensemble approach, while when you go to the very low multiplicity, you have to conserve charge point-like, and so you have to restrict your phase space, and so the number of strange particles produced. Nonetheless, this is one of the most studied observables since SPS, I would say. And indeed, this is a plot from the Alice experiment, but which puts together the results from NA59, I think, and STAR, NA57, sorry, and STAR, and also Alice. And you can see that as a function of the number of participants in the collision, which is kind of connected to the centrality of the collision. So here you have central collisions, here you have peripheral collisions. With respect, when you normalize it to the rate of production of strange baryons, for example, this is the Xi baryon, with respect to what you produce in small colliding systems, so you normalize it to 1, you have an enhancement as a function of the centrality, let's say. And nice. But what was striking, and you have also for the omegas, you have for lambdas, and so on. And the higher the number of strange quarks you have in your hadron, the higher this trend is, the steeper this trend is, okay? What was striking at the beginning was to see that actually, if you look at NA57, which is at much lower center of mass energy collision, with respect to the RIC, which are the open dark point here, and with respect to Alice, which is LHC, so orders of magnitude higher in center of mass energy, you have an enhancement which is lower and lower. And in the naive picture of Rafalski and Müller, you would have expected actually the other way around. You have a system which is hotter, and so you can expect that the Q value is less important for the production of SS bar, and so you should produce even more strangeness. Yeah, right. But we soon realized that, for example, also by using the statistical hadronization model, that we were always normalizing to proton-proton or anyway the small system value, okay? But this was taken at very different central mass energies. And since the production cross-section for the Xi baryon at different energies changes very much in proton-proton collisions, then you're not observing enhancement here, you're just normalizing for the suppression that you have at low multiplicity. So what we decided to do was to plot this quantity, not normalized to the value at low multiplicity, but normalizing to the number of pions that you produce in the collisions. We gauge the production of strangeness to the production of the most common hadrons that you can produce, pions. Okay, so this is the Xi over pion, omega over pion ratio as a function of the number of participants, the, let's say, centrality, and of course, the number of participants in proton-proton interactions is 2, fine. And you can check this, and you can see that indeed there is an enhancement with respect to small colliding systems. But if you put together, for example, STAR and LHC, they end up with the exact same rate in production of strange particles in heavy ion collisions, which is remarkable and shows also that indeed there is a large difference in the production rate in small colliding systems, which can be studied. Where does this come from? Why at lower center of mass energy I produce less Xi baryon than at high end center of mass energies? This might be trivial for someone, but it turned out not to be that trivial. More in general, I was talking about hydrochemistry in general, and now focusing mainly on strangeness. But what is important to say is that actually, if you try to use your statistical hadronization model, so basically that is a model which has two parameters, basically, the temperature of hadronization, so the temperature at which you have this, this transition from your quark-gluon plasma to the hadronic phase. And then the biochemical potential, which at the LHC is, you can not use, I mean, it's one, you can avoid. So you have one free parameter. And with this one free parameter, you can describe the yield in production from the pions to the anti-helium 4 over 9 orders of magnitude in rate in a very good way. There are some hiccups here and there, but many of these hiccups are very well understood. For example, for resonances, you don't describe it because resonances are very much affected by the hadronic phase after the transition. So yeah, we report it here, but just to say, yeah, this is not compliant, but we know why, okay? So, but anyway, the statistical approach shows you that in heavy ion collisions, you are very well gauging your ability in understanding how many of all these pieces you can produce in one collision, okay? There are caveats, there are many things to say, but I will not say. Because then I want to go in small colliding systems, okay? This is actually the result that Lizardo was discussing in the introduction. So what we decided was, okay, we have this nice plot. Okay, I have 10 minutes. Thank you very much. I will ignore that. So, no, I will try to stick on time. So we have this production rate in heavy ion collisions for the different species, okay? Which you can very well fit with a statistical hadronization model. Here, 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 and here, okay? But then we want to check how this changes as a function of the multiplicity in the collision, because we know that in proton-proton interaction, minimum bias proton-proton interaction, we produce less. But is there a dependence on the multiplicity that we showed before for the V2, for example? And so across all multiplicity span, again, from 2 particles at mid-rapidity to 2,000 particles at mid-rapidity, we show the omega over pion ratio. This is omega over pion, psi over pion, phi, and blah, blah, blah. And we can see this evolution, which actually multiplicity really helps you in understanding how many of these particles are produced. Tell me the multiplicity of your collision. With this plot, I will tell you exactly how many of these particles you produced. For whatever system, you see, there is proton-proton here, proton-lead, lead-lead, and even xenon-xenon on top. No issue. You want to put here the results from Rick? You can put there. They're exactly on top of this. We tried, and it's like that. And actually, this enhancement of strangeness, you can see that for omega is very well visible here, also for Xi. If you normalize it to the value that you have in minimum bias collisions, so you renormalize it to 1, you can see that actually for omegas, the increase is the steepest. Then you have Xi's, and then you have lambdas and K0 short, which go together. So this is actually proportional to the number of strange quarks that you have in your hadron, okay? And it's not really a baryon connected effect, but it's a strangeness connected effect. Because if you try to do the lambda over K0 short ratio again, as a function of the multiplicity, this time not as a function of PT, but as a function of multiplicity. So you are integrating the full spectrum, except for this, probably this point, which is anyway not significant, you don't have evolution. So you have one strange quark, being it a meson or a baryon, you will have the same quantity. And also the proton over pion ratio does, okay, this doesn't work anymore, but no worry, I will. The proton over pion ratio remains really flat as a function of simplicity. So it's really straight. So Yeah, this was the result out on the small native planning and decreased out because they are very difficult for them to use, but then they were, and they are very intelligent also. And years they tried, and both from the point of view of simple hadronization of PTL-like, let's say, so let's call it in vacuum hadronization, they are at least qualitatively introducing different effects like rope hadronization, color reconnection, and so on. They actually, qualitatively speaking, can reproduce our data. And also models which implement core and corona, which means two different phases in the hadronization. One is the underlying event one, let's say the core one, and then the corona is the jet fragmentation. They end up in reproducing quite well our results. So this is very interesting because it shows again, as for the V2, that the two different approaches, which start from very different assumptions, can get to some extent our data, at least qualitatively speaking. And so what? Well, they are intelligent, but we are cruel as experimentalists. So we are trying to break their understanding again. So do you remember that I was talking to you about the production in jet and outside the jet, okay, for the spectra? Now we can integrate the spectra and we can calculate yields. And this is what we did. This is a preliminary result from the ALICE collaboration. It will come to publication very soon. And we did it, for example, for size on top and for K0 short on bottom. And this is basically the yield of production in blue, actually in green is in the transverse to leading. So in the underlying event dominated part on top, on green, and on red is in the jet. So it's striking here to show that as a function of multiplicity, what dominates the production of Xi baryons is actually the production in the underlying event. That is where you would expect strange resonance from a QGP, okay? So this is clear across multiplicities and also for K0 short. But remind, this is the production yield. It's not the ratio to pions. It's not the ratio to any other particle. So what we wanted to do is the ratio Xi over K0 short, because Xi has two strange quarks, K0 short 1. So we would expect an enhancement. Fine, we did it. Again, for the green points and for the red points as a function of the multiplicity. Now, this is not fantastic, I would say, because okay, we have large errors. We will do much better in round 3, hopefully. But you see, they increase for sure in the green point increase, and this is somehow expected. If you have strange resonance, you should have this increase as a function of the multiplicity. Fine. But then the red points, okay, we don't know. They increase, they do not increase. We still don't know. We have to study much more. But you remember when I was showing you, now I cannot go back. Oh, yes, I can go back. When I was showing you these models which incorporate some core and corona. So let's say QGP dominated production and then jet dominated production. What you can see is that their reproduction of the omega over pi ratio, which is the red one, okay, which is very good. It's actually coming from a superposition of the light blue on top and of the dark blue on bottom, which are two trends that as a function of multiplicity are completely flat. So this approach is saying in a QGP, you produce so many particles, which do not depend on multiplicity. In the jet, you produce so many particles which do not depend on multiplicity. And then the fact that across multiplicity, you are actually weighting differently the importance of the jet part with respect to underlying event tells you that the omega is rising. So this is why we did this in jet and outside jet. And now it's no way that this will work, I guess. It's working. So in that naive, if you want, picture, we were expecting that in the jet and outside the jet, these two trends were completely flat, but they're not. At least they're not in the transverse region. So, question mark there. I don't know if I have to stop or if I can comment what is not visible. I can go on if you want, if you wish. But this is actually not very important why they decide. I can just say that I was talking about strangeness. Oh, this is more important, yeah. But anyway, I was talking about strangeness, but we observe actually this evolution as a function of the multiplicity, not only for strange hadrons, but also for nuclei production. At the LHC, we can produce a lot of nuclei in our collisions. We can measure them. I showed you the description of the statistical hadronization model for anti-helium-4, for example. And we can study this, the production yield, as a function of the multiplicity. And then I will let you the stage, of course. And we can see this evolution, which is connecting very low to very high multiplicity in a very good way. Also, because now there was the transition to hard probes that I have like less than 5 minutes to talk about. Cool. Okay, thank you very much. So yes, you see that also for nuclei, for deuterium on left, the deuteron over proton, this evolves as a function of multiplicity, but also the helium-3 and the triton and so on. So will be interesting to understand why there is this evolution. The statistical hadronization model tells you that you have actually canonical suppression for the biochemical potential, but that's hard probes. I will try to be quick on this. So, as I told you, we have to put together all the pieces of the puzzle, and hard probes are an important ingredient in all this. So, as I said, you produce this. Yes. Sorry. Of course, yes, please. So when you produce this big system, which is like 100 Fermi in radius, more or less, which is in thermal equilibrium, collectively expanding, and so on. If you produce back-to-back jets, thank you very much. If you do produce back-to-back jets, but this production actually happens at the boundary of your phase, you can expect that one of the two jets will cross this very easily and will go out and will give you a nice jet that you can reconstruct. While the back-to-back one will have to cross a colored medium. I mean, so colored quarks, of course, and gluons coming in the jet. They will interact a lot into this environment, and this will lead to a very much depleted back jet in your observation. And this actually was first observed by the STAR experiment at RIC, where you see that the triggering jet is the one at 0 in phi radians, okay? Then you look at back-to-back, and if you look at proton-proton or deuterium-gold collisions, you have the back-to-back jet. It's slightly spread around because it's not the triggering one, but still it's present. While the blue point in gold-gold central, they're completely depleted. So you lose the back-to-back, the back jet because of the colored medium. And at the LHC, we are studying this in very much detail. This is a result from CMS, I think, yeah, but also Atlas did a lot of stuff on this. You can see that in proton-proton, top left, you have that the asymmetry in the asymmetry in the PT that you reconstruct for the first and the second jet that you expect to be 0 in E plus E minus is in proton-proton very well reproduced, for example, by PITIA. But then if we go to very central collisions, this asymmetry goes up to values which are like 0.3, which means a lot of energy has been wasted inside your medium, okay? And then you can have the RAA to quantify this at high PT. The RAA is an important variable, which is basically the ratio of the production of a given particle in AA with respect to the rate that you have in proton-proton collisions, multiplied by a factor which tells you how many binary collisions you had at that centrality, okay? And you can do it for charged particles, for pions, kaons, and protons, and also for d mesons, which gauge how much energy loss you can have in your system. Or for quarkonia, it's actually the same observable, which leads to completely different interpretation, because in a colored medium, QQ bar heavy ion pairs, which are very near in phase space, actually can be screened by screening, and so they can melt. Okay, so this is another important observables, which actually led to the first announcement of QGP discovery at the SPS. So to go to, then I will be killed, but to go to smaller and smaller system, we can stay on heavy ions. and we can go to very peripheral collisions, more peripheral, even more peripheral in different experiments. And even when we go to the number of participants, which is like 5 in heavy ion collisions, which means that these two heavy ions basically didn't see each other almost, you can still measure an RAA which is different from 0, which means you have depletion in the RAA, which means you not being at 1, you have some hot nuclear matter things happening in your system, okay? And then you can go in small colliding system, for example, PLAD in Alice, and you say, okay, if I had a part which is 5 in heavy ions, I can expect that in minimum bias proton LAD, which have much larger end part, I should observe something. And you actually don't observe anything. This QPLAD, which is something like the RAA, let's say, the RPLAD, is actually very well to 1 for all the different experiments at the LHC. So this triggered the puzzle, why we don't observe jet quenching at the LHC in small colliding system. But this is an ill-posed problem, because in Alice we studied this RAA in heavy ion collisions in very granular way in different centrality regions. And we observed that actually when you go from very central, you have a very small RAA, which means that a lot happens, okay? Then it increasing towards 1, but at some point, it will go again down to very small values. And this is actually only coming from selection biases. So this is just to say, we were actually triggered by this and questioning this, but we can say that we don't observe jet quenching in peripheral collisions in heavy ion at the LHC, so we cannot expect to have it in small colliding systems. Quarkonia, very, very quickly, in proton-lead collisions, we don't observe any anomalous J-psi suppression, but we observe psi-2F suppression with respect to the J-psi. This is shown for Alice and for CMS. You can observe an RAA which is lower, an RPLAD which is lower for the psi-2S with respect to the J-psi, which is consistent with the idea that at the temperature that you have in the system, in the PLAD system, you are actually melting the psi-2S, where is it? Which is happening at lower temperature, you see there, but you're still not melting the J-psi. So, okay, you produce a system which have lower temperature, fine, maybe. But then very puzzling is this result from CMS, which is the upsilon2s over upsilon1s, so which gauges the temperature at which the upsilon2s should melt. And you see that the upsilon2s should melt at a temperature which is the same of the J-psi, because that's how much it is linked, let's say. And you can observe as a functional multiplicity this depletion which goes to heavy ions from small systems, which is very tricky to be understood. So I will not go through all my conclusions. I just want to say that I hope I convinced you that I mean, the studies of QGP in small colliding systems are very interesting, both for our ability of describing heavy ion collisions themselves, but also for the study of hadronization, which actually received a very important boost from these studies. Sorry, thank you very much.
Okay, thank you for this summary of activity. We have questions or reports, but very interesting subject. Professor Ayala.
Thank you very much for this review, very comprehensive. I had a question regarding the last topic that touched upon the RAA. So yes, that one. So you've done differential measurements as far as I understand, but it may be a very naive question, but you see, typically what you measure when you measure RAA is in the denominator, you have like minimum bias, PP, so to speak. So have you tried selecting the events to compute the denominator, say, for instance, in classes of multiplicity or something, to see how the RAA behaves, to see if there is this collectivity in small systems, maybe the RAA may show some, discrepancies with respect to minimum bias, which and these kind of, other kind of stuff.
Yes, this is a very good question. And actually, it's one of the first things that happened to our mind. Because again, I showed that there is an evolution with multiplicity of the spectra. So why not using as a reference something as a function of the multiplicity? So for the RAA, it's a very difficult thing to do, because the RAA inherently has inside this TAA, which is the nuclear overlap function, that it works if you're taking the minimum bias spectrum. Otherwise, it's very difficult to do. What we did was to do the ratio spectrum, which is, something very similar, if you want. And what we are currently working on is the ratio spectra at similar multiplicities for different colliding systems. It goes along with what I was showing before. It's not exactly that. We are actually working on a fair and detailed comparison like this one. But let's say, to partly answer your question, it goes like showing the average PT as a function of the multiplicity for the different colliding systems. And this is very interesting, because I pinpointed to you many of the similarities that we have across different systems. I didn't talk too much about the differences that actually we have, because you can say, okay, you have this evolution, which is the same as a function of multiplicity, qualitatively speaking. But then when we look at the average PT of the spectrum, there is a clear jump between PP, PLED, and LED-LED. So my interpretation, before answering your question with our work, that will lead to something for sure, is that there is still something very different in heavy ion collisions, okay? Hot nuclear matter effects cannot be completely denied in their difference in heavy ion collisions with respect to proton-proton collisions. Now, the effect that they have on yields is basically zero, okay? The effect that they have in spectral shape is sizable, and thorough, let's say, study of the spectral shape as a function of the multiplicity is we are doing it. Just if I still have time for another small point. In the past, something that I don't show because people get angry with that, so I don't show it, but is a comprehensive study with a simplified hydro picture, which is the blast wave model, which tries to, let's say, model the spectra for all colliding systems. And what is exactly in that case, this model has as an input the beta of the expansion, okay, and the temperature of the hadronization. And what we showed in the past is that for PP and PLED, there is a very good agreement of these parameters as a function of whatever you want. But in heavy ions, you have a step. So it's very difficult to say that spectra are the same as same multiplicity, which goes along with your request. It would be great to have an RAA with different multiplicities. Difficult right now, but we will do something for that.
Okay, so we have a question from Zoom. It's Jorge. Can you hear us?
Yeah, can you hear me?
Yes, please.
Yeah, I think, well, first, thank you for your talk. It was really nice. And second, I think I have a kind of naive questions, but at the beginning of your talk, you said that we cannot really define a centrality for the proton-proton collisions. But I don't know if there are sizable particles. I don't know if such a crazy idea that maybe thinking not central collision for the protons, or I don't know why you can't consider that.
Sorry, can you repeat the question? Sorry, it was a bit chunky, so can you repeat?
Like why we cannot able to talk about centrality in proton-proton collisions if there are sizable particles?
Yeah, okay. Yes, thanks for this question. So what I was showing to you is always as a function of multiplicity, which is the easiest, if you want, observable that we have as experimentalists, as you measure the number of particles, and that's it. Well, it's not that easy, but okay, fine. It's true that the best observable from the theoretical point of view would be energy density, because we expect to have all these effects be scaling as the energy density goes. So we tried in the past to use as scaling variables energy densities also in small colliding systems. Then you end up by being very much model dependent, as if you want to calculate energy density coming from multiplicity, you need to define volumes, and volumes are very much model dependent. So yes, one can try. What I can ensure in this case is that one relies very much on models, and okay, we want it to be less model dependent as possible. But yeah, that's actually a very fair point. Yeah.
Okay, thank you.
Thanks to you.
Finally, here we have.
Yeah, thank you for a nice talk. I was wondering, people use these holographic approaches to try to describe the plasma. How do they do when they try to generalize it both to very small systems and so on? Is there any,
Yeah, very difficult question. So yes, the holographic approach is one of the approaches that has been used to try to interpret basically the eta over S, so the shear viscosity that we observe in heavy ion collisions. And there is actually comprehensive studies on different observables in order to put everything together, also from the ADS-CFT approach. This is true. In small colliding system, I think nobody did much. Because, well, in small colliding systems, still theorists are trying to understand how much hydro can be applied. So even basic quantities as eta over S, which are those that ADS-CFT can predict actually quite well in heavy ion collisions, honestly speaking, they're still not at our hand. So I think there is still some maquillage to be done at the phenomenological level to try to understand if we can apply hydro in small colliding systems. And if we can extract parameters in a Bayesian way as it's done in heavy ion collisions. That is our dream, let's say. And once that's done, we can compare to ADS-CFT, I think. But then I'm not a theorist, so but as far as I understand, this should be the way to proceed. But yeah, it would be very interesting.
Okay, well, we thank again Livio for this short talk. And well, we have to be here to be back within 1 hour at most. Thank you. Have a nice lunch. Okay, hello. Hope you had a nice and fast lunch. So we will resume now with the cosmic ray session with two talks. The first talk is from David Alvarez Castillo that will be talking about the extremely distributed observatory. So, okay, David, go on.
Good evening, everybody. I would like to really thank the organizers for this opportunity to present this work here. For me, it's a great pleasure and an honor to be here in this community because I've been for several years living outside Mexico, so like abroad. So for me, as I said, this is a great pleasure. And this time I'm going to talk about this collaboration that is called the Cosmic Ray Observatory of Credo. And I will shout out some of the goals and expectations. So first of all, I will say something about the detections of cosmic rays and what is particularly interesting in Credo. I will also invite everybody to participate because this collaboration is open to anyone. And then I will briefly outline a few of the theoretical scenarios that could produce the so-called high-energy cosmic ray ensembles. Such ensembles could be probes of fundamental physics, as I will discuss. And then there's an application that is also very valuable, that is the signatures of cosmic ray signatures as possible precursors of earthquakes. And finally, I will conclude. Okay, so as we have heard today in the morning or during the sessions, it's very interesting to look at the very high energies because at the beginning of the universe, the forces could be unified or there could have been produced some dark matter early candidates that could explain all those cosmological phenomena. And some of the candidates are like the grand unified theories. In the morning, we were listening to that. And also the possibility of discovering or something like quantum gravity if it exists. And typical scales of energies go from orders of hundreds of giga electron volts to even 10 to 19 giga electron volts, which is basically the Planck scale that is the most extreme energies that probably exist in the universe. On the other hand, so there's ideas that dark matter could be particles, and here is just a plot that summarizes all these possibilities. For instance, some of the popular ones are the axioms that could explain the strong QCD problem, for instance, or some others that are related to pre-inflationary epochs. There are also WIMPs and different ideas where the masses are higher, of the order of giga electron volts, of the electron volts, and there are also possibilities of the existence of the so-called primordial black holes. So these are just ideas that come from cosmology to describe the observations. But now we are in the multi-messenger era. So as you remember, we are in the days of the multi-messenger era, where we have already detected a few events, not only in electromagnetic radiation, but also in gravitational waves. And I think the cosmic rays also play a role. So it's another channel, another way to study the universe. And very interesting is that there have been detections of very energetic cosmic rays, the so-called ultra high energy cosmic rays, which have energies above 10 to 18 electron volts. That's of the order of exa electron volts. And this is the typical flux. So lower energies, most of the phenomena are produced by astrophysics scenarios or astrophysical processes, like for instance, particles from the sun or from supernova explosions and pulsars. Some others come from active galactic nuclei. and here is where the very energetic particles are detected. And one of the, the situation is that the flux is very low. So this is part of the challenges to try to understand what can be producing these high energy particles. As I said, the flux decreases very rapidly. It's very low. We want to know where they come from, how do they propagate, and we would like to collect more of these ultra high energy photons. And as I will discuss later, there are also applications to prove fundamental physics. So nowadays we have a few observatories that look for this kind of showers where a primary particle comes and then interacts with the atmosphere and then produces a shower. Basically, it's just the case of many different species of particles. And what is depicted here is the Piroyer Observatory that is located in Argentina. And it consists of a few water Cherenkov detectors and also fluorescence telescopes that detect the light that is produced by these decays. And so they try to characterize this kind of showers, and with this data they can usually reconstruct the primary particle and try to figure out where it comes from. So there are two of these kind of observatories at the moment. One in the north, that is a telescope array in the USA. It covers an area of 680 kilometers squared. And the counterpart is the Piroyer, as I mentioned, which is an area of 3,000 kilometers more or less, and tries to answer these questions that I mentioned. But now we want to consider other possibilities, that the shower is not just a localized shower that is produced by us primary cosmic rays, but it could be produced by something else, and that could interact and create several of these showers. The difference here is that usually the shower here is produced with interactions with the atmosphere and produce a signature here that is localized. But in the case of something that can interact outside the Earth, then there could be different of these showers, and then there's a chance to try to understand if these detections have some kind of correlation. So, for instance, we can try to look for clustering in a space where we see geometrically how they are localized, or just clustering in time, where there could be some correlations depending on the times of arrival of these multiple showers. Thank you. So as I was mentioning, this is the typical spectrum. This is Credo tries to look at mostly at the higher energies. It's expecting to look at the higher energies. And the ideas, the basic idea, or the first trial, or the first attempt to try to discover these showers that could cover extended areas like of the orders of hundreds of kilometers, is to try to invite people to use smartphones to detect the different signatures. And for this, the group in Krakow has developed some app that at the moment works rather well in Android. And with this, we aim at trying to figure out if it is possible to detect these extended signatures. So at the moment, we have the support from many countries and many institutions who are doing this for the sake of not only scientific goals, but also educational. And we believe that with this kind, if we have under control this kind of showers and understand the nature, and if we find the proper correlations, we'll be able to study different phenomena that could extend from distances of 10 to the minus 35 meters that could correspond to any space-time structure deviation from being soft or kind of structural, up to very energetic, to very high distances that will correspond to to different astrophysical phenomenon or even at cosmological scale, like here dark matter or so. So in this way, one of the messages of this talk is to try to, I mean, we would like to invite anybody to support, especially students, to help us, at least for the moment, with the smartphones, to develop this project and to try to study many different aspects. I will, as I say, I will elaborate a bit more in details in a moment. But basically, Credo tries to explore all this from cosmology, from geology, from high technology and different types of infrastructures, or even biology or ecological because of the environment on the Earth. So at the moment we have, as I said, we have support. This is probably the latest numbers. We have 48 institutions with about 20 countries all over the world in 5 continents, and we have groups of users of the order of 15,000 and many teams. Sometimes they team up to study together, like for instance in a university or a school, and this corresponds to many smartphones. So the smartphone collects the data, and the data is sent to Poland and is processed there is being through supercomputers that try to figure out what is being detected. So basically anyone as a person or as an institution is welcome to join. There's this memorandum of understanding, and it's very simple, just to agree to give support to the project, and in this way whoever is member can be in contact and also participate in publications or in discussions and so on. So these are just statistics. So once the data is collected, the smartphones, what they see is this kind of traces. So we need to figure out if they are like muons or what kind of earth showers are there, or if they are high energetic cosmic rays. So there's already some basic studies that serves as a guidance, and with the machine learning in these supercomputers, all these events try to be classified. Of course, there's an imprint of time and position, and this is how it's been reconstructed, all these showers. At the moment, we have already been collecting data, so there's still, we need a lot of manpower to deal with this, at least at this level of the smartphones. So now we'll discuss a bit of the physics. So for instance, if we consider a particle that has, for instance, been produced in the early universe, it can interact at some point. It could be, for instance, dark matter or a monopole. And then it's expected that it will decay into a very high energy photon, and this photon it can create these ensembles of showers. And this is why if something like this happens, we expect to have detectors everywhere to try to reconstruct it. So as I mentioned, there are localized there could be localized showers, or there could be showers that are more extended. So depending on that, it's necessary to do simulations to try to figure out what are the differences and so on. Of course, there has been some motivation in the past. There are a few papers where people have reported something similar to extended showers. For instance, in this one, where this happened, for instance, in 1981. And there was some number of observations. So this is probably not taken into consideration very seriously, or also in this time was in 75 also an extended detection. So this is sort of motivation. So if this really happened, we want to see if we can proceed with that. So the strategy is more or less the following. So we need theoretical scenarios. We need different considerations to start with, and then we can do simulations. And the simulation will consider the interactions with the atmosphere. There are programs dedicated to simulate the propagation of this particle from the ground. Then we have for the detector response. So we need also to simulate And then of course we need to gather data. And of course this can also be done in the inverse way depending on what we collect. So there are astrophysical scenarios like acceleration of nuclei producing shock waves. There are interactions with the cosmic microwave background. There are many astrophysical objects that sometimes are difficult to find. Photons and neutrinos also could contribute. And beyond that, there are these exotic scenarios like decay or annihilation of early universe relics, particles like supermassive particles with energies of very high, like 10 to 23. The decay of quarks and leptons, probably from some unified theories and so on. And then we need to figure out what is the high energy flux. I think this doesn't work anymore, but let's try to go on. Okay, here is some more or less recent plot that considers detections from from the two observatories that I was telling you, the OGER and the TA. And the higher the energies, the lower the flux. Thank you. So this is where we need to try to figure out how to improve, and this is very interesting because it could bring some insight of fundamental physics. For example, consider the scenario of the pre-shower. When a photon comes into the Earth, it interacts with the magnetic field of the Earth, and it could go through magnetic pair production. And as the electrons and positrons get accelerated, they could produce synchrotron radiations. And this will create the so-called pre-shower. With pre-shower, we mean a shower that is produced right outside the atmosphere of the Earth, and then can leave an imprint. Other scenarios are very energetic, like the mergers of neutron stars. For instance, here I cite some estimations of in this paper where people have thought that because of the merger there could be some sort of ejecta, and there are estimates for the energies. So we have already detected neutron star mergers both in electromagnetic and gravitational waves. So this is interesting. Another scenario that I have developed from the point of view of theory is to consider an evolution of a neutron star that basically is made of protons and neutrons, but as it evolves either by accreting matter or by losing rotational energy, it can develop the so-called quark-gluon plasma that we were discussing, so the confined matter. And if this process happens, so the star will go an evolution from one branch that is pure hadronic, made of protons and neutrons, into a hybrid star that will have a core that is made of the confined matter, quark matter. And because of that, there's an estimate of the energy that could be released. So if you want to look at the details in this article, we have modeled this scenario, which has helped us also to explain some of the orbits of binary stars that are not circular, that are eccentrical. So some of them have been discovered. So one possible explanation is this scenario that will help both for production of very high energy particles and also to explain these eccentrical orbits. Other ideas of how particles could come with such a high energy is the so-called Penrose process. So basically, Roger Penrose long ago figured out that the particles could fall into the ergosphere of a rotating black hole, and somehow one of the particles will gain energy and will be expelled. And then this process has also been considered with the inclusion of electric and magnetic fields, and apparently it could be a source of production of very high energy. As for instance, here I take one example of the particles that could be produced that could leave an imprint. We have also considered the production of showers by a very energetic particle nearby the sun. So for instance, we have just started with some models of the magnetic field of the sun, can be dipole or can be a quadrupole. And by consider that the particle a very energetic photon, and it will be split into pairs, and this pair could come and create this extended shower. So with the simulation, we have found the typical distances and the probability for the conversion, depending on the distance from the sun. For instance, here you can see how many Earth radii it's necessary for the conversion. So for instance, here we see that about 5 times the radius of the Earth, the conversion is very low, but meanwhile it stays more or less feasible under the simulation. And then we have computed the footprint, and what you see here is this kind of elongated lines that will correspond to different channels, to different possibilities, varying the latitude of the initial configuration. And this is the typical footprint that you will detect on Earth. You see that in this case, this is like the core of the footprint of about 1 kilometer. So these footprints are extended, but they have some sort of a concentrated area. We call them sort of galaxy footprints because they resemble galaxies, and they can extend for very long distances. So here I'm showing you some of the simulations that motivate us to try to understand and detect these scenarios. Another possibility is that the photons split around compact objects like a black hole or a magnetar. In this article, the authors have come with this idea and calculations of how the photons interacting with the magnetic field and with the plasma around could split. And so these are some of the configurations in this article. The idea is that there could be a competition between the photon splitting, whenever it happens, against the pair production. That will be the typical scenario that the photon produces pairs, but instead we can also have the photon splitting. So in this study, the authors have found the parameters that are where photon splitting is favored against pair production. Okay, another of the ideas is to consider that these ensembles can be produced by synchrotron radiation. So if that's the case, one can also try to find the synchrotron radiation associated. And one of the postdocs in the institute, Alexander, has done this study, and he has considered, for instance, the galactic center and a radius of 20 kiloparsecs, and has come with some numbers that could more or less give us an insight on what could be the preliminary values for these showers and the associated synchrotron radiation, because the synchrotron radiation could be like the smoking gun, or at least will support this scenario. Something that we have discussed is whether the cosmic ray showers could also, whenever they are well characterized and well understood, could lead us to or they could display some effects, for instance, of the variation of fundamental constant at the cosmological level. So there's the idea or the search for variations of the fundamental constants, like the H bar, like the alpha, like the structure constant, or even the G, or associated quantities, because all of them are somehow related. So if this happens, some of the processes that determine the characteristics of the showers, like the interactions, electromagnetic interactions, and so on, could present a deviation, and the possibility of detecting could be precisely through these cosmic rays ensembles. There's also what was discussed yesterday, the possibility of Lorentz invariant violation. So one of the motivations is that some quantum gravity approaches come with some modified dispersion relations for photons, like is this one. Here is the reference. But also we heard yesterday that even extensions of the standard model that try to understand or to explain different issues on at the level of particle physics could consider the Lorentz invariance variation. So if it exists, so it's possible that the cosmic rays ensembles will give us some insight. And now I would like to probably come to the last part of the talk, which is trying to use the cosmic rays shower to look for possible precursors of earthquakes. And you might wonder what is the connection between the earthquakes and the cosmic rays. So the basic hypothesis is that the steady flux of cosmic rays, as well as a localized air shower leading to some footprint, might be affected before an earthquake occurrence, because the dynamics of the Earth's magnetosphere. So we really want to explore this possibility. We are just started, but in this work, we have looked at the correlations between different data from earthquakes and also from the Auger Observatory. The motivations, as I said, we know that there are very devastating earthquakes in certain parts of the world. Mexico is one of them. And there have been some very preliminary works where people have claimed that there could be some precursors. So in this article, the authors have considered details on the geomagnetic disturbances of the Earth before the earthquakes. So this is from 2007, from the earthquake of 2010. And they have measured some variations in the density of the ionosphere related to these earthquakes. And the authors claim that 10-20 days before the earthquake, there was this anomaly. In our study, we have just taken the public Pierre Auger observation of cosmic rays, together with 3 sites of earthquakes monitoring that were in Moscow, in Finland, 2 in Russia and 1 in Finland, and we have just looked at the general behavior of the earthquakes, not localized but global, all over this data, and try to correlate and try to find how they compete or how they compare to the cosmic rays. And after checking for some correlation between the data from cosmic rays using 5 days over 5 years, we have found some signal. And we wonder if it's something that is global or could be dependent on the geographical location. So what you see here, as I said, there's data from the observatory, the Pierre Auger, the blue one, and there's also the data from the different earthquake stations. One of them is in Oulu in Finland and in Moscow, and even more. We have not in this article, but more recently, we have also considered if the sunspots could also be correlated, because the dynamics of the magnetosphere may be tied to the cosmic wind, also related to the sunspots, to the solar wind. Sorry. Okay, doesn't matter. So this is the idea. So we're interested in to continue with this analysis, and of course we want to collect more data with different types of detectors. So these are the correlations. In this case, 15 days before the corresponding change in seismic activity is what has been found. There are also we have to look at many years. So this is not like we want to look at different scales to see if we can find some behavior, perhaps self-similar. These are kind of the questions that we are asking ourselves. Other approach that we have followed to try to look at the variation of the signals is through Bayesian inference. So for those that never heard about this method, it's basically based on the so-called Bayes theorem, where we have to have some prior probability distribution. We have to have some data, and out of that, it's possible to compute posteriors, and these posteriors can be used for taking mean values and so on. So the method consider these probabilities is usually done through computations. But there's one specific example where this analysis can help to find a change in modulation of a signal. For instance, consider a signal that before certain moment, it has a mean mu1 and a sigma deviation of sigma 1, and at a moment changes into sigma 2 into mu2 and sigma 2. This method allows for finding exactly the critical point, of course, when we have some experimental data, and also we use these priors. Thank you. So we have done this analysis for the same data of the earthquakes, and we have found two possible change points. So in this case, you see here there's a signal with mu1 sigma 1 that changes into mu2 sigma 2, and the method gives a probability for this change point to happen. So we have found two change points. So we're still doing analysis. So this is work in progress, but perhaps this is one way to try to determine if the signal of the seismological signal is changing. So we have applied it for cosmic rays and seismological signals. The change points that we found do not coincide, so we're still wondering what's going on. So it's part of this analysis. And now I would just like to tell you, as I said, Credo, it's ambitious and wants to study this phenomena. But what do we have with Credo today? So today we have many detectors that are based mostly on citizen science. These are all these smartphones. But we also have some support from other institutions and different scientists. So when it comes to the smartphones, the Android app is already working well. There's another one being developed for iOS for iPhones. Then also the webcams of the laptops can also be used. So there's also some tests. And then there's a system of scintillators that is already in Australia by some professor. And these are the specifications. And also in the institute we have a gamma spectrometer. Here is some description. And what we also have in our hands is basically public resources, like the data from pre-year or from neutron monitor databases. So we want to extend this, and we want to invite everybody to help at any level, at educational or citizen or more technical. And besides that, there are some companies that are talking to us, or we are having some interplay. One of them is the Albacam that has produced this mini pigs, which is basically a detector that looks like an USB stick and can be used in the laboratory or in the office. And it's been already tested in the International Space Station, so they are collecting data. So it is capable of detecting different things like radioactive dust in air conditioning, or muons, or radon in cellar, or different things related to X-rays and so on. There's another prototype in the University of Łódź in Poland. that Professor Bibi is developing there. So he's basically using scintillators and trying to test the possibility to create some table experiment, let's say, with these detectors. It's called CredoMaze. This is also in development. Another of the ideas is to use the colliders as cosmic ray detectors. It has been already used for some time in CERN. So we would like to continue this by being in contact with people who are directly involved in the construction and in the control of the colliders, because the time of flight will be different from atmospheric muons than from muons that are being produced in the collision. So this could be some way to give a double use to these muon detectors in the colliders. Now there's also a company that developed as a startup, and it's called Astrotectonic, also based with people based in Krakow, from scientists there. So the idea is to try to create a huge neural network with data, and also create different detectors. So the idea is that they want to do research, but they also want to extend this to universities. So that's why they have support, and we're in deep collaborations with them. So let's say there's some interplay and some support. If you want to know more about Astrotectonic, I have another PDF file that I can give to you, so in case you are interested. So this is basically a company that is doing research, but they also plan to sell their devices and give support for educational or scientific purposes. And as I said, for us, it's very important the citizen science component, because this is the way that we can basically cover the whole planet with different kind of detectors. The simplest one and the first approximation are those smartphones. So the opportunities for participating people or your institutions is to develop educational programs, do real science, feed their curiosity, and of course get involved in the scientific papers, because the collaboration is open to everybody. And what we get out of this is obviously the manpower, the geographical expansion, and the popularization of these ideas and public relations aiming at also gaining funding for expansion of the project. So one of the alternative roads or to popularize it is to go through gamification. For instance, in Poland, there have been some organization of competitions where students or anybody comes and try to detect as many particles as they can, and in this way we popularize the project. So this is the Particles Hunters competition that can be also extended to everywhere. So if anybody is enthusiastic, they can visit this Particle Hunters competition in the website of Credo. This is the website. And well, I just would like to conclude that well, we need, one of the possibilities is really through citizen science, and for us it's very, very valuable. Yeah, with this, I would just like to invite everybody to participate or to interact with us. We listen to everybody, we welcome everybody. So this is the website, and the leader of the collaboration is Piotr Homola. So here are his contacts, and thank you very much.
Thank you very much for this review of all these opportunities, cosmic ray opportunities. So do you have any question? Okay, Professor Alejandro.
Thanks, Lisandro. Thank you, David, for this very nice overview. Two questions. One is that you mentioned that extended showers with the many components, not a single shower or a single particle producing an extended shower, but rather one particle producing several particles that eventually produce several showers can happen. And I suppose that the probability for that to happen increases with the energy of the primary, so to speak. There should be some correlation between not only the energy of the primary, but also the composition. In other words, the A number. And also with energy, is there a way that you guys quantify this correlation between the number of showers and you see the A number and the energy? And second, and this comes to this a project which seems to be very interesting, the correlation between earthquakes and cosmic rays. What is the source of the background for your signal? In other words, you're thinking that the magnetosphere is distorted somehow by earthquake activity, but you mentioned also hotspots in the sun. What are the other sources of a background that and how you subtract them if you do?
Okay. So for the first question, we really rely on a theoretical scenario because this would probably, we rely on the theoretical scenario because it will determine very well the channels of the case. For instance, if you consider dark matter, you might consider that the particles produced have different spectrum, right? So this could be the source of this different. Why it's not a single shower, but also because of the kinematics of the process in the case of dark matter or monopoles, depending on the theoretical scenario. So we basically take a few of them, and we also invite everybody to provide if they have some theoretical explanation for us to test their idea with and do the simulations, because we have the tools for the simulations once we have the remaining particles or the photons that is created. This is with respect to this first question. For the second question, we are actually exploring these different signals that could be the background, or that could be probably, or the other way around. That might be the signal over the background. In the case of the spot, we are looking for a regular for regular behavior. Know that the cycle is about 11 years of the sunspot, but the sun also presents some sort of differential rotation, and this can be modulated. So we are studying if this is something that we need to subtract, or the other way around, it might be the one that dominates. So this is something that we are just starting to do. This is still going on. So basically, I don't know if I answered.
Any other question? No? Okay, if not, then now you have a question.
Yeah, it's a short question. Sorry, I didn't listen all your presentation, but are you planning to do something or to contribute to the muon post-law problem?
Say it again.
Can you contribute to the muon post-law problem?
To the muon puzzle problem.
Yeah, because you can adapt or calibrate for showers, because I see that you are planning to have a lot of detectors and you have coincidence, right? So you can try to calibrate and say something.
Yeah, this is something very important. I think we can also contribute in that direction. Personally, I've been thinking about this problem, and I would like to look at the hadronic models. Perhaps this is the reason why we detect more muons that are predicted. But of course, all these detectors can be used once the data is there. It can be used to test these different scenarios or different explanations for the muon problem. Yeah.
Okay, thank you. So we thank again the speaker. And now we keep on the cosmic ray subject. But okay, before I forget, please avoid eating inside the room. It's strictly forbidden. And also you are invited, okay, remember that we are obliged to use the mask inside the room. So please And okay, so now we are turning to also to cosmic rays, but about neutrino detection in the HOC by Hermes León from the Instituto de Física UNAM. Creo que es con el pad, con el pad. Exacto.
Okay. So I want to thank the organizers for the opportunity to show my results here. And I will be talking about neutrinos. So I have to start with the most important detector of neutrinos, high energy. In this case, I'm referring to high energy neutrinos. So this is an event display of the IceCube Observatory. Most of you know about it. It's a kilometer of ice instrumented with photomultipliers. And what you see on the slide is the visualization of an almost horizontal muon is coming from below the horizon and propagating towards the left of the slide. And I want to show you, and I hope I can convince you that we have a tiny slice of a detector like that in Mexico. This is a picture of the HOC Observatory. I don't have enough time to show you and discuss all the technical details, but this is a real event that we see with the observatory. You see the view from above of the instrument. Each of the large circles corresponds to a water Cherenkov detector. This detector contains 200,000 liters of water, and inside of it, we have 4 photomultipliers that are looking upwards to observe the volume of water for Cherenkov light. If you have more questions, of course, I will be presenting a poster afterwards, so we can discuss about that if you are interested. So the observatory is located in a very nice place. It's between the Pico de Orizaba and Sierra Negra volcanoes. You see on the left, the Pico de Orizaba, on the top, on the bottom right, the Sierra Negra, and the little speck in the middle is the HOC Observatory, and you can see a zoom over there. And to make it interesting to my students, I always say that it's the only instrument that's studying physics that you can observe from the space. So these are actual pictures from the International Space Station, where you can see the Pico de Orizaba on the bottom, on the top, the Sierra Negra volcano, and in the middle, the HOC Observatory. So what I will discuss today is a work that I did. This was an analysis that I started 6 years ago. So it was a very long period of time to develop it. The first time I've discussed this topic in the HOC collaboration was more than 6 years ago. And then it took me 6 months to have a look at the data, implement the ideas I was developing. I studied 10 seconds of data at that time. And the publication finally appeared this April. So it's kind of a little more recent. And that's what I want to discuss today. So the idea is you have a huge target, in this case, the Pico de Orizaba volcano, and you can use that target to produce neutrino-nucleon interactions as exemplified by the Feynman diagram on the right. You have an incoming neutrino interacts with a nucleon in the mountain through a charge current, and you get a lepton, a charged lepton of the same flavor as the incoming neutrino. So in that instance, I have there a tau neutrino, but you can have a muon neutrino, and you get outside of the mountain a muon. The idea is that then the lepton escapes the mountain, and it can be detected with HOC. And also the mountain serves as a shield for the horizontal radiation that is propagated toward the detector. So it has 2 uses: to produce the neutrino-nuclear interactions and to filter all the cosmic rays that are coming from that direction. Now, this is, of course, not the first time that this is attempted. On the top left, you can see an example that happened in Hawaii. So experimental physicists will like fancy places. In that case, they located a air Cherenkov detector in one volcano called Mauna Loa. On the right, you have the Mauna Kea. So these are 2 very close volcanoes. And the idea was to produce the neutrino interaction and then observe the air shower as it was propagated horizontally towards the telescope. They didn't get any signal, but in the lower part of the slide, you can see the flux against the energy of the neutrinos. Maybe you cannot see the values, but the solid red line corresponds to the limits they obtained for multi-PeV neutrinos. So this is above the energies that can be studied with IceCube. And on the right, you have the MAGIC observatory. This is an air Cherenkov telescope. And what they do is that from time to time, they, instead of pointing towards the sky, they point it below the horizon, trying to look showers that are coming from below the Earth. Okay. And they also were not able to observe any signal, but they put limits for neutrinos above 1 PeV using this method. And there's also this example in China, with Professor Zheng Cao proposed to build an observatory for tau neutrinos. It was very interesting because he came with this idea in this Chinese program of developing science, and they told him that it was not ambitious enough. So they gave it $180 million, and he built a huge detector that is 4 times the size of Hawk. So yeah, sometimes they tell you to do something even more impressive. So I have more history about this type of science, how we have tried to do it. In this slide, you can see 5 names of experiments that were proposed to do this type of science. However, none was built because the common belief is that it's impossible, right? You have heard that multiple neutrino detectors are located below ground to kind of isolate from the cosmic radiation. And the idea of having an observatory above the ground, was not funded because of the reason. Most of them are Cherenkov detectors using water, so very similar to Hawk. In this case, Hawk was already built, so I just had to try it. And this is what I'm discussing today. I will be showing several event displays, and this is an example so you can understand it. Is a visualization of the Hawk observatory from above. Again, the big circles corresponds to the Cherenkov detectors, and inside you can see you have very good eyes for smaller circles. These are the photomultipliers that are located inside of each of the detectors, and the color codes indicate the time in nanoseconds. So blue is early time, and red is late time. So it's an air shower propagating through all the detector from left to right, and the size of the circles with colors correspond to the charge. So a large circle corresponds to a large charge deposit. And you can see in the middle of the detector, a lot of big circles. This corresponds to the so-called core of the shower, where by momentum conservation, you expect a lot of particles and therefore a lot of light producing that region of the detector. Okay. So this is how you can read the event displays. Color indicates time, and the size of the circles indicates the charge. And what I do is, instead of using Hawk as an air shower detector, I use it as a particle tracker. So all of you are familiar with CMS. You can imagine that you have the pixel detector. Now you show it using Hawk. And what I will be looking for are propagations through lines of detectors, right? Either columns or rows, okay? And this is an example of how one of these signals look like. In this case, I injected in the simulation a muon coming from the top right corner of the display, propagating in the opposite direction. So it's starting the blue towards red. And the algorithm that I had developed was using the information of the water Cherenkov detectors. I consider each WCD as a pixel, as in the tracker of CMS. And then based on the amount of light and the amount of PMTs that were activated in each detector, I consider the quality of the pixel, okay? Just as in a tracker in a LHC experiment. And these are some examples. So this was kind of the main problem when I was trying to explain this idea to other people. They were expected to see events like this. You can see that there are only scatter points with color. So this is kind of uncorrelated signals falling in the detector. And these are most likely vertical muons hitting at not consistent times in the detector. And people told me, well, you are just going to find this, right? You will see no correlation of a signal propagating horizontally through the detector. You will see what happened. So in order to do this, I have to develop all the algorithms because nobody cares about this type of signals in Hawk. So what I will show you corresponds to 6 months of lifetime of the detector. So these are more than 260 terabytes. And in order to process this amount of data, I require more than 7 million CPU hours. In this case, I use 2 clusters. We have one in ICN in UNAM and another at the University of Maryland. The selection of the pixels, I require that each PMT sees at least 4 photoelectrons in order to be kind of above the background. And also, I require that at least 2 PMTs out of the 4 inside each WCD has a signal. Also, because I'm doing the reconstruction, that's why it takes so much computing power, I can remove all the showers from the data and just keep data that could be related to horizontal muons. And to give you an idea of the background, of this background that it was supposed to be impossible to control, vertical muons are hitting the detector from above all the time, and the rate is around 10 to the 4 per square meter per minute. So it's a very high rate background. Each WCD has a diameter of 7.3 meters, and the PMT rates are between 24 and 39 kilohertz. So you have to find a needle in a haystack to look for these signals. And on the bottom part, you can see an event display. So in this case, it's a real signal. So you can observe a particle that is propagating from left to right. You can see that it's very clear to observe even by eye. And just to tell you what additional cuts I implemented, I just require that the propagation should be consistent with the speed of light. That's what we expect from leptons. And two quality cuts that are very simple. The one on the left, I call heat activity. I just make the ratio of the number of detectors that are present in the event display divided by the number of detectors that belong to the track as identified by the algorithm. So the idea is to get very clean events where you can only see the track propagating. And on the right is the same cut, but in the total number of pixels, I require that they have at least 2 PMTs with more than 4 photoelectrons. And with these two very simple cuts, I was able to get this kind of signal that you can see there, a muon propagating from left to right over hundreds of meters in the detector. Now, there's also the problem of combinatorial background. So you can, this is my illustration of fog as seen from the side. On the right, you have the Pico de Orizaba volcano, and on the left, the fog tanks. And you can imagine that it's being hit by vertical muons all the time. So for instance, you have there muon hitting T0, then you have another vertical muon, T1, T2, T3, and just by chance, you can have a sequence where it's hidden up and randomly. And because I represent that it's on this one information vectors, I can be very naive and say, okay, this is propagating from the volcano to the detector. So this is the combinatorial background. And in my case, I used my background on particle physics. I was a member of this collaboration, so I knew some of these things. So, for example, you have the plot on the left bottom. You have some signals in your detector. What you do is you take the signals and then randomly change the position of the signals, so you get a mixed event. And then I run my algorithm to find patterns in this random event to see how likely this is to happen. I did this with all the events that I had in my data sample. This, of course, increased the computational complexity. But after doing that, over the 6 months of data, the longest track that is produced randomly consists of 3 tanks. So that, for example, the one that I showed in this illustration. So for the analysis, I simply select tracks longer than 4 pixels to get rid of the combinatorial background. And these are some examples of very nice long tracks that I observed in the data. For example, in the top left, you have from left to right. On the top right, you have from the bottom of the detector upwards. On the bottom left, from right to left, and the opposite in the last plot. So you see, we can observe this type of signals using this detector that was not designed for this purpose. And of course, you may wonder where is the volcano in these diagrams. The volcano should be on the top right section of this display. So in this case, I'm showing you an example of a track that is coming from the volcano. Is longer than 4 pixels, so it's a real signal. Of course, and this is very interesting. However, as you know, in collaborations, you have to prove that you are not doing something silly. And one of the tests was that, as you can see, there is a clear pattern of a line of the detectors being activated at the speed of light. However, there are some signals that are close to each other. Let me see if I can indicate you where. Here you see 2 tanks that are close and are being fired at the same time. And some people could say, well, if you have an elementary particle that is propagated at the speed of light, you should only see signals in 1 tank. Of course, this is not that simple, but I have to address this issue that we have collinear hits in detectors that are 7 meters wide, and it should be, in principle, a perfect line. So this is one of the first problems I had to address. And the first thing you do is to go to the simulation. So in this case, in this plot shows only simulations, and because they're simulations, I can identify where the muon was propagating in the data. So where you see a detector that has kind of a circle around it, it means that the simulation says this is the path that the muon followed in the simulation. And as you can see, we have this effect of having non-collinear WCDs being activated in time. So for instance, in the top left, you see that we have the muon, and then at the end, you have a small shower of tanks that are activated on time. On the top right, you see 2 tanks being together, having signals. And on the bottom, you see the same case. More WCDs activated, even when the muon was not propagating through there. And I will tell you the reason in 1 second. So the reason, in the Monte Carlo, of course, you can go to the origin of the Cherenkov light, and this plot illustrates this. This is normalized. This is in percentage in the y-axis, and in the x-axis, you have the identity of the particle in the simulation that produced light. What I injected are positive muons, so you expect to see the larger percentage in the column of the positive muons. I don't know if you can see it, is the third one from left to right. And of course, then the second most significant contribution comes from electrons, produced, for instance, from brainstorming or from quantum effect. But you can also get, in very rare cases, hadrons producing additional light in the detectors. But mostly it's coming from the muons. Now, this is, I think, a more illustrative picture. On the top left, I show you the sources of chemical light. When you inject 10 GeV muons in the simulation, you can see that it's dominated, 80% coming from positive muons. This is what I inject. And then the remaining contribution is coming mostly from electrons and a small fraction from positrons from pair production. Now, if you go to 1 TeV, you get the distribution from the right. You see that the contribution for the original muon decays by almost half. Now it's only 40%, and most is coming now from electrons. And if you go even higher energies in the bottom part, for a 10 TeV muon, 60% of the light is produced by electrons, 32% is by positrons that are coming from pre-production, and only 8% for muons. So the reason why I have signals in more than a straight line is because of the mechanisms of energy loss of the muons. So this is the simple formula that we have. A muon loses energy via two mechanisms: ionization, radiation, that is the Bethe-Bloch formula that you all know. And on the right, and this is not so common to know, is the radiative energy loss that happens for very high energy muons. So when you have radiative energy loss, you produce electron-positron pairs that make the muons lose a lot of energy. And the critical energy that I put below is the energy where the radiative energy loss is larger than the ionization energy loss that is more common. And so to quantify how many or how often should I see more WCDs with signal, not only restricted to the line of tanks, I made this plot. So on the y-axis, you have the percentage of events that have more than the ones contained in a simple line as a function of the muon energy. So you can see for 10 GeV muons, this is the most left bin, is of the order of 2% of the times you have more signals than where the muon was propagating. And if you go to the other edge of the slide, to 10 to the 4 GeVs, 10 TeVs, more than 50% of the events have more signals than a single line. So this is clear, and we understand the effect or the reason why we have not perfectly linear signals. Now, the second problem is tracks with discontinuities. This, again, a real data signal is pointing to the volcano. And if you have good eyes, you could see that it starts with blue. And then if you follow the line, you will see in the middle a WCD that doesn't have any signal. So again, this was a problem. I have to show that this is real, that is not an artifact in the data. And I have to address this issue. So in order to do this, I have to do quality control of all the data. In this, I can identify which is the date of this event. This happened in May 5th of 2018. I know exactly to the second. And the tank that there where we have no signal, remember it's the one just in the middle here, in the Hawk, internal information, we call it N11, just to have a numeric code. And on the bottom right, you can see the PMT rates of the PMTs located inside this tank. Remember, there are 4 of them. And you cannot see the y-axis. This is the time. But the point is that all 4 PMTs were taking data at the moment that we have the signal. And on the left part, you can see the region of the sky that the observatory was looking at that precise moment. And most importantly, there is a red line on the bottom part that indicates the stability of the detector. So the detector was perfectly stable. The PMTs were taking data. We simply don't see any signal in that detector. The same, I have another example here. I think I will just skip it, but it's the same idea. You have a signal that starts, you expect to see a straight line of tanks with signal, but again, we have a gap over there. In this case, the tank is I10. All 4 PMTs were taking data, and the detector was stable. So it seems that everything was okay. So what is the reason of these discontinuities? Again, we have to go to the theory. And to illustrate this, on the bottom part, on the top part of the slide, you can see a simulation, in this case for the reference I put there in the slide. They inject an electron in ice, and the red and blue lines corresponds to positive and negative particles produced in the interaction of the muon as it propagates in the ice. So you can see in the case of the electron, it's kind of very uniform, and then it dies out. The scale is on the bottom of that part of the figure. This is 1 meter, the line that you see there. And the most interesting part is you look for muons, in the case that is illustrated in the bottom part of the slide. In this case, what they injected was a 5 TeV muon coming from the left. So the muon enters the ice. You can see there's production of secondary particles. Remember, it's a semicode, red negative and blue positive, but there are gaps, right? It's kind of flashing the muon as it propagates through the ice. And to make things clear, here I show you the scale of one of the detectors of Hawk. So if you move this detector along the propagation of the muon, you can see that there will be instances where the muon deposited a lot of light and instances where it deposits barely enough light. So this was the problem. The detector sometimes is seeing a lot of light and sometimes it doesn't see any light. So this is perfectly understandable using simulations. And again, not only we know the theory behind it, we made simulations, and in this case, all 4 examples are simulated muons injected in the Hawk Observatory. And you can see there with the arrows, the points where there is no signal in the detectors. So we understand this and it makes sense. Now I can finally show you, these are 4 examples of tracks that point to the Pico de Orizaba volcano. This is exactly what I was looking for. And I show you the reasons why you see some peculiarities, like not only one tank being fired, but neighboring tanks fired on time, or even gaps in the tracks. So this all makes sense based on the detector performance. Now, the first background was this combinatorial signal coming from vertical muons, but it turns out that there was a second background that was very hard to identify. And this is because I'm looking for a process that is very rare. You have to think a lot of rare processes that could accompany this. So this again, a picture of Hawk from the side. You have the Pico de Orizaba volcano, you have vertical muons hit the detector all the time. It turns out that with some probability, as we all learned on undergrad, one of these muons of discharged particles can simply deflect by a small angle and produce a horizontal signal. And then again, I'm very naive and I say this points to the volcano, and it's not the case. So this is just a scattering, and it's very energy dependent. It's a very unlikely process, but it happens. And it turns out, well, at this, I found this reference from 30 years ago from people in Italy that they were proposing to build an above ground detector. And they identified this background. They said it should be below 20 GeV. It means muons with energies below 20 GeV are very affected by this possibility of being scattered towards horizontal directions. So I have to be careful also about this. So then the name of the game was I have to characterize this background of muons that are being scattered towards the horizon. And this is what I did. What you see on the slide is kind of a visualization of the Pico de Orizaba volcano. If you stand in the center of Hawk, and then you look at the mountain, and the color code tells you how much matter would be in each direction. So yellow corresponds to a lot of matter, 25 kilometers water equivalent. So it kind of, you have 25 kilometers of water in that direction. And in order to get this map, whether this was to use data from INEGI to characterize the shape of the volcano, and then I converted geometry to this amount of matter using this density of andesite rocks. In order to do this, I contacted an expert at UNAM about this volcano, and he told me if you were going to use one single value, use 2.6 grams per square centimeter. And with this, I get this map. Now, the region that I identify with the red lines corresponds to the analysis region. So I will be pointing my analysis to that region that is encircled in red. You can see I don't go very high in elevation because Hawk is flat. So it's very difficult to identify more elevations precisely. And I was very happy because when I submitted this work to a neutrino workshop, they put me in the new facilities section. So they told me that I made the first neutrino detector in Mexico. And the idea of looking to regions with a lot of mass comes from the plot on the left, from the particle data group. What you have there axis, you have the amount of matter that you have in front of them. So if you start on the left, you have basically no matter on above your detector. And if you go to the right, you have more and more matter. Yes, it is in kilometer water equivalent. You can see that the curve decreases very fast, but then it reaches a value close to 10 kilometer water equivalent, and then you cannot get rid of the signals. So what is happening there is that you are stopping all the muons, but you are producing muons by charge currents, right? So these muons that you see that stay on the horizontal region of the plot are neutrino-induced muons. This is exactly what I am looking for. So this is the goal of looking at very deep regions of the volcano. In order to make the scattering model, what I did is a very simple model. So I apologize to the theorists. This is a poor experimentalist approximation. You have there the profile of the volcano, and on purple behind the mountain is the region where the muons are coming to the detector. And on the bottom part, what I did was use the giant force simulation of Hawk. I inject muons coming from different angles, and I see the probability that they scatter towards horizontal directions. The plot, the x-axis is the elevation angle. You can see that it starts around 5 degrees because the lowest part not covered by the volcano is around here, 5 degrees. Okay, and of course the processing will happen or almost because they look like that one. The pattern very high, scattering and get a consistency. But this was done with simulations. And then for the real flux of muons, I use data from this observatory in Armenia, in Aragats. And also, well, the problem is that the data is very scarce. You don't have many observatories like Koch located at 4,100 meters above sea level. So in this case, the mountain in Armenia is at 3,200 meters above sea level, but good enough. So this is the origin of the plot that you see on the bottom part. This is the flux, the intensity of muons as a function of the zenith angle. So I use this data and some modeling from Professor Lipari in order to do the modeling of the muons that should be coming to Hawk. And the calculation is very simple. I show you here the example where I do it for 5 GeV muons. You see that I have an integration from a starting angle to a final angle, and this corresponds to these angles in this figure. So I start at 18 degrees. As you saw above, is very unlikely to happen. And then the limit of integration will be given by the profile of the volcano. So in this case, I'm doing this in steps of 1 degree in azimuth in the horizontal direction. So this is illustrated by the shaded band on the left. And what I do is integrate, in this case, for the region 1, that's indicated in the bottom part of the figure. These are 6 bins. So I just repeat that for the 6 different regions and then add them. So I have the contribution for 5 GeV muons. Then I just repeat the same for all energies. It turns out that the threshold for the detection with Hawk is of 2 GeV. So that's why the summation starts there and goes up to 100 GeV. You will see in a second why. And then I simply divide this value by the solid angle covered by the detector, indicated by these different analysis regions. And I obtain this plot on the left that compares the intensity in the y-axis as a function of the analysis region, where full is the complete rectangle, 1 is the section that is on the left, and 2 is the section that is at the center of the volcano. The data points indicate the flux that we measure with Hawk, and the gray band indicates my prediction using this simple scattering model that I just described to you. And as you can see, it works very nice, but it basically tells me that most of the signal is coming from scatterings. It's not really neutrino-induced muons inside the volcano. But also makes sense if you compare, for instance, region 1, you don't have that much mountain above it, so the intensity is smaller. Sorry, it's larger compared when you have a lot of mountain, that is region 2. That explains the factor of 6 between regions 1 and 2. So everything makes sense. But then you can say, well, that's very nice, but you are just seeing scatterings. You were not able to get the neutrino-induced signals. But what we have actually is a model that tells us what is the energy distribution of the muons that are being scattered. And this is shown with the gray plot that is on the right-hand side of the figure, on the slide. And what I show in the left axis is the differential distribution, and the horizontal lines that you see in the plot on the right are the integration. So for instance, if you integrate the whole gray area, you get the line that is up the top, and that corresponds to this region here, okay? So you can repeat that for all regions, but the important part is that instead of integrating above 2 GeV, if you increase the threshold, if you start integrated, say 60 GeV, you can see that it decreases by orders of magnitude. You have an integrated flux much slower. And if you go to 80 GeVs, you get the dashed line that is on the bottom. Now, the important part is that you have to look at the purple band that is here. This is a measurement from an Italian group in an experiment called LBD in Gran Sasso. So they measure these neutrino-induced muons. So this is what you have to be able to measure. So if you are below, with this background, below that purple line, then you're in business, you're getting neutrino-induced muons. So basically my model tells me that I have to be above 100 GeV to be able to get neutrino-induced muons, okay? Now, how can we get some numbers out of the Hawk data? So the detection probability using an observatory like Hawk is estimated using this factor that is called effective area. Don't worry about it. Basically, just look that it depends on the ratio. If you use your simulation of the number of signals that trigger the detector, that is in the numerator, divided by the number of particles that you generated in the simulation and activated the detector. And this, of course, depends on the energy. To illustrate that, you have to look at the plot that is on the bottom right and look at just at the red curve, right? On the x-axis, you have the energy of the muons. On the right axis, you have the trigger efficiency. You can see that Hawk doesn't work below 2 GeV. The efficiency is practically zero. And if you start to increase the energy of the muon, you get more and more efficiency to trigger the detector. And we already discussed what is the reason of that. Remember, you have a high energy muon, it starts to radiate particles, and this increases the probability to activate more PMTs and then activate the trigger of the detector, right? So again, we understand perfectly this, and we can use it to our advantage. Now, the table on the left part in the bottom illustrates the values of the effective area. So this is, if there is a fan of ice cube, you will say this is a joke. It's a very small effective area, 5.1 times to the minus 2. So this explains why we have a very low rate with an observatory like Hawk, because it's just kind of a tiny slice of a big observatory like ice cube. But this value, as I show you above, depends on the energy that you start integrating your signal. So in order to estimate what happens if I start at 100 GeV instead of 2 GeV, I took the most likely value, that is actually 5 GeV, because 2 is at the threshold. And then I compared that value at 100 GeV. It turns out that this factor is almost 120 times larger. So the more energy, you are more likely to activate your detector for the reasons that we just discussed. And then you can extrapolate the effective area I have from the simulations for Hawk for a detector above 2 GeV to what happens if I start triggering above 100 GeV, and it goes to 6 square meters per state radian. This is again very tiny compared to ice cube, but you can calculate how many signals you should have in 1 year using a detector like Hawk. For that, use that simple formula. You know the intensity of neutrino-induced muons from LBV, this experiment in Italy, and you get to a final number that after 1 year, you should have of the order of 2 neutrinos in the data, okay? So this is, and here's one of the difficult points, because most people see this number and say, well, it's a joke, 2 is nothing. But the point of this whole exercise is that an above ground detector is much less expensive than an underground observatory. We save a huge factor in the economy. And also, with a detector like Hawk, and you see this method, if you observe a high energy signal in the detector, it's more likely to be a tau lepton. There are many tau lepton experts in the audience that can tell you better this than I do. But if you have a very high energy muon, the energy losses are super high when it's leaving the mountain compared to a tau lepton. It loses much less energy and is more likely to exit the volcano. So we have then of the order of 2 signals per year with the current configuration of the observatory, if I'm able to select signals with more than 100 GeVs of energy. And to put this number in context, because we are talking about tau neutrinos, this particle was discovered in the 2000 in Fermilab. It was the penultimate particle of the standard model to be discovered. And the discovery was announced with 4 events, right? The statistical significance was 3.5 sigma. Then in 2007, they reviewed the data sample again with improved methods, and they identified 9 tau neutrinos, okay? Then Opera in 2018 reported 10 more neutrinos, and just at the beginning of this month, IceCube finally published 2 additional neutrinos. So in total, in the whole history, there have been 21 direct detections of tau neutrinos in physics. So even if my numbers are ridiculously small, we are in a very ambitious game where there are only 21 detections in total. Now, to kind of motivate more this method of using an above ground detector, using a mountain as a target, this shows the field of view that we have with Hawk. What you see there are the 122 signals that I found in the data that point from the Pico de Orizaba to the Hawk detector. So imagine if all these were neutrinos, that would be how they look in the sky. And to give an idea of the scale, I put there some constellations, Cassiopeia, the Big Dipper, and the 2 in the bottom are 2 active galactic nuclei that, as the previous speaker told us, are one of the possible sources of the most energetic cosmic rays in the universe. So I think it's kind of nice that with a very simple detector that was meant to do something completely different, we can try to get in the game and show people that it's possible to do this physics in a much cheaper way than going underground. Of course, you can wonder, well, if you say you have 2 signals per year, do you have any candidates? And this is what I'm going to show you now. This from a result I had 3 years ago that I showed in this conference, ICRC. So what I did was take the volcano. You see there, I took a much simpler approach. I divided the shadow of the mountain in the small rectangles that are identified by letters A to G in the bottom part. And the histograms that you see on the right-hand side corresponds to the cell C that is kind of in the middle, and then cell E that is shifted to the right of the middle. The histogram in black shows the data, and what is showing is the average deposit of light in the detector in the x-axis. You can see there the value in photoelectrons, and the different colored lines indicate what I get when I inject muons of different energies. So for instance, if you look at the C cell, the one in the middle, you see that if I inject 10 GeV muons, it goes up to this value. It's around 50 photoelectrons because the muons are only losing energy by ionization. But if you get, you go to 100 GeV, you get this purple distribution. It starts to radiate. And if you go to 10 TeV, you get this blue distribution. All distributions are normalized, so you can compare them by eye. And you can look for this most extreme signal we have it in data sample. And this is the visualization. It's clearly pointing to the volcano. And the same for the cell E. You can see that we have a very interesting outlier here that deposits a lot of light. And it's the visualization is the one here below. So to give you an idea, an average muon deposits 30 photoelectrons in the detector, and this is depositing 1,500 photoelectrons, and this 1,600 photoelectrons. So these are signals that are depositing a lot of light. Now we can do a napkin calculation of what could be the energy of that. So I told you that the reason a particle produces more light in a Hawk detector is because it's radiating particles, and you can imagine that you can integrate the Cherenkov formula, remember the Frank-Tam formula, tells you how many photons are radiated per unit length. So the length corresponds to the amount of distance that the particle travels inside the detector. But if it's radiating charged particles, you can add the path of the secondary particles, for instance, positons and electrons that are radiated, and actually increment the length that is allowed to produce Cherenkov photons. So on the bottom part, I'll show you again a result from a German group that actually participates in IceCube, where they studied, depending on the energy of the muon, that is the x-axis, what is the total length that will be able to produce Cherenkov photons. And as you can see, it's a linear relation, right? The higher the energy, the higher the length that you have to produce photons. And therefore, you can, in first approximation, compare the amount of photons to the energy of the particle, right? But just only on first approximation. So if we do that, we can tell that this particle, the one that I'm showing you on this slide, is depositing 50 times the average energy loss. And if my average energy was 5 GeV, I'm here at 250 GeV very approximately. And this could be a candidate for a neutrino detection using Hawk. Okay, so I show you it's possible, and just some very promising signals that I already presented at the conference 3 years ago. So with this, I get to the conclusions. I was not able to tell you the astrophysics of Hawk. I wanted to concentrate on the work that I have been doing. I will be presenting a poster, so if you want to discuss technical details, I will be more than happy to do that. And just wanted to show you this experience, especially to the students, that if you get into a mess that you're not supposed to do, it will be a long time. I spent basically 8 years working in this project, but I'm happy with the result. I'm not now telling you these are the neutrinos, the first neutrinos detected in Mexico, but I think I got very close, and I'm happy with that. I have to develop all the tools because Hawk is designed to detect air showers. Nobody thought that it could detect leptons, and so it took me years. And as you saw, years of CPU processing to get the signal. And the conclusion is that it's not impossible. It's just really, really hard. Right? And thank you.
Thank you very much. Congratulations. Any questions?
Thank you for your nice presentation. I have a question. This is a proposal for the collaboration to do this project here in Mexico?
Well, actually, the proposal was 6 years ago, and I'm happy to tell you that in April, it was finally published. So yeah, now it's a reality.
Perfect. Okay. My question is why you are not considering the electron channel? I mean, electrons that comes from the mountain with horizontal trajectories after interacting with the mountain.
Well, the problem is that an electron immediately showers, So it's completely absorbed in the mountain. It's not able to escape. The only ones that can escape are the muons and the taus. And because of the energy loss, the most likely, if you have a very high energy signal, is a tau. So electrons, yes, they are produced, but they stay in the mountain. They are not able to escape once produced.
Okay, perfect. And the last one, could be better consider not only a big mountain like Pico de Orizaba, instead of considering several mountains to catch more muons, not only from a direction, instead from several directions.
Well, the only thing is that in order to claim that you have a neutrino-induced signal, is that you need a lot of matter to stop everything else. And that's why the Pico de Orizaba is only what? Next to Hawk, we have the Sierra Negra, but it's not as thick as the Pico de Orizaba. So this is the only one that can serve the purpose of stopping everything and just neutrinos out of the mountain. Thank
you. Okay.
I have a question concerning another project, which was to detect neutrinos in the mountain, between Chile and Argentina. So I don't know if this project, is being pursued, or do you know what the status is for this project?
The last time I heard it was actually, I think, a week ago, and it's ongoing. Actually, because the people of Hawk are also looking for a site in the southern hemisphere to build something similar. And then they were told that there are two projects. There is a second Hawk or Hawk South, and the one that you mentioned to look for neutrinos. So it's ongoing.
Okay, well, I have a question. So what's next? What are you thinking to do? Okay, now that you have successfully developed all these, what are you thinking about doing with what you have developed? What else can be done, for example?
Well, actually, the morale is that the problem is that it took me a long time to develop all these tools. And if I want to process more data to look for more candidates, it takes forever, even using these two clusters. So what I want to do is to use muons that are coming from different directions. Actually, there's one that is not blocked by the mountains, and I can only look for atmospheric muons. And the importance is that nobody has taken data at that altitude. So I can use that. And also I invite you to my poster. I will be talking about, we can also use physics to infer, for instance, the production of chaos and pions in the atmosphere, measuring muons. That's what I plan to do. I don't plan to do more of this analysis because it takes a long time. And instead, I will use the data that I already have to get other physics analysis that are kind of closer to get soon and published.
Okay, perfect. Thank you very much, Hermes, and congratulations. So we thank Hermes. So in principle, in the agenda, we have a coffee break, but we have a good and bad news. The good news is that we have coffee. The bad news is that we don't have the break. Okay, so we will, because we are quite behind the agenda. So now we switch to the new other session, and another announcement is that for the students that are supposed to present their posters, the mamparas are already there, so you can go and start pasting your posters. Okay. So now the convener is going to be Mario.
Okay. So hello, everyone. Today I'm going to talk about the work that we perform as a team from WAP and Simba staff. And here is the outline. An introduction, very brief, about colliders, NICA, MPD detector, and the monitoring detector that we proposed. The second point is the BB cells, the prototypes that we explored. And the third point is next is the physics performance of the detector. And last part is for the conclusions. So at the moment, we have 7 colliders. These 7 colliders are ongoing, working, and we have 2 under construction, FAIR and NICA. The nuclear matter that it is produced in those colliders, in the in the ones that are in constructions will be studied by CBM at FAIR and in NICA by BM at 10. That is here. It's a fixed target experiment. And in MPD detector. The other one is a detector for spin physics. So there is a big competition between these two experiments and some delays because pandemic and other things, of course. And for some reason, I like this more because there is an advertisement in the city. You can see, okay, we are building a collider. Come here and make tourists. Or maybe it is better to make more business there. So this is how it looks like. Here's the nucleotron, the MPD hole, and the SPD hole. For the MPD, we have two stages. The first one will be considered these detectors, and the second stage will consider the ITS inner system and forward spectrometers. At the conceptual level, MPD has three detectors for make the level 0 trigger, which are the FFD, 0-degree calorimeter, and the beam counter. So because the detector is divided into two stages, we can propose detectors for the first stage and for the second stage. For the first stage, this is the luminosity detector that it has these dimensions, this geometry. And for the stage 2, these kind of geometries that are more complicated, and I'll tell you later why are here. So the first one was first proposal, and the second one is the proposal as that I'll talk about it. The idea is to increase the pseudo rapidity coverage. And because it is sometimes very difficult to take a reference like this or take a look the detector geometry or the dimensions. Well, I'm over there, so you can imagine I try to fix the detector in this room. And I open the arms like that because this is the size of our detector, our proposal detector. So we're going to characterize and make laboratory measurements for this kind of system. So at the beginning, we perform GN4 simulations for the cells, considering the impact of the particles, sharp particles in the corner, in the center, and in all the surface, like in an experiment. And roughly, we can see that if we perform, for example, a beam test that is very collide or very specific surface of the cell, it is impinged by the particles, we can have a factor of 5 if we go to the measurement in all the surface, for example. So the laboratory measurements are here. We consider different number of sensors and different kind of them for two different cell sizes. So you can see that the better result, it is here with this photosensor. And we explore, for example, for this photosensor, these two overvoltages. So we can see that the time resolution, it is decreasing if we increase the overvoltage. So let's keep increasing the overvoltage if we have the necessity to have less time resolution or better time resolution. So the problem if we try to increase the voltage is that the time resolution is also dependent of the noise factor of the silicon photomultiplier. So as you can see here, for example, in this silicon photomultiplier, we have this crosstalk gain that are increasing with the overvoltage very linearly, and the photodetection efficiency is not very, well, it is increasing, but at some point is not longer increasing. So that's a matter. We have to work with these two quantities. About the physics performance, we have 3 different studies. The first one is the trigger efficiency. The main detector to do this kind of tasks for heavy ions is the FFD detector. But for proton-proton collisions, this detector sometimes is not very good. So we consider the trigger efficiency for for this beam monitoring detector, for proton-proton, and also heavy ions. And as a comparison, we have here in this right side, the values that are obtained for FFD, FH are considering an OR between these two detectors. Of course, it is using different Monte Carlos, different energies, slightly different, but we can see that this detector can reach very, very good trigger efficiencies. About the centrality and the reaction plane of the collision, the detector that it is going for this objective is the 0-degree calorimeter. And for centrality, we obtained these results that are in the left for the beam encounter. And you can see that using different Monte Carlo generators, for example, in these centrality values, we reach 34, 45. And if we look at the FH call, it is having similar values in this centrality region. So it is very competitive. For the reaction plane, we also perform a simulation. So we obtained different values for the centrality, for the resolution for the centrality, and we reach 44, 43 percentage of this for this region in the impact parameter. So conclusions. Well, at the beginning, I showed the results from the laboratory, and we reach time resolutions between 0.4, 1.4 nanoseconds. And for triggering and centrality resolutions, this detector get an excellent characteristics. And for the even plane resolution, this detector is complementary for the 0-degree calorimeter. So we believe that this kind of detectors will be very useful for NICA physics for the stage 2. So that's it. Thanks.
Okay, thank you very much, Marco. We have time for questions. Okay, I have one quick question. Do you have any constraint about the time resolution of this detector?
Excuse me?
Do you have any constraint about the time resolution?
Well, this proposal at the beginning, it is getting 100 picoseconds, and in the last collaboration meeting was okay. So 100 picoseconds is all right for them. I mean, this would be a good value. This monitoring the very effect.
Okay, because as far as I know, it would be the detector for the planet flight. So it should be less than 100. So this detector won't be able to see this.
That's true, but they want to have a detector for the next year, so they cannot dedicate too much time for a detector that have to be there. So they reach 100 picosecond, and they will try to improve this value, but if not, they will put this detector there.
So another detector will do this task.
Yes.
Thanks.
For example, this one for the stage 2.
Okay. Is there any comment or question for Marco? Otherwise, we thank again Marco.
Thanks.
So our next speaker is Nadia Mariana Leal. She will talk about the development of online software for the Totem CMS data acquisition system. So go ahead. Thank you.
Hi, so thank you. So this is a project that I developed as my thesis for my undergraduate, and I will briefly show you. So this is the overview we will go through, just a general overview of the experimental apparatus, then the main objective of the project, then The DAQ, I will not go into detail about CMS and totem DAQ, just mention briefly how the DAQ of the detector I worked on connects to those. Then I will go into the electronics and online system that we used. And finally, the main work, which was the control software for the new T2, which is the detector I worked on. And finally, the outlook and conclusion. So if you're not familiar with totem, this is one of the experiments which are in the LHC. Here we have a diagram showing the shim of the detectors, the previous shim before long shutdown 2. So these detectors are located taking the CMS interaction point, IP5, symmetrically installed from there. So before we had T1 and T2, which are charged particle detectors. And about 200 meters from this interaction point, we also have Raman bots, which are detectors that are used for measuring scattered protons, protons that scatter really close to the beam pipe. And well, I will mainly talk about the new version of the T2. So I will not go into detail about the upgrades, but I think it's important to mention, we have already seen this LHC plan of upgrades during the workshop. So during the long shutdown 2, which already passed, and we are already on long 3, the new beam pipe for the interaction point 5, which is where CMS is located, was installed. This is important because the diameter of the beam pipe is different. So for example, T2 wouldn't fit now in that section. The new T2 is located and installed around the beam pipe. So this is important to remember. And also, well, CMS and Totem have upgraded the Raman bot and moving system, as well as the telescope 2, which is now referred to as new T2 because it's a newer version. And my work focused on the development of the control software for the new T2 detector. So this is the one I will be discussing next. So this is a scheme of where the new T2 detector is located. The detector is under commissioning and it uses a different type of technology. T2 used gems and this one uses scintillators. So taking the shim in the center, we can see, well, on the left, we can see where CMS is located. So from the interaction point as a reference, the new T2 is at about 15 meters. And this is a shim of the detector. So the detector is installed symmetrically from the interaction point. So we have 2 detectors, one on each side from CMS. And here I show a shim of the scintillator planes. So we have 8 sections that make up a plane. And then they are stacked together and form like a whole unit of each detector. And as I mentioned, in the figure to the right, we can see how it's installed around the beam pipe being the gray tube. And it's installed in what previously was the caster table, and it has sliding rails. This is important because we need quick installation and easy, because it will only be used on special runs, on low luminosity runs. So we don't have time to like do a whole like process or shutdown to the installation. Okay, and going into the DAQ, here we have a scheme of how the detectors are are collecting the information. So as I mentioned, they are symmetrically installed on each side of CMS, which is what we see in the top. And then the detectors send the signal to silicon photomultipliers, which then send the signal into the digitizer board, which is the one I control with the software I developed. And then that data is sent into the FED and goes into the DAQ system. So nowadays, the totem data acquisition system is integrated and is, let's say, into the CMS data acquisition system. So although this detector is part of totem, the DAQ is within CMS. And just something that we also did after the project for the control software for the NUT2 was to kind of replicate the same software, but now with little modifications to control also the digitizer boards for the Raman bots, which are other type of detectors that I mentioned for totem. For the Raman bots, a unit has three types of Raman bots. So we have a horizontal, a top, and a bottom Raman bot. In my case, the software that we could develop is for controlling the vertical Raman bots. So it's the one that I'm showing here. Those are used for tracking, mainly for aligning at the beginning with the whole set of the Raman bots. These are the ones that are going to measure scattered photons. Okay, and why do we care, for example, about this detector? So totem is a collaboration that is dedicated to measurements of the total proton-proton cross-section and the study of elastic and diffractive proton-proton scattering of the LHC. And in this sense, the inelastic events make relevant contributions to this total cross-section. However, the CMS detector has not full coverage. It only has coverage on eta below 4.7. So this is why a complementary inelastic detector like this NUT2 with eta which is greater, it's between 5.3 and 6.5 range is really important. So what I did and what is the objective of this was the development of an online software utility written in an object-oriented programming language, C++, which controls the NUT2 detector through a control optical link. And here we have the scheme of how the setup was for the software development. So the T2 mezzanine, which is in the center, the digitizer board, is like the main part that we did the software for. And this is connected to the DOHM, which is a converter from optical to electrical signals and vice versa. And that sends information to the crate, which then goes to the main DAQ for CMS. And well, just for the testing, there also was a clock box and a local power supply. A good accomplishment was that the readout box for this detector is set up in a radiation protected zone in CMS. So this zone can be powered up and stay non-attended, given that its infrastructure is compliant with the regulations against fire and other safety requirements. So it was good because everything was done online and we can operate the detectors at any time. So this is the result. This is the interface that we ended up with. So we have these buttons that control the actions that are done to the digitizer board and then, for instance, to the detector. And we have different tabs for the FEC board, CCU, DOH control, DL25, and the read status. And here I have a comparison because the first part of this project was just the coding of these actions, let's say, to the digitizer board. And this can be simply done through a terminal, which is what I'm showing here. For example, it's a function that is called scanning device. It's a simple one because it only tells us as an output all the components that we have in the ring, and that is what is showing here. And that same thing can be easily done with just, instead of putting all the commands through the terminal, can be simply done through a button on the interface. So that's the comparison. And as I mentioned, we use that as a base to develop one that controls the vertical silicon strips Raman pots detectors. So then in this case, we have 4 CCUs compared to the first one where we only have 1, and each one has 3 GOHs. And so we have 4 different tabs with those buttons in this case, and well, the ones that we previously had. In the interface, the board CCU addresses are fixed but can be changed. Another important feature is that in the interface, we can deactivate buttons that are only meant for experts, for example. So if someone is, I don't know, on shift or something like that, it's like more safe if they don't press those buttons. So that is also a good like safety measure that can be easily implemented. Whereas on the terminal, well, it could be maybe more easily to make a mistake. So in the outlook and conclusion, so we did coding with the parsing method and for controlling the hardware components, and then migrated the same method to the process. The process is the base that I showed where the substitution with the EQ. And so yeah, we ended up with the discovery utility that controls the nearly 2 detectors as well as the Raman pot vertical silicon strips. And this is what was presented. So right now, the software has already been tested, and we have sent data successfully into CMS DAQ, although there are still some developments that need to be improved and applied. But this is mainly what it was about. So thank you.
Okay, thank you, Nadia. We have time for questions. Okay, I have one. This work is only for the round 3, or is this planned for the high luminosity?
I guess you could say that it could be used for high luminosity, but I don't think that's like the purpose, because totem in general works for low luminosity runs. So as these detectors, as I mentioned, is really close to the beam pipe. So the radiation is pretty intense in that region. So they are intended for low luminosity and special runs.
So this is only for the round 3, right?
Yeah.
Okay. Is there any other comment, question for Nadia?
The software is not a type of trigger or something like that, right?
Sorry, could you repeat?
Okay. The software is not a something like a trigger, right?
No.
No, it's only to manage the different process in the experiment. Okay.
Yes, we only control like the actions on the detector.
Oh, perfect.
And then, well, data that you collect could be used as a trigger because it inputs, for example, in CMS and into totem DAQ, and then from there you could take it as a trigger.
Perfect. Okay, thanks.
Thank you, Christoph.
Yes, so maybe just a short comment about the high luminosity situation for totem. So what was a priori decided by the LHC committee is that totem will run with CMS at high luminosity LHC if the project is fully approved. It's not 100% fully approved, but this is the intention at least for the high luminosity runs. It means that there will be no special runs during the high luminosity LHC, only high luminosity runs, and then it will be focusing more on anomalous coupling studies and this kind of studies. So this will be the goal at least.
Thank you, Christoph, for the comment. So if we can Nadia again. Our next speaker is Jose Jesus Aguilera. He's going to talk about our first approach to loop tree duality. Please go ahead.
Well, first of all, thanks to the organizers for accepting this talk. And this talk is supposed to be like the prequel of the talk of Germán Sborlini yesterday morning. So, well, here's the outline of this talk. There are like several slides, so I'm gonna try to go a bit fast. And we have a really fast introduction about loop tree duality, what it is, and what do we do in the loop tree duality, which is the iterated and the nested residues. Also the loop tree duality itself and the results we have about this loop tree duality, the direct application of the nested residues into particularly scalar diagrams. And we have some causal representations. And finally, we have a summary. Here, as an introduction, first of all, what do we do with the loop tree duality? Essentially, in the first lectures of quantum field theories, we start like looking at the standard model, and after we look at the standard model, we start studying the quantum field theories in order to understand the standard model, and then study beyond the standard model theories. But specifically, here we are going to be looking at the perturbative regime of the theories in the standard model, more specifically in scalar theories, and we are going to go directly to Feynman diagrams. And in Feynman diagrams, the idea of the loop tree duality is to apply the Cauchy residue theorem and the full formalism and methods that we applied and the results we apply is what we call the loop tree duality. So, in order to apply the loop tree duality and the Cauchy residue theorems for multi-loop diagrams, which is the idea of the loop tree duality, is that we have to apply residues one behind another in an iterated way. So a way to apply this residue theorem is essentially, if we have an amplitude, and scattering amplitude, we know that we can directly write it as a numerator times some product of scalar propagators, of Feynman propagators, which has that form. And if we look at this propagator, we can actually write it as a difference of squares, where we have these two roots here on the bottom left of the screen. And essentially, we are going to take the pole of the propagator as a positive real part of the energy component of the momentum of the internal particle. So given this, if we want to apply the Cauchy residue theorem, we have to define a contour of integration, which we essentially do, closing it around the lower half plane. So we can take the positive real part of the energy of the internal particles. So given this, if we apply directly the Cauchy residue theorem, we get some expression, which is essentially the sum of the residues of the integral, particularly in the scalar case. And the idea here is that the Cauchy residue theorem actually let us take one dimension of the integration space out. And in particular, if it's the energy of the momentum, then we go to an Euclidean space. Here, if we apply the Cauchy residue theorem, naturally, we're going to get this expression here after applying some partial fractioning to the residues of a scalar bubble diagram. This is quite nice because we see that the only divergences that we have depends essentially on the sign of the external energy, the energy of the external particle, because each of these Q1 0 plus and Q2 0 plus are the real part is positive, so it can only diverge in one of the two terms. Now, if we want to take this residue theorem to multi-loop diagrams, what we do is essentially to keep using exactly the same contour, closing below the lower half plane, which is essentially the same as writing a minus sign at the very beginning and a heaviside function at the end on the imaginary part of the poles. Now, this is given in the sum of the sum overall the poles of the propagators. Now, something quite disgusting appears when one goes on directly in the two loop case, where we have, for instance, this sunrise diagram. This is scalar sunrise diagram where we have two poles, two negative imaginary part poles that are located in the complex plane of the energy of the second particle, of the second momentum, sorry. So we have here in the diagram this pole and this Q20 plus, which is essentially the pole of the second propagator, and the dashed line corresponds to the variation of this, of the location of the second pole of the last propagator due to the real energy of the momentum of the first particle. So this gives us, if we apply the Cauchy residue theorem, we're going to have some expression that actually gives this kind of pole structure. But the point here is that the difference of these two energy components are the difference of some parameters that are going to go to zero. So we do not know essentially what is the imaginary part of this kind of pole. Fortunately, we have proved that actually the contribution to the residues of this kind of poles, which we call the displaced poles, there are the differences. They cancel pairwise. So the only contributions that we have are those that have a definite imaginary part sign. And this is quite interesting because it's not the sign, but it's just the sum of them. So this gives us an idea of how to interpret this as causal and non-causal divergences. And these causal and non-causal divergences can be understood as the flow of the momentum inside the diagram when cutting the internal edges. So in the case of the non-causal divergences, we have like different directions of the momentum flow going to the same vertex. So it makes it, it leads to divergences that needs to be concealed. But the causal divergences here actually gives some physical meaning in the diagram, in the scattering amplitude itself. Now, this is, as we know that these divergences that needs to be concealed make it like really slow and tortuous to conceal it correctly, so we can take like the real part of the scattering amplitude. Meanwhile, if we take just the causal divergences, then it becomes a bit faster. And if these divergences, if the non-causal divergences cancel in the meantime, then the computation could be even smoother and faster, even for the computation. Now, for the loop tree duality, once we have the notion of what is the iterated residues, now the idea of selecting just the poles that has a definite imaginary part sign, which is negative, then we can apply the Cauchy, the Cauchy residue theorem, but just to the poles that have a definite sign in the imaginary part, leading us to what we call the nested residue. And if we apply it to the sunrise diagram, we find essentially the same structure that we found with to the bubble diagram. So this gave us insight to define some kind of topological families, which depends essentially on the number of vertices. And if we take just the number of vertices, then we can talk about what we call the maximal loop topology, which essentially has two vertices. The next to maximal loop topology has 3 vertices, next to, and so on. 3, 4, 5 vertices and ongoing. Now, all the topological information of the number of vertices and the momentum and the momenta of the internal particles are encoded in the relations of the internal momentum between, but also with the external momentum. So this, you saw it yesterday morning in Orlin's talk, and actually the second part of this talk is this talk. So in the case of applying these negative residues to the sunrise diagram, to the MLT diagram, we find that just both one direction, leaving one internal particle of shell. And this actually gives us inner combination of all the spanning trees of the underlying graph of the Feynman diagram. Fortunately, if we again split it into partial fractionings, so we get the causal representation of the MLT. Nevertheless, if we use the loop tree duality for the NMLT, we again have a linear combination of spanning trees of this diagram, which can be written as a sum of convolutions. And also we have exactly the same result for the next to maximal loop topology diagram or family. So in one hand, we have that the nested residues lead us to contributions of all the spanning trees of a given topological family, and also give it into the and also give us an expression in terms of convolutions of topological families with lower topological complexity on the other hand. So if we have a causal representation for the maximal loop topology, can we have a causal representation of any family? Well, fortunately, it turns out that it can be. It can be obtained in the causal representation. So if we have, in the case of the sunrise diagram for the scalar case, we have this causal representation, and actually we have it in the correct form as we took it in the previous slides. And actually, if we just take the nested residues, we see some peaks out there in the left graphic, so that we see this the divergences, that the non-causal divergences that still does not cancel appears. But if we just take the causal representation, then we have a smooth surface, and it actually makes it faster for the computer. Now, in the case of the next to maximal loop topology, well, we have the causal representation just giving as cuts of these causal thresholds that we have in the sunrise diagram and the MLT diagram, which essentially is the cuts that can lead to corresponding orientations of the momentum flow in each of the internal lines in one part of each of the cuts. And in the case of the N2MLT, we have some weird expression there, but the idea is that it also can be written as a sum of multiplications of cuts. Again, these cuts are causal thresholds in this diagram, and in particular, we have performed some computations here with Monte Carlo and Fiesta, SACDEC and Fiesta. And we have, for the analytic result we obtained from the loop tree duality, we have the solid lines, and with Fiesta we have these dots. So we have a great correspondence with Fiesta and loop tree duality. In the case of SACDEC, actually the same result as Fiesta. So also from these thresholds that we found, as causal thresholds, we realized that these thresholds, in order to be able to appear in the same term of the expansion of the causal expression, should have three properties, which is these three last lines. In the first case, all the internal lines shall be on shell, I mean, after applying all the cuts. The second one is that the causal thresholds do not intersect. I mean, these cuts that we saw, they do not intersect geometrically. And also the momentum flow is compatible from one cut to another. So from the same vertex to another vertex, the flow goes, in one vertex, all the momentum flow goes out or goes inside the vertex. And in the other vertex also happens the same. All goes inside or outside the vertex. So all of this was given in Sborlini's talk quite briefly at the very beginning. And I think that as a summary, we can tell that we had that the contribution and the residue of the displaced poles actually canceled, which is something really amazing because it gives us the idea of having a causal representation of the diagram. And also the causal structure of the MLT diagram is obtained directly from the Cauchy residue theorem and directly applying the partial fractioning. And also we obtained factorization formulas to the first two topological families, and analytic reconstructions led us to the causal representation, to the causal structures of these families. So we have studied here the stability of these results, and we found like really good agreement with custom tools. So thank you very much.
Thank you. We have time for questions.
This loop tree duality has been applied to specific like QCD process, and what is the power of the method as compared with others?
Okay. Specifically into QCD, I'm not really sure. What I know is that they have been developed different tools, like in Germán Sborlini's talk, some geometrical algorithm that based on the properties of the entangled causal thresholds, it could be obtained directly the causal representation without even looking to the Feynman integral. Also, there is another partner called William Torres Bobadilla. And this guy actually built up a computational code, which is Lottie. And I think in that case, he has programmed an algorithm to develop essentially the causal representation of a diagram with some changes in the numerator, so it can be reobtained, the causal representation, independent of the nature of the internal particle specifically. But I'm not 100% sure of this last part. But in a specific case of QCD, I think we haven't, but the tools are already given, so I think it's possible to use it.
And in those algorithms, even at the formal level, as I understand you are working, is there like any hope that using machine learning can be applied?
Well, actually, I'm not sure about machine learning. I think that it's, I mean, I would like to work with machine learning to this kind of algorithms, but I'm not an expert in machine learning, so I'm gonna need to study about that. But what they have been working with is with quantum algorithms. So I'm not really sure if machine learning they've been working with. So it's a good idea to work in that line.
Okay, is there any other short question? Otherwise, we thank again the speaker, and we move to the last talk of this session. Please go ahead.
There it is. Right. Thank you. Well, as I was saying, this is part of my thesis project. Well, here's a little overview of the. I'm going to be skipping it, and straight into matter. With this work, we want to give a prediction for the mass of the heavier neutrino, and two corrections that we. Well, two corrections that we are proposing also in here that are given by those delta 1 and delta 2 primes. And we are giving these ranges for, as I was saying, the heaviest mass, the mass of the heaviest neutrino and these corrections. So a little introduction. In the standard model, we group particles given their properties. For example, in the case of the quarks, we know that the quarks all interact strongly, while for the leptons, they don't interact strongly, but they do via weak force. We also know that each family in the standard model has a different mixing, generation mixing mechanism. And for example, for leptons, it's quite larger than for quarks, and we don't know why is that. And for fermions, we know that they can have a Dirac or a Majorana mass. And as someone said earlier, sometimes 2 is just better than 1. So that's why we want to work with the Majorana masses. We use the Gell-Mann matrices, and specifically only the 3rd and the 8th. Well, these are the only ones that their diagonals are not made out of only zeros. We also use the identity matrix that I'm labeling L0, and that factor of the square root of 2/3, it's there so that it normalizes a product that we'll be seeing later. The reason we are using the Gell-Mann matrices is they form a basis for matrices of 3 by 3, and in particle physics, they also allows us to create mass matrices. All right, this is the mass matrix that we are using, and as you can see, it's just the fermion masses in the diagonal, and it's scaled by the heavier fermion in each sector. This matrix comes from the diagonalization of the mass term in the Lagrangian associated to the electroweak interaction. And well, of course, we want to reproduce the experimental data. And in this case, it's the squared mass differences for the second and 1 neutrino mass, and the 3rd and 2nd neutrino mass. To note, these values are taken from the PTG. And this is the parameter we are using in this work. Later on, as you can see there, it says the universal texture. I'm going to be talking very briefly about that concept, but basically these parameters that we are giving here, we want to calculate them in one sector and then put it in another as invariant. Oh, and that delta is just the error value. If, for example, we are computing the parameters C0, C3, and C8 for the lepton sector. And these parameters, at least for the leptonic sector, we can compute them where we can find a numerical value, or we know the masses of the electron, the muon, and the tau. This is something we can do for neutrinos, but we don't know the masses. And furthermore, we can do that for all the sectors, the quarks up and the down. And if we do this numerically, we can find that there is certain pattern, if you want to call it like that. As you can see in the C0 parameters, the values are very, very similar, and so are for the C8 parameters. The only strange one is the C3 parameters, but this may suggest the existence of a common mechanism to describe every sector. That is why we are calling it a universal texture. Well, we begin with the Dirac masses approach. Here we compute them, the parameters for neutrinos. Once again, we cannot know the numerical value because we don't know the values of M1, M2, or M3. But what we can do is to solve for and then change the parameters for those that we do know. In this case, those in the leptonic sector. And so we gain something because now the only thing we need to know, or need to find, is the value of the M3. That's the only thing we need. But as we can see here, it doesn't work. At least for the Dirac masses, it just doesn't work. We can compute the M1 and the M2 numerical, but when we create our squared masses differences, it just doesn't match with the experimental data. In the case of the 3-2 masses, it kind of does, but in the case of 2-1, it doesn't. There's an error of 1 magnitude. And we can see here more clearly that for the case of the squared mass differences for 2 and 1, it never increases, at least in this range. So, well, and since we cannot do anything more to the expressions, we really can't do anything else here. And so we begin with the Majorana masses approach. Here we are proposing 2 ways of this correction, 2 forms. One is the adding of the addition to the mass, and one is the scaling of the mass. And ultimately, what we want to accomplish is this. We want to create functions, or, well, we want to create theoretical data that matches the experimental data. All right, I'm gonna go back. So keep in mind that one is the addition and one is the scale. If we use the addition, the corrections, in the expressions that we saw before, we get to these expressions. Once again, the masses are used in terms of the third of the heavier mass and the correction that now appears in the second term of the expression. But there's a problem. When we plot the function for the squared mass differences for 2 and 1, there is a breaking in the normal ordering, and that's not something that we want or that we are considering. So just by then, we can know that something is wrong. However, if we continue with this calculation and we form some level curves, we see that the 0 level, it's there, and it kind of gets close in both expressions F1 and F2, but it never really touches. So that tells us that there's no solution. Now we go to the second case, and in this case, you remember, is the scaling. So when we make the process again, we substitute the expressions, and then we again compute, solve for M1 and M2. We get those expressions. And if we work with this, we see that there's no breaking in the normal ordering for the masses. And if we plot again the level curves for these expressions F1 and F2, we see that the 0 level curves appear and they intersect at some point. Probably that's what appears. If we zoom in that intersection, and we also add the experimental errors for the squared mass differences, we get that area of them. The F1 and F2 are the black lines, and the blue and red lines are the errors. And so from there, we can get the ranges for the mass and the corrections. And that is our prediction, that is the conclusion. And for the perspectives, we want to see how these will how to match these corrections to the electron and to the generation mixing mechanism for neutrinos. And we also want to repeat the procedure, but now using the C8 parameters to see if they match with what we have get here. And that would be all. Thank you so much.
Thank you very much. We have time for questions. Pablo.
Yeah, it was very interesting. Did you have a look to the consequences for neutrinoless double beta decay in the Majorana case?
Thank you. I haven't yet, but yes, there's since this is just the first part of my thesis, I'm considering this that for the next part. Yes.
It will be very interesting to see your results. Thank you.
Thank you so much.
Thank you, Pablo. Another question?
In your equations 10 and 11, you substitute the C parameters for charge leptons to the neutrinos. Is that correct? What you do from 10 to 11?
Do you mean? Well, I didn't get it.
The C's in equation 11 are for charged leptons, right?
Yes.
But you use them for neutrino masses.
Yes.
What are the Higgs sectors that allow you to do that?
Well, that's maybe I should say that this is just a part of a bigger project, I would say, from my coordinators of thesis. And they are proposing this model of universal texture. That is like the main reason that we are doing this. So it may not appear that right now this is right. It may seem like we are trying to do something illogical, something like that. But the model is what we are trying to prove. We are trying to prove the viability of the model.
Thank you. Another question?
Thank you for your talk. I have a question. Maybe you mentioned it, but what is, I'm not sure to understood what it is the universal texture. Can you repeat it, please?
Yes. All right. Well, this, as far as I know, as far as I understand, since I tell you, this is the universal texture constraint is not my idea. It's not my work. It's theirs. But the idea behind this is that if we look at the values of these parameters, they appear to be well, they are quite similar, and there must be a reason for that, because there's no why should there be similar for charged leptons, up quarks, down quarks? I mean, there's no really a reason behind that. So they are proposing this universal texture as an explanation of why this happens, and as a form of saying that there is a relation between three sectors, and for that matter, all sectors in the standard model. I hope that.
Thank you.
Thanks.
Yeah, probably I missed something, but I don't understand what is your motivation on your equation 14 and 15.
What is the?
Yeah,
I,
next one. No, 14 and 15, your equation 14 and 15, there.
oh, okay.
Yeah. Why you consider those cases?
Okay. Well, here are only two, but actually we made a few other cases, and it really happened something quite similar to this. Sometimes the normal ordering was broken. Sometimes it wasn't, but here in the level 0 curves they didn't intersect. So we tried with several cases, but these are the most notable, we think. So that's why they are only here. But no, we actually did more.
Excellent. Another question? Otherwise, we thank the speaker again. Okay, at the end, we only have 30 minutes delay, so it could be worse. So we have 1 hour for the posters. Please go ahead. There's coffee. I don't know if you sleep, and see you tomorrow.